Hello, and welcome to this introductory course on logic. I am Michael Genezareth from Stanford University, and I'll be leading you through the material of the course. This first session is a high-level introduction to logic, but although it's a high-level introduction, you should not ignore it. It introduces the main concepts of logic, describes how they relate to each other, and in so doing provides a mental map for organizing the many details in the sessions to follow. Let's start with a definition. Logic can be defined as the study of information encoded in the form of logical sentences. This includes both simple sentences, for example, the statement that Sacramento is the capital of California, as well as more complex sentences, such as negations, which tell us what is not true, disjunctions, which express alternatives, if-then rules, existential sentences, which assert the existence of objects without explicitly naming them, universal sentences, which state conditions that are universally true, and so forth. We use logic in almost all of our personal and professional affairs. We use the language of logic when we state observations, when we write definitions, when we encode physical laws. And we use logical reasoning in deriving conclusions from these bits of information and in convincing others of their validity. As pervasive as logic is in human affairs, it's not limited to purely human use. Logic is increasingly being used at the interface between man and machine, especially in logic-enabled computer systems, where the users can view and edit logical sentences. Think, for example, about email readers that allow users to write rules to manage incoming mail messages, deleting some, moving others to various mailboxes, and so forth, based on properties of those messages. In the business world, there are e-commerce systems that allow companies to encode price rules based on the product, the customer, the date, and so forth. Moreover, logic is sometimes used not just by users in communicating with computer systems, but by software engineers in building those systems, using languages like Prolog, illustrated here, and a programming methodology known as logic programming. In this section, we introduce the main elements of logic and illustrate those elements using sentences written in English. First of all, there are linguistic issues of syntax and semantics. What are the syntactically acceptable expressions of our logical language, and how do we know that our sentences say what we think they say? Second, there's the concept of logical entailment. Given a set of sentences that we know to be true, which other sentences must also be true, according to our semantics? Finally, there is logical reasoning. Are there symbolic manipulation procedures that we can use to derive these necessary conclusions via purely syntactic manipulation of the initial sentences? As we shall see, these three issues are closely related to each other. Consider the interpersonal relations of a small sorority. There are just 4 members: Abby, Bess, Cody, and Dana. Some of the girls like each other, but some do not. Here's one set of possibilities. Abby likes Cody, Bess likes Cody, and so forth. Let's assume that we do not know this information ourselves, but we have informants who know the girls and are willing to share what they know. Each informant knows a little about the likes and dislikes of the girls, but no one knows everything. Here's where logic comes in. By writing logical sentences, each informant can express exactly what he or she knows, no more, no less. For our part, we can combine these sentences into a logical theory, and we can use this theory to draw logical conclusions, including some that may not be known to any one of the informants. Here we see one such collection of sentences. The first sentence is straightforward. It tells us that Dana likes Cody. The second and third sentences tell us what is not true without saying what is true. The fourth sentence says that one condition holds, or another, but does not say which. The fifth sentence gives us a general fact about the girls Abby likes. The sixth sentence expresses a general fact about Cody's likes. The last sentence says something about everyone. As we go through these videos, we will occasionally come upon interactive exercises, like this one. Different exercises have different purposes. In some cases, they are simple demonstrations. In other cases, they test one's understanding of the ideas just presented. And in yet other cases, they motivate upcoming material. This exercise tests one's intuitive understanding of logic by creating various states of sorority world that satisfy the sentences like the ones we've just been seeing. Do the exercise, and when you're done, continue with the video. Sentences like the ones we have just seen constrain the possible ways the world can be. Each sentence divides the set of possible worlds into two subsets, those in which the sentence is true and those in which the sentence is false. Believing a sentence is tantamount to believing that the world is in the first set. Given two sentences, we know that the world must be in the intersection of the sets of worlds in which the first sentence is true and a set of worlds in which the second sentence is true. Ideally, when we have enough sentences, we know exactly how things stand. Unfortunately, this is not always the case. Sometimes a collection of sentences only partially constrains the world. For example, there are 4 different worlds that are consistent with our sorority world sentences. Even though the set of sentences does not determine a unique world, it's often the case that some sentences are true in every world that satisfies the given sentences. A sentence of this sort is said to be a logical conclusion from the given sentences. Or said the other way around, a set of premises logically entails a conclusion if and only if every world that satisfies the premises also satisfies the conclusion. What can we conclude from our set of sentences? Quite a bit, as it turns out. For example, it must be the case that Bess likes Cody. Also, Bess does not like Dana. There are also some general conclusions that must be true. For example, in this world with just 4 girls, we can conclude that everybody likes somebody. Also, that everybody is liked by somebody. One way of making this determination is by checking all possible worlds. For example, in our case, we notice that in every world that satisfies our sentences, Bess likes Cody. So the statement that Bess likes Cody is a logical conclusion from our set of sentences. Unfortunately, determining logical entailment by checking all possible worlds is impractical in general. There are usually many, many possible worlds, and in some cases there can be even infinitely many. The alternative is logical reasoning, namely the application of reasoning rules to derive logical conclusions and produce logical proofs. As an example, consider a proof that starts with the premises shown above and shows that Bess likes Cody. We know that Abby likes everyone that Bess likes, and we know that Abby does not like Dana. Therefore, Bess must not like Dana either. If Bess did like Dana, then Abby would like her as well. At the same time, we know that Bess likes Cody or Dana. Consequently, since Bess does not like Dana, she must like Cody. The concept of a proof, in order to be meaningful, requires that we be able to recognize certain reasoning steps as immediately obvious. In other words, we need to be familiar with the reasoning atoms out of which complex proof molecules are built. One of Aristotle's great contributions to philosophy was his recognition that what makes a step of a proof immediately obvious is its form rather than its content. It does not matter whether we are talking about blocks or stocks or sorority girls. What matters is the structure of the facts with which we are working. Such patterns are called rules of inference. As an example, consider the rule of inference shown here. If we know that all Accords are Hondas, and we know that all Hondas are Japanese cars, then we can conclude that all Accords are Japanese cars. Now consider another example. If we know that all borogoves are slithy toves, and we know that all slithy toves are mimsy, then we can conclude that all borogoves are mimsy. What's more, in order to reach this conclusion, we do not need to know anything about borogoves or slithy toves or what it means to be mimsy. What's interesting about these examples is that they share the same reasoning structure, namely the pattern shown here. The existence of such reasoning patterns is fundamental in logic, but raises important questions. Which patterns are correct? Are there many such patterns or just a few? How many do we need? Let us consider the first of these questions first. Obviously, there are patterns that are just plain wrong, in the sense that they can lead to incorrect conclusions. Consider, as an example, the faulty reasoning pattern shown here. All x are y, some y are z, therefore some x are z. Now let's take a look at an instance of this pattern. If we replace x by Toyotas, and y by Japanese, and z by made in America, we get the following line of argument, leading to a conclusion that happens to be correct. All Toyotas are Japanese, some Japanese are made in America, therefore some Toyotas are made in America. On the other hand, if we replace x by Toyotas, and y by cars, and z by Porsches, we get a line of argument leading to a conclusion that happens not to be correct. All Toyotas are cars, some cars are Porsches, therefore some Toyotas are Porsches. Not so good. What distinguishes a correct pattern from one that is incorrect is that it must always lead to correct conclusions. That is, conclusions that are logically entailed by the premises. As we will see, this is the defining criterion for what we call deduction. Of all the types of reasoning, deductive reasoning is the only one that guarantees its conclusions in all cases. It has some very special properties and holds a unique place in logic. So far, we have illustrated everything with sentences written in English. English is a good language for expressing logical information in many circumstances. However, it's not without its problems. English sentences can be grammatically complex, and they can be ambiguous. And failing to understand a sentence can lead to errors in reasoning. Even very simple sentences can be complex. Here we see two grammatically legal sentences. They are the same in all but the last word, but their structure is entirely different. In the first sentence, the main verb is blossoms, while in the second sentence, the main verb is sank, and blossoms is a noun. As another example of grammatical complexity, consider the following excerpt taken from the University of Michigan lease agreement. The university may terminate this lease when the lessee, having made application and executed this lease in advance of enrollment, is not eligible to enroll or fails to enroll in the university, or leaves the university at any time prior to the expiration of this lease, or for violations of any provision of this lease, or for violation of any university regulation relative to residence halls, or for health reasons, and so forth. The sentence in this case is sufficiently long and the grammatical structure is sufficiently complex that people must often read it several times to understand precisely what it says. As an example of ambiguity, suppose I were to write the sentence, "There's a girl in the room with a telescope." Here we see two possible meanings of this sentence. Am I saying that there is a girl in a room containing a telescope? Or am I saying there is a girl in the room and she is holding a telescope? Such complexities and ambiguities can sometimes be humorous if they lead to interpretations that the author did not intend, as in these infamous newspaper headlines with multiple interpretations. Crowds rushing to see Pope trample 6 to death. Who would have guessed that the Pope could be so cruel? British left waffles on Falkland Islands. Is the British left unclear on what to do? Or do the Brits simply not like waffles? Scientists grow frog eyes and ears. Food stamp recipients turn to plastic. Fried chicken cooked in microwave wins trip. Indian Ocean talks. I always imagine it as a deep voice. Using a formal language eliminates such unintentional ambiguities, and for better or worse, eliminates unintentional humor as well. As an illustration of errors that arise in reasoning with sentences in natural language, consider the following examples. In the first, we use the transitivity of the better relation to derive a conclusion about the relative quality of champagne and soda from the relative quality of champagne and beer and the relative quality of beer and soda. Champagne is better than beer, beer is better than soda, therefore champagne is better than soda. So far, so good. Now consider what happens when we apply the same transitivity rule in the case illustrated here. The form of the argument is the same as before, but the conclusion is somewhat less believable. Bad sex is better than nothing. Nothing is better than good sex. Therefore, bad sex is better than good sex. The problem in this case is that the use of nothing here is syntactically similar to the use of beer in the preceding example, but in English, it means something entirely different. Logic eliminates these difficulties through the use of a formal language for encoding information. Given the syntax and semantics of this formal language, we can establish simple symbolic manipulation rules that produce all and only logically entailed conclusions. In this regard, there is a strong analogy between the methods of formal logic and those of high school algebra. To illustrate this analogy, consider the algebra problem shown here. Xavier is 3 times as old as Yolanda. Xavier's age and Yolanda's age add up to 12. How old are Xavier and Yolanda? Typically, the first step in solving such a problem is to express the information in the form of equations. If we let x represent the age of Xavier and y represent the age of Yolanda, we can capture the essential information of the problem as shown here. X equals 3y, or x minus 3y equals 0, and x plus y equals 12. Using methods of algebra, we can then manipulate these expressions to solve the problem. First, we subtract the second equation from the first. Then we divide each side of the resulting equation by -4 to get a value for y. Finally, substituting back into one of the preceding equations, we get a value for x. Now consider the following logic problem. If Mary loves Pat, then Mary loves Quincy. If it is Monday and raining, then Mary loves Pat or Quincy. If it's Monday and raining, does Mary love Quincy? Yes. If it is Monday and raining, does Mary love Pat? Maybe, maybe not. If we learn that Mary loves only one person at a time, is it the case that if it is Monday and raining, that Mary loves Pat? No. How do we solve a problem like this? As with the algebra problem, the first step is formalization. Let P represent the possibility that Mary loves Pat. Let Q represent the possibility that Mary loves Quincy. Let M represent the possibility that it's Monday. And let R represent the possibility that it's raining. With these abbreviations, we can represent the essential information of this problem with the logical sentences shown here. The first says that P implies Q. That is, if Mary loves Pat, then Mary loves Quincy. The second says that M and R imply that P is true or Q is true. That is, if it's Monday and raining, then Mary loves Pat or Mary loves Quincy. Our job is to prove that M and R implies that Q is true. That is, if it's Monday and raining, then Mary loves Quincy. Given this formalization, we can use a reasoning rule analogous to the rule for subtracting equations to answer our question. We notice that P occurs on the left-hand side of one sentence and on the right-hand side of the other. Whenever this occurs, our rule allows us to cancel the P and thereby derive the conclusion that if it's Monday and raining, then Mary loves Quincy or Mary loves Quincy. Dropping the repeated symbol on the right-hand side, we arrive at the simpler conclusion that if it's Monday and raining, then Mary loves Quincy. We can use a similar approach to show that if Mary loves only one person at a time, that Mary does not love Pat. This example is interesting because it showcases our formal language for encoding logical information. As with algebra, we use symbols to represent relative aspects about the world, and we use operators to connect these symbols in order to express information about the things those symbols represent. The example also introduces one of the most important operations in logic, namely resolution. In this case, a restricted form of resolution. Resolution has the property of being complete for an important class of logic problems. That is, it's the only operation necessary to solve any problem in this class. This exercise tests your understanding of formalization using these logical operators. The existence of a formal language for representing information and the existence of a corresponding set of mechanical manipulation rules have an important consequence, namely the possibility of automated reasoning using digital computers. The idea is simple. We use our formal representation to encode the premises of a problem as data structures in a computer, and we program the computer to apply our mechanical rules in a systematic way. The rules are applied until the desired conclusion is attained, or until it's determined that the desired conclusion cannot be attained. Unfortunately, in some cases, this determination cannot be made and the procedure never halts. However, in many practical cases it works, and the idea is basically sound. Today, the prospect of automated reasoning has moved from the realm of possibilities to that of practicality, with the creation of logic technology in the form of 1. Standard logical languages, 2. Automated reasoning systems, and 3. The development of knowledge bases, definitions, physical laws, artificial laws, and so forth. The emergence of this technology has led to its application in a wide variety of areas. To begin with, there are obvious applications in mathematics. Automated reasoning programs can be used to check proofs, and in some cases can produce proofs by themselves, or at least portions of those proofs. For example, given the axioms of group theory, which assume the existence of a right inverse for the group's operator, it's a simple matter for an automated theorem-proving system to prove that the inverse is also a left inverse. Over the years, automated reasoning methods have been used to prove or verify proofs of many fundamental theorems in mathematics. There are libraries of problems to use in testing theorem provers, such as the TP library. And there are annual competitions pitting theorem provers against each other, most notably the competition at the annual conference on automated deduction. Engineers can use the language of logic to write specifications for their products and to encode their designs. Automated reasoning tools can be used to simulate those designs and in some cases validate that the designs meet their specifications. Such tools can also be used to diagnose failures and to develop testing programs. By conceptualizing database tables as sets of simple sentences, we can use logic in support of database systems. For example, the language of logic can be used to define virtual views of data in terms of explicitly stored tables, such as this definition of grandparent in terms of parent. And it can be used to encode constraints on databases, such as this constraint that people cannot be their own parents, or this second constraint that people cannot be the parents of their parents. Automated reasoning techniques can be used to compute new tables and to detect problems and to optimize queries. Logical spreadsheets generalize traditional spreadsheets to include logical constraints as well as traditional arithmetic formulas. Examples of such constraints abound. For example, in scheduling applications, we might have timing constraints or restrictions on who can reserve which rooms. In the domain of travel reservations, We can have constraints on adults and infants. In academic program sheets, we might have constraints on how many courses of varying types that students must take. And there are applications in law and business. The language of logic can be used to encode regulations and business rules. For example, as shown here, we can define the concept of an office mate, and we can use that concept in expressing a business rule about office assignments. Given such rules, automated reasoning techniques can be used to analyze such regulations for consistency and overlap and so forth. This exercise allows you to try out a very simple logical spreadsheet. Before finishing this session, I want to make some general remarks about the course. First of all, a few words about background. The course presumes that you are comfortable with symbolic manipulation, as used, for example, in solving high school algebra problems like the one we saw earlier. The course also presumes some basic mathematical background. In particular, it assumes that you understand sets, set operations, such as union and intersection, and set relations, such as membership and subset. And it presumes that you are familiar with functions and relations. However, nothing else is required. If you have this background, you should be fine. If not, you might want to brush up on these things before continuing. Next, a few words about how to proceed through the course. The course consists of these lectures, lecture notes, additional readings, and exercises. All four are useful. While it may be tempting to do so, do not skip the exercises. They reinforce points made in the lectures and the readings, and in some cases they motivate subsequent material. Also, consider taking advantage of communication aids to discuss issues with others taking the course. Post questions that are bothering you, and if you know the answers to questions posted by others, help out by answering. Explaining material to others is one of the best ways of learning a subject. Although logic is a single field, there's more than one logic in this field. In the three main units of this course, we look at three different types of logic, each more sophisticated than the last. Propositional logic is the logic of propositions. Symbols in the language represent conditions in the world, and complex sentences in the language express interrelationships among these conditions. Primary operators are Boolean connectives such as and, or, and not. Relational logic expands upon propositional logic by providing a means for explicitly talking about individual objects and their interrelationships, and not just monolithic conditions. In order to do so, we expand our language to include object constants, function constants, relation constants, variables, quantifiers, and so forth. Epistemic logic goes one step further and provides a means for talking about sentences as objects in their own right, and providing operators for expressing relationships between expressions and other expressions, and relationships between expressions and the things they represent. This extension allows us to encode information about information and allows us to define the notions of truth and belief within logic itself. Each logic brings new issues and capabilities to light. Despite these differences, there are many commonalities among the logics. In particular, in each case, there is a language with a formal syntax and a precise semantics. There is a notion of logical entailment, and there are legal rules for manipulating expressions in the language. These similarities allow us to compare the various logics and to gain an appreciation of the trade-offs between expressiveness and computational complexity. One final comment. In hopes of preventing difficulties, it's worth pointing out a potential source of confusion. This course exists in the meta world. It contains sentences about sentences. It contains proofs about proofs. In some places, we use similar mathematical symbology, both for sentences in logic and sentences about logic. Wherever possible, we try to be clear about this distinction, but the potential for confusion remains. Unfortunately, this comes with the territory. We're using logic to study logic. It's our most powerful intellectual tool. First logic we treat in this course is called propositional logic. As its name suggests, propositional logic is concerned with propositions and their interrelationships. The notion of a proposition here cannot be defined precisely. Roughly speaking, a proposition is a possible condition of the world that is either true or false. For example, the possibility that it is raining, the possibility that it's cloudy, and so forth. The condition need not be true in order for it to be a proposition. In fact, we might want to say that it is false, or that it is true if some other proposition is true. In this first session, we first look at the syntactic rules for the language of propositional logic. We then look at the meaning, or semantics, of expressions specified by these rules. We then talk about the processes of evaluation and satisfaction. And finally, we define propositional entailment, which identifies for us all of the logical conclusions one can draw from any set of propositional sentences. In propositional logic, there are two types of sentences: simple sentences and compound sentences. Simple sentences express simple facts about the world. Compound sentences express logical relationships between the simpler sentences of which they are composed. In propositional logic, simple sentences take the form of atomic symbols called proposition constants. By convention, we write proposition constants as strings of letters, digits, and occurrences of the underscore character. In order to avoid conflict with other types of symbols we use later, we require that every proposition constant begin with a lowercase letter. For example, raining, spelled as shown here, is a proposition constant, as are raining, spelled with lower and uppercase letters, but beginning with a lowercase letter, are 32 raining, and raining underscore or underscore snowing. Raining beginning with a capital letter is not a proposition because it begins with an uppercase letter. 3, 2, 4, 5, 6, 7 is not a proposition constant because it begins with a number. Raining hyphen or hyphen snowing fails because it contains the dash or dash character or minus sign. Compound sentences are formed from simpler sentences and logical operators of various sorts. There are 6 types of compound sentences in propositional logic. A negation consists of the negation operator followed by a simple or compound sentence, all enclosed in parentheses. For example, given the sentence P, we can form the negation of P as shown here. The argument of a negation is often called the target of the negation. A conjunction is a sequence of sentences separated by occurrences of the AND operator and enclosed in parentheses. For example, we can form the conjunction of P and Q as shown here in the middle. The AND operator is usually written using this wedge-like symbol, though occasionally we use ampersand, for example in typing formulas for application programs. The constituent sentences of a conjunction are called conjuncts. A disjunction is a sequence of sentences separated by occurrences of the OR operator and enclosed in parentheses. For example, we can form the disjunction of P and Q as shown in the example at the bottom. The OR operator is usually written using this upside-down V, though we sometimes use vertical bar as an alternative, again when we're typing for application programs. The constituent sentences in a disjunction are called disjuncts. 3 down, 3 to go. An implication consists of a pair of sentences separated by the implication operator and enclosed in parentheses. The sentence to the left of the operator is called the antecedent, and the sentence to the right is called the consequent. The implication of P and Q is shown here in the example at the top. A reduction is the reverse of an implication. It consists of a pair of sentences separated by the reduction operator and enclosed in parentheses. In this case, the sentence to the left is called the consequent, and the sentence to the right is called the antecedent. An equivalence or biconditional is a combination of an implication and a reduction, and we can express it as shown here at the bottom. Note the constituent sentences with any compound sentence can be either simple sentences or compound sentences, or a mixture of the two. For example, the expressions here are all legal compound sentences. One disadvantage of our notation, at least as written, is that the parentheses tend to build up and need to be matched correctly. It would be nice if we could dispense with unnecessary parentheses, as shown in the example at the middle. Unfortunately, we can't do without parentheses entirely, since then we would be unable to render certain sentences unambiguously. For example, the two different sentences shown here would result in the same unparenthesized expression, even though they mean different things. The solution to this problem is the use of operator precedence. The table shown here gives a hierarchy of precedence for our operators. The negation operator has higher precedence than any of the other operators. And has higher precedence than OR and the remaining operators. And OR has higher precedence than the implication operator, the reduction operator, or the equivalence operator. And those last three operators have equal precedence. In unparenthesized sentences, it's often the case that an expression is flanked by operators, one on either side. In interpreting such sentences, the question is whether the operator associates with the operator whether the expression associates with the operator to its left or to its right. We can use precedence to make this determination. In particular, we agree that an operand in such a situation always associates with the operator of higher precedence. When an operand is surrounded by operators of equal precedence, the operand associates to the right by convention. The examples here show how these rules work in various cases. Expressions on the right are the fully parenthesized versions of the expressions on the left. In the first case, Q in the middle is associated with the AND because AND has higher precedence than OR. Similarly, in the second sentence, Q is associated with the AND on the right side, since again, AND has higher precedence than OR. In the next two cases, the association is to the right because the operators are of equal precedence. And then the final example, P is associated with not because it's the operator with the highest precedence of all. That's all for syntax. Let me just summarize with a few definitions. We use the phrase propositional vocabulary to refer to a set or sequence of propositional constants. Given a propositional vocabulary, a propositional sentence is either an individual member of this propositional vocabulary, or it's a compound sentence formed from simpler sentences built from this vocabulary. Finally, a propositional language is the set of all propositional sentences that can be formed from a propositional vocabulary. This exercise tests your grasp of the rules of syntax by asking you to determine whether various expressions are syntactically legal sentences in propositional logic. The semantics of logic, in other words, the meanings of propositional sentences, is similar to the semantics of algebra. Algebra is unconcerned with the real-world significance of variables like x. What is interesting is the relationship between those variables expressed in our equations, and algebraic methods are designed to respect these relationships, no matter what meanings or values are assigned to the constituent variables. In a similar way, logic is unconcerned with what sentences say about the world being described. What is interesting from a logical point of view is the relationship between the truth values of simple sentences and the truth values of compound sentences within which the simple sentences are contained. Moreover, logical reasoning methods are designed to work no matter what meanings or values are assigned to the proposition constants used in sentences. Although logic does not prescribe inherent values for proposition constants, in analyzing logic, it's useful to consider the values that logic users associate with proposition constants. Such associations are often called truth assignments. Formally, a truth assignment for propositional logic is a mapping assigning a truth value to each of the simple sentences in the language. In what follows, we use the symbol 1 as a synonym for true and 0 as a synonym for false. We refer to the truth value assigned to a propositional sentence using a truth assignment I by superscripting the sentence with I as the superscript. The assignment shown here is an example for the case of a logical language with just 3 proposition constants, namely P, Q, and R. P is assigned the value 1 for true, Q is assigned the value 0 for false, and R is assigned the value 1, again, for true. Note that the expressions written here are not themselves sentences in propositional logic. Propositional logic does not allow superscripts and does not use the equals symbol. Rather, these are informal meta-level statements about particular truth assignments. Although talking about propositional logic using a notation similar to propositional logic itself can sometimes be confusing, it allows us to convey meta information of this sort precisely and efficiently. To minimize the problems in this course, we use such meta notation infrequently and only when there is a little chance of confusion. A sentential truth assignment, as opposed to a propositional assignment, is an association between arbitrary sentences in a propositional language and the truth values 1 and 0. Unlike propositional truth assignments, sentential truth assignments are not arbitrary. Given a truth assignment for the proposition constants of a language, the semantics of logic fixes the truth assignment for all compound sentences in that language. Viewed another way, we can extend any propositional truth assignment to a sentential truth assignment by using the semantics of the logical operators in our sentences. Let's start with negation. If the truth value of a sentence is true in a truth assignment, then the truth value of its negation must be false. If the truth value of a sentence is false, then the truth value of its negation must be true. For example, if the truth value of P is 0, then the truth value of its negation is 1. If the truth value of a conjunction is 1, then the truth value of the negation of that conjunction must be 0. The truth value of a conjunction is true under a truth assignment if and only if the truth values of its conjuncts are both true. Otherwise, the truth value is false. The truth value of a disjunction is true if and only if the truth value of at least one of its disjuncts is true. Otherwise, the truth value is false. The type of disjunction here is called inclusive OR, which says that a disjunction is true if at least one of its disjuncts is true. This contrasts with exclusive OR, which says that a disjunction is true if only an odd number of its disjuncts is true. What about implication and reduction? These two are not quite so obvious as negation, conjunction, and disjunction. And in fact, in some variants of propositional logic, these operators are defined in different ways. The version given here is called material implication. The truth value of an implication is true if and only if its antecedent is false or if its conclusion is true. The case of reduction is analogous. The semantics deserves a few words of explanation. The intuition behind an implication is that the truth of the antecedent requires the truth of the consequent. So clearly, if the antecedent is true and the consequent is false, then the sentence as a whole must be false. This fixes the second row of the implication table. If the antecedent is true and the consequent is also true, then it makes sense to say that the implication is true. But what about the case when the antecedent is false? Such sentences are usually called counterfactuals. Intuitively, we might think that when the antecedent is false, an implication tells us nothing whatsoever about the consequent. Logicians have captured this, somewhat arbitrarily, by saying that the sentence as a whole is true whenever the antecedent is false, no matter whether the consequent is true or false. Some people find such counterfactuals disturbing. Consider the sentence, "If George Washington is alive, I am a billionaire." In the real world, this sentence is true, given our semantics, since George Washington is not alive. This feels wrong to some people because the antecedent seems to have nothing to do with the consequent. The good news is that, other than this slight oddity, everything works out very nicely with the semantics, as we shall see. Finally, we get to equivalence, and this is an easy case. An equivalence is defined to be true if and only if the truth values of its constituents agree. In other words, they are either both true or both false. Given a propositional truth assignment and these definitions for operators, we can compute the truth value of any sentence in the language. The technique is quite simple. We first replace the proposition constants in our sentence with their values in our truth assignment, forming an expression consisting of ones and zeros and logical operators. We use our operator semantics to evaluate sub-expressions with these truth values as arguments. We then repeat working from the inside out until we have a value for the sentence as a whole. Here's a simple example. We start with a formula and a truth assignment for a language with 3 proposition constants. We replace the constants in the formula with their truth values. We replace the negation by its value, in this case 1 or true. Next, we replace the 2 disjunctions with their values, both 1. Finally, we evaluate the conjunction to get a value for the entire sentence. Here's a more complex example. In this case, we are using propositional logic in digital circuit analysis. There are 3 input nodes, some internal nodes, and 2 output nodes. There are gates connecting these nodes to each other, 2 XOR gates shown at the top, 2 AND gates in the lower left, and an OR gate in the lower right. In our model, each node in the circuit corresponds to a distinct proposition constant. Using the language of logic in this vocabulary, we can capture the relationship between the values of the nodes as propositional sentences. For example, the output of the first AND gate is 1 if and only if the 2 inputs are 1. With this encoding, we can write a formula for the truth value of the second output of the overall circuit in terms of the truth values of the 3 inputs of the entire circuit. This formula then holds no matter what the inputs are. We can then use evaluation to simulate our circuit. First, we replace the proposition constants with their truth values. We simplify our negations. We simplify our basic conjunctions. We simplify one disjunction, the resulting conjunction, and the remaining disjunction to get a value of 1 for the sentence as a whole. This exercise tests your understanding of evaluation by asking you to determine the truth values of various sentences for a given truth assignment. Let's finish up our discussion of semantics with a few definitions for future use. We say that a truth assignment satisfies a sentence if and only if it assigns the value 1 to that sentence. A truth assignment falsifies a sentence if and only if it assigns the value 0 to the sentence. A truth assignment satisfies a set of sentences if and only if it satisfies every element of the set. And a truth assignment falsifies a set of sentences if and only if it falsifies at least one element in the set. In evaluation, we start with a propositional truth assignment and use that truth assignment to determine the truth value of compound sentences. Satisfaction is the opposite of evaluation. We begin with one or more compound sentences that we believe to be true and try to find a propositional truth assignment that satisfies those sentences. Recall the circuit example we saw earlier. In that example, we used evaluation to compute the output of the circuit for a given set of inputs. Using satisfaction, we go the other way, finding a set of inputs that would give us a particular output. If you're thinking that this is more complicated than evaluation, you're right. One way to do this is using a truth table for our language. Truth table for a propositional language is a table showing all of the possible truth assignments for the proposition constants in the language. Here we see a truth table for a propositional language with 3 proposition constants. Each column corresponds to an individual constant. Each row corresponds to a single truth assignment. For a language with n constants, there are clearly 2 to the n truth assignments. Here's an intuitively simple method of finding truth assignments using truth tables. First, we create a truth table for the proposition constants, and we add columns for each sentence in our set. We then evaluate each sentence for each of the rows of the truth table, and finally, any row that satisfies all the sentences in the set is a solution to the problem. Let's look at an example. Suppose we want to find a truth assignment that satisfies the sentences Q implies R, P implies Q and R, and not R. The first step is to form a truth table for our language and add columns for the sentences in our set, as shown here. Next, we evaluate the first sentence in our set, Q implies R, for each of the truth assignments in the table. Here we assign false to every row in which Q is true and R is false, and we assign true to the remaining rows. Next, we evaluate the sentence P implies Q and R for each row. Here we assign false to every row in which P is true and either Q or R is false. Finally, we assign false to every row that does not satisfy not R. That is, we assign false to every row in which R is true. When we're done, we notice that there's just one row in which all of our sentences are true, namely the truth assignment that makes all proposition constants false. Of course, the satisfaction procedure does not always terminate with a single truth assignment, as in this case. Sometimes there can be more than one. Sometimes there can be no truth assignments whatsoever. This exercise tests your understanding of satisfaction by asking you to select truth assignments that satisfy various propositional logic sentences. Evaluation and satisfaction are processes involving sentences and specific truth assignments. In logic, we are sometimes more interested in the properties of sentences that hold across different truth assignments. In particular, sentential truth assignment imposes a classification of sentences in a language based on whether or not there are truth assignments that satisfy that sentence. A sentence is valid, for example, if and only if it is satisfied by every truth assignment. A sentence is unsatisfiable if and only if it is satisfied by no truth assignment. And a sentence is contingent if and only if there is some truth assignment that satisfies it and some truth assignment that falsifies it. It is frequently useful to group these classifications as shown here. A sentence is satisfiable if and only if it is either valid or contingent. That is, if and only if there is at least one truth assignment that satisfies it. A sentence is falsifiable if and only if it is either contingent or unsatisfiable. That is, if and only if there is at least one truth assignment that falsifies it. We can check whether a sentence is valid or contingent or unsatisfiable by evaluating it for all truth assignments. In the example here, we show that the sentence P implies Q or Q implies R is always true. In other words, it's valid. Looking at P implies Q, we note that it is true except when P is true and Q is false. Look, the sentence Q implies R is true except when Q is true and R is false. Combining these two, we see that the overall sentence is true whenever either of these components is true, and in this case we notice that it's true for every row of the table. Hence the sentence is valid. There are many examples of validities. Some of them even have names. There's double negation, P if and only if not P. De Morgan's laws, which allow us to distribute negation over conjunction and disjunction. implication introduction, implication distribution, and so forth. This exercise tests your understanding of these concepts by asking you to say whether various sentences are valid, contingent, or unsatisfiable. Validity, satisfiability, and unsatisfiability are properties of individual sentences. In logical reasoning, we are not so much concerned with individual sentences as we are with the relationships between sentences. In particular, we would like to know, given some sentences, whether other sentences are or are not logical conclusions. This relative property is known as logical entailment. When we're speaking about propositional logic, we sometimes use the phrase propositional entailment. By definition, a set of sentences, delta, logically entails a sentence phi if and only if every truth assignment that satisfies delta also satisfies phi. In what follows, we will use this notation shown here, where we write delta, then what's called the double turnstile, a vertical bar followed by an equal sign, and phi as our way of notating the statement that a set of premises delta logically entails phi. As an example of this concept, we can say that the sentence P logically entails the sentence P or Q. Since the disjunction is true whenever one of its disjunctions is true, then P or Q must be true whenever P is true. On the other hand, the sentence P does not logically entail P and Q. The conjunction is true if and only if both of its conjuncts are true, and Q might be false. Of course, any set of sentences containing both P and Q must logically entail the single sentence P and Q. Note the relationship of logical entailment is a logical one. Even if the premises of a problem do not logically entail a conclusion, this does not mean that the conclusion is necessarily false. Even if the premises are true, it just means that it's possible that the conclusion is false. Note also that logical entailment is not the same as logical equivalence. The sentence P logically entails P or Q, but P or Q does not logically entail P. Logical entailment is not so much analogous with arithmetic equality as it is with arithmetic inequality. One way of determining whether or not a set of premises logically entails a possible conclusion is to check the truth table for the proposition constants in the language. This is called the truth table method. First, we form a truth table for the proposition constants and add a column for the premises and a column for the conclusion. We then evaluate the premises, we evaluate the conclusion, and we compare the results. If every row that satisfies the premises also satisfies the conclusion, then the premises logically entail the conclusion. Otherwise, they don't. As an example, let's use this method to show that P logically entails P or Q. We set up our truth table and add columns for our premises and the conclusion. In this case, the premise is just P, and so evaluation is straightforward. We just copy the first column. The conclusion is true if and only if P is true or Q is true. Finally, we notice that every row that satisfies the premise also satisfies the conclusion. Hence, P logically entails P or Q. Now let's do the same for the premise P and the conclusion P and Q. We set up our table as before and evaluate our premise. In this case, there's only one row that satisfies our conclusion. Finally, we notice that the assignment in the second row satisfies our premise but does not satisfy our conclusion. So logical entailment does not hold in this case. Finally, let's look at the problem of determining whether a set of premises consisting of the sentence P as well as the sentence Q logically entails the sentence P and Q. Here we set up our table as before, but this time we have two premises to satisfy. Only one truth assignment satisfies both premises, and this truth assignment also satisfies the conclusion. Hence, in this case, logical entailment does hold. As a final example, let's return to the love life of the fickle Mary. Here is a slightly simplified version of the problem from the course introduction. We know P implies Q, that is, if Mary loves Pat, then Mary loves Quincy. We know M implies P or R, that is, if it's Monday, then Mary loves Pat or Quincy. And let's say we know that it is Monday. Let's show that Mary loves Quincy. To make this determination, we form the truth table for our language. We evaluate each of our premises, and we evaluate our conclusion. Finally, we check that the conclusion is satisfied in every row that satisfies the premises. Hence, in this case, we can say that Mary loves Quincy is a logical conclusion from the premises. Note that logical entailment and satisfiability have an interesting relationship to each other. In particular, if a set of delta of sentences logically entails a sentence phi, then delta together with a negation of phi must be unsatisfiable. The reverse is also true. If delta and the negation of phi is unsatisfiable, then delta must logically entail phi. This is guaranteed by a meta-theorem called the unsatisfiability theorem, shown here, with a small proof that it's correct. An interesting consequence of this is that we can determine logical entailment simply by checking for unsatisfiability. Finally, as an exercise in using some of the concepts introduced in this section, let's consider the following problem. Stanford people always tell the truth, and Berkeley people always lie. Unfortunately, by looking at a person, you cannot tell whether he is from Stanford or Berkeley. You come to a fork in the road and want to get to the football stadium down one fork. However, you do not know which road to take. There is a person standing there. What single question can you ask him to help you decide which fork to take? There are a number of ways to approach this problem. The most interesting involves a question in which a person is asked how he would answer if he were from Stanford or if he were from Berkeley. However, we can also approach the problem without entertaining such meta-level questions. Let's draw out a table with a set of all possible states of affairs, and leave columns for the question we want to ask and the response we want to receive. We want to ask a question that will elicit one response, let's say true or 1, if the stadium is to the left, and a different response, for example, false or 0, if the stadium is to the right. Note that the response in each case may differ from the actual truth of the question depending on whether the informant is from Stanford or from Berkeley. Now let's see what the actual truth value of a question must be to elicit this response. If the stadium is actually to the left and the informant is actually from Stanford, then we want a question that has value true. If the stadium is not to the left and the informant is from Stanford, then we want a question with truth value false. Since Stanford person is going to tell the truth, the value should be the same as the values in our response. The opposite is true for the Berkeley cases. If the stadium is to the left and the informant is from Berkeley, we want a question that has truth value false, since the informant will lie. If the stadium is not to the left and the informant is from Berkeley, then we want a question that has truth value true. Now, looking at our operator semantics tables, we see that this is exactly the set of truth values assigned to the sentence left if and only if SU, Stanford. So we can phrase this as a question as follows. Is it the case that the left road is the way to the stadium if and only if you are from Stanford? Okay, that's not a particularly clever or simple question, but it will elicit the right response. Importantly, the example illustrates that it's possible to solve problems of this sort using just the concepts we have seen so far. In our last lesson, we defined the notion of logical entailment. A set of premises logically entails a conclusion if and only if every truth assignment that satisfies the premises also satisfies the conclusion. We also saw that it's possible to determine logical entailment by looking at the truth table for our language. Checking logical entailment with truth tables has the merit of being conceptually simple. However, it's not always the most practical method. The number of truth assignments of a language grows exponentially with the number of logical constants. When the number of logical constants in a propositional language is large, it may be impossible to process its truth table. Proofs provide an alternative way of checking logical entailment that addresses this problem. A proof is the result of the symbolic manipulation of sentences rather than the enumeration of truth assignments. Importantly, it's possible to create a proof of a conclusion from a set of premises that is much smaller than the truth table for a language. Moreover, it's often possible to find such proofs with less work than is necessary to check an entire truth table. We begin this lesson with a discussion of simple linear proofs. We then move on to hierarchically structured proofs, where proofs can be nested inside of other proofs. And once we have seen both linear and structured proofs, we show how they are combined in the popular Fitch proof system. We finish with definitions for soundness and completeness, the standards by which proof systems are judged. As we saw in the introductory lesson, the essence of logical reasoning is symbolic manipulation. We start with our premises, apply some rules of inference, stringing together these rule applications to form linear proofs. The idea is simple. Getting the details right requires a little care. Let's start with some definitions. A schema is an expression satisfying the grammatical rules of our language, except for the occurrence of metavariables in place of various parts of the expression. For example, the expression shown here is a schema with metavariables phi and psi. A rule of inference is a pattern of reasoning consisting of some schemas, called premises, and one or more additional schemas, called conclusions. Rules of inference are often written as shown here. The schemas above the line are the premises, and the schemas below the line are the conclusions. As we shall see, the meaning of a rule of inference is that we can derive an instance of the conclusion whenever we have corresponding instances of the premises. The rule in this case is called implication elimination because it eliminates the implication from the first premises. It's also sometimes called modus ponens. An instance of a rule of inference is the rule obtained by consistently substituting legal sentences for the metavariables in the rule. For example, the rules on the bottom of the here are both instances of the implication elimination rule. In the first instance, we replace both occurrences of phi by p, and we replace both occurrences of psi by q. In the second instance, we replace both occurrences of phi by p implies q, and we replace both occurrences of psi by q implies r. A rule applies to a set of sentences if and only if there's an instance of the rule in which all of the premises are in that set. In this case, the conclusions of the instance are the results of the rule application. Here's an example. We have a set of 3 sentences to start. Our rule is implication elimination. On the right here, we have an instance of this rule. Both premises are in the set. We have p implies q, and we have p. Consequently, we can derive the result q. Here's another example. In this case, we have the same set of sentences and the same rule, but a different instance. Again, the premises are in our set. We have p implies q implies r. We have p implies q, and so we can derive the conclusion q implies r as a result. Same rule of inference, 2 different results. Note that it's okay to have rules of inference with no premises. Rules with no premises are sometimes called axiom schemata. That's the plural of axiom schema. Axiom schemata are usually written without horizontal lines, like the ones used in ordinary rules of inference. An axiom schema allows us to derive any instance of the schema that we like without any premises whatsoever. Sentences at the bottom of the slide here are examples. Here are some common axiom schemata. The schema we just saw is called implication creation. The implication distribution axiom schema allows us to distribute one implication over another. If a sentence phi implies that psi implies chi, then if phi implies psi, then phi implies chi. The contradiction realization axiom schema permits us to infer the negation of a sentence if the negation of that sentence implies some sentence and its negation. By stringing together applications of rules of inference, it's possible to derive conclusions that cannot be derived in a single step. The idea of stringing together rule applications leads to the notion of a linear proof. Linear proof of a conclusion from a set of premises is a sequence of sentences terminating in the conclusion, in which each item is either a premise, or an instance of an axiom schema, or the result of applying a rule of inference to earlier items in the sequence. Here's an example. Suppose we have a set of sentences we saw earlier. We start our proof by writing out our premises. We believe P, we believe P implies Q, and we believe that P implies Q implies that Q implies R. Using implication elimination on the first premise and the second premise, we derive Q. Applying implication elimination to the second premise and the third premise, we derive Q implies R. Finally, we used the derived premises on lines 4 and 5 to arrive at our desired conclusion. Here's a somewhat more complicated example. This one illustrates the use of axiom schemata. Whenever P is true, Q is true. Whenever Q is true, R is true. With these as premises, we can prove that whenever P is true, R is true. On line 3, we write down an instance of implication creation. Q implies R implies that P implies Q implies R. From this conclusion and premise 2, we use implication elimination to derive the sentence P implies Q implies R. On line 5, we write down an instance of implication distribution. If P implies that Q implies R, then if P implies Q, then P implies R. We combine the conclusions from lines 4 and 5 to derive the sentence on line 6. And finally, we use implication elimination once again to derive the overall conclusion. It's not an easy proof, not a trivial proof, but it works. Later in this lesson, we'll see how to produce a simpler proof of this very same result. This exercise tests your grasp of proofs by asking you to produce a multi-step proof using implication elimination. The collection of rules of inference is called a proof system. Let R be a proof system if there exists a proof of a sentence phi from a set delta of premises using the rules of inference in R. We say that phi is provable from delta using R. We usually write this as shown here using the provability operator, which is sometimes called a single turnstile. If the set of rules is clear from context, we usually drop this subscript. The Mendelssohn system is a well-known proof system for propositional logic. It consists of the implication rule of inference that we just saw and the 3 axiom schema that we saw. The Mendelssohn system is interesting in that it is sufficient to prove all logical consequences from any set of premises in propositional logic using only the operators not and implication. And as we shall see later, this subset of sentences is interesting because for every sentence of propositional logic, there's a logically equivalent sentence that can be written in terms of these 2 operators. The downside is the proofs in the Mendelssohn system can be a little complicated. The good news is we can eliminate much of this complexity by moving from linear proofs to structured proofs. In this segment, we turn our attention to proofs of a different sort, called structured proofs. Structured proofs are similar to linear proofs in that they consist of sequences of reasoning steps. However, they differ from linear proofs in that there's more structure. In particular, in structured proofs, groups of sentences can be grouped together into subproofs nested within outer superproofs. Here's an example. It resembles a linear proof, except that we have grouped the sentences on lines 3 through 5 into a subproof within our overall proof. The main benefit of structured proofs is that they allow us to prove things that cannot be proved using only ordinary rules of inference. In structured proofs, we can make assumptions within subproofs. We can prove conclusions from those assumptions, and from those derivations we can derive implications outside of those subproofs, with our assumptions as antecedents and our conclusions as consequents. Structured proof shown here illustrates this. On line 3, we begin a subproof with the assumption that P is true. Note that P is not a premise of the overall problem. In a subproof, we can make whatever assumptions that we like without contaminating the outer proof. From P, we derive Q using the premise on line 1, and from that Q, we prove R using the premise on line 2. And that terminates the subproof. Finally, from the subproof, we derive P implies R in the outer proof. Given P, we can prove R, and so we know P implies R. The rule used in this case is called implication introduction, or II for short. As this example illustrates, there are 3 basic operations involved in creating structured proofs. 1, making assumptions. 2, using ordinary rules of inference to derive conclusions. And 3, using structured rules of inference to derive conclusions outside of subproofs. Let's look at each one of these operations in turn. In a structured proof, it's permissible to make an arbitrary assumption in any nested proof. The assumptions need not be members of the initial premise set. Note that such assumptions cannot be used directly outside of the subproof, only as conditions in derived implications, so they do not contaminate the superproof or any unrelated subproofs. For example, in the proof we just saw, we used this assumption operation in the nested subproof, even though P was not among the given premises. An ordinary rule of inference applies to a particular subproof of a structured proof if and only if there's an instance of the rule in which all of the premises occur earlier in the subproof or in some superproof of that subproof. Importantly, however, it's not permissible to use sentences in subproofs of that subproof or in other subproofs of its superproofs, only in the subproof itself and the superproofs of that subproof. For example, in the structured proof we've been looking at so far, it's okay to apply implication elimination to 1 and 3. And it's okay to use implication elimination on lines 2 and 4. However, it's not acceptable to use a sentence from a nested subproof in applying an ordinary rule of inference to an outer proof, as illustrated here. This sort of reasoning can be formalized with a new type of rule of inference. Like an ordinary rule of inference, a structured rule of inference is a pattern of reasoning consisting of some premises and 1 or more conclusions. As before, the premises and conclusions can be schemas. However, the premises can also include conditions of the form phi proves psi, as in the example shown here. The rule in this case is called implication introduction because it allows us to introduce new implications. A structured rule applies to a particular subproof of a structured proof if and only if there's an instance of that rule that satisfies the following conditions. A premise of the form phi proves psi is satisfied if and only if there's an earlier subproof within the current proof where phi is the only premise and psi is any conclusion. In other words, if the earlier subproof proves that psi follows from phi. Once again, looking at our example, we see that there is an instance of implication introduction, which I've written here over on the left, in deriving line 6 from the subproof on lines 3 through 5. This exercise tests your grasp of structured proofs by asking you to prove a result using implication introduction. The discussion of structured proofs leads to the Fitch system. Fitch is a proof system that is particularly popular in the logic community. It's as powerful as other proof systems for propositional logic, and it's far simpler to use. Fitch has 10 rules of inference. In the version shown here, 9 of these are ordinary rules of inference. The other one, namely implication introduction is a structured rule of inference. Negation introduction allows us to prove that a sentence is false if it leads to a contradiction. If we believe phi implies psi, and we believe that phi implies not psi, then we can derive that phi is false. Negation elimination allows us to delete double negatives. And introduction and an elimination are straightforward. If a proof contains sentences phi 1 through phi n, then we can infer their conjunction. And if we have the conjunction of phi 1 through phi n, then we can infer any of the conjuncts. Or introduction allows us to infer an arbitrary disjunction as long as at least one of the disjuncts is already in the proof. Or elimination is a little more complicated than and elimination. Since we do not know which of the disjuncts is true, we cannot just drop the operator. However, if we know that every disjunct entails some sentence, then we can infer that that sentence is true, even if we do not know which of the disjuncts is true. Implication introduction is the Fitch embodiment of more complicated reasoning that we saw earlier. If by assuming phi we can infer psi, then we can infer the sentence phi implies psi. Implication elimination is the same here as the rule we saw earlier. Biconditional introduction allows us to infer an equivalence, a biconditional, from an implication and its inverse. And biconditional elimination goes the other way, allowing us to infer two implications from a single biconditional. This exercise tests your grasp of Fitch by asking you to use the sentences P implies Q and M implies P or Q to prove M implies Q. Talking about logic, we now have two notions: logical entailment and provability. A set of premises logically entails a conclusion if and only if every truth assignment that satisfies the premises also satisfies the conclusion. A sentence is provable from a set of premises if and only if there's a finite proof of the conclusion from the premises. The concepts are quite different in definition. One is based on truth assignments, the other is based on symbolic manipulation of expressions. Yet, for the proof systems we've been examining, they are effectively equivalent. Let's have some terminology. We say that a proof system is sound if and only if every provable conclusion is logically entailed. In other words, if we can prove a sentence from a set of premises, then the set of premises logically entails the conclusion. A proof system is complete if and only if every logical conclusion is provable. In other words, if a set of premises logically entails a conclusion, we can prove it. The Mendelssohn system is both sound and complete, at least for those problems in which the premises and conclusions are expressed using only the not and implication operators. In other words, for this system, logical entailment and provability are identical. The Fitch system is also sound and complete. Again, logical entailment and provability are identical. Moreover, in this case, this is true for the entire language of propositional logic. An arbitrary set of sentences delta logically entails an arbitrary sentence phi if and only if phi is provable from delta using Fitch. The upshot of this result is really significant. The truth table method and the proof method succeed in exactly the same cases. On large problems, the proof method often takes fewer steps than the truth table method. Moreover, proofs are usually much smaller than the corresponding truth tables, so writing an argument to convince others does not take as much space. As we shall see, the benefits of proofs are even greater for relational logic, where the truth assignments can be infinite, while proofs remain finite. Propositional resolution works only on expressions in clausal form. Before propositional resolution can be applied, our premises and conclusions must be converted to this form. Fortunately, as we shall see, there's a simple procedure for making this conversion. A literal is either an atomic sentence or a negation of an atomic sentence. For example, if P is a logical constant, the sentences shown here are all literals. A clausal sentence is either a literal or a disjunction of literals. And a clause is a finite set of literals, interpreted as a disjunction. The set can contain one element, two elements, or more elements. Note that the empty set is also a clause. It's equivalent to an empty disjunction, and therefore is unsatisfiable. Why is that? Well, remember that a clause is a disjunction. The more disjuncts we have in a clause, the easier it is to satisfy. The fewer disjuncts, the harder it is to satisfy. In the limit, when there are no disjuncts, we have an unsatisfiable clause. As we shall see, the empty clause is a particularly important special case in resolution. As mentioned earlier, there's a simple procedure for converting an arbitrary set of propositional logic sentences to an equivalent set of clauses. The conversion rules are summarized here. All of the rules within each group should be applied repeatedly until there are no changes before moving on to rules in the next group. The purpose of the transformations in the implications out group is to eliminate all implications and biconditionals. We rewrite phi1 implies phi2 as not phi1 or phi2. And we rewrite a biconditional as a conjunction of two transformed implications. The purpose of the transformations in the negations in group is to move negations through other operators until they are applied directly to proposition constants. We drop double negations. We push nots through ands by negating the conjuncts and changing to ors. And we push nots through ors by negating the disjuncts and changing to ands. The purpose of the distribution rules is to push or operators to the inside of and operators, and to normalize every disjunction of disjuncts to a single disjunction, and every conjunction of conjunctions to a single conjunction. The purpose of the final step, operators out, is to turn disjunctions into clauses and to turn conjunctions of clauses into separate clauses. As an example, consider the job of converting the sentence G and R implies F to clausal form. The conversion process is shown here. In the I step, we eliminate the implication operator. The N step, in this case, has no effect. Same for the D step. In the O step, we change each of the conjuncts to a clause. As a slightly more complicated example, consider the following conversion. We start with the same sentence, except that in this case it's negated. The I step in this case is the same as before. However, this time around we have a negation operator on the outside, and we need to push that in before we can continue. First, we distribute the negation over the conjunction. Then we distribute the negation over the disjunction in the second conjunct. And then we remove the double negative. In the D step, we distribute the OR operator over the AND. And finally, in the O step, we convert the two conjuncts to clauses. In this case, we end up with two clauses, each with two literals. Note that even though the sentences in these two examples are similar to start with, disagreeing on just that one negation operator, results are quite different. This exercise tests your ability to convert propositional logic sentences to clausal form. The idea of resolution is simple. Suppose we know that P is true or Q is true. Suppose we also know that Q is false or R is true. One clause contains Q and the other contains not Q. If Q is false, then by the first clause, P must be true. If Q is true, then by the second clause, R must be true. Since Q must be either true or false, then it must be the case that either P is true or R is true. In other words, we can cancel the Q literals. This intuition is the basis for the rule of inference shown here. Given a clause containing a literal chi, and another clause containing the literal not chi, we can infer the clause consisting all of the literals of both clauses without this complementary pair. This rule of inference is called the resolution principle, or alternatively, propositional resolution. The case we just discussed is an example. If we have the clause P or Q, and we also have the clause not Q or R, then we can derive the clause P or R in a single step. The rule is quite simple, but there are some issues to keep in mind and one common pitfall to avoid. First of all, there's this issue of collapse. Since clauses are sets, there cannot be two occurrences of any literal in a clause. Therefore, in drawing a conclusion from two clauses that share a literal, as in this case, we merge the two occurrences into one, here resulting in a singleton clause Q. Resolving two singleton clauses leads to the empty clause, that is, a clause containing no literals at all. The derivation of the empty clause means that the set of clauses contains a contradiction. If two clauses resolve, they can have more than one resolvent because there can be more than one way in which to choose the literals being canceled. The example shown here illustrates this possibility. We can resolve on P, producing one result, or we can resolve on Q, producing a different result. And here's the pitfall. In resolving two clauses, only where there's more than one possible resolution, only one pair of literals may be resolved at a time, even though there are multiple resolvable pairs. For example, the case shown here is not a legal application of propositional resolution. If we allow this to go through, we would be saying that these two clauses are inconsistent. However, it's perfectly possible for P or Q to be true and not P or Q to be true at the same time. For example, we just let P be true and Q be false, and we've satisfied both clauses. It's noteworthy that resolution subsumes many of our other rules of inference. Consider, for example, implication elimination, shown here on the left. If we have P implies Q, and we have P, then we can deduce Q. The clausal form of the premises and conclusion are shown here on the right. The implication P implies Q corresponds to the clause not P or Q, and P corresponds to the singleton clause P. We have two clauses with a complementary literal, and so we can cancel those complementary literals and derive the clause Q, which is, of course, the clausal form of the atomic sentence Q. As another example, recall the case of formal reasoning introduced in Chapter 1. We said that whenever we have two rules in which the left-hand side of one contains a proposition constant that occurs on the right-hand side of the other, then we can cancel those constants and deduce a new rule by combining the remaining constants on the left-hand sides of both rules and the remaining constants on the right-hand sides of both rules. So it turns out this is just propositional resolution. On the right, here, we have the clausal form of the sentences on the left. In place of the first sentence, we have the clause not P or Q. And in place of the second sentence, we have not M or not R or P or Q. Canceling the P literals, we can deduce not M or not R or Q, which is, of course, the clausal form of the sentence we derived on the left. This exercise tests your understanding of the resolution rule of inference. Reasoning with the resolution principle is analogous to reasoning with other rules of inference. We start with premises, we apply the resolution principle to those premises, and apply the rule to the results of those applications, and so forth, until we get to our desired conclusion. A resolution derivation of a conclusion from a set of premises is a finite sequence of clauses terminating in the conclusion in which each clause is either a premise or the result of applying the resolution principle to earlier elements of the sequence. Note that our definition of resolution derivation here is analogous to our definition of linear proof. However, in this case, we do not use the word proof. because we're reserving that word for a slightly different concept, which we will see shortly. In many cases, it's possible to find resolution derivations of conclusions from premises. Suppose, for example, we are given the clauses not P or R, and not Q or R, and P or Q. Then we can derive the conclusion R as shown here. After writing down our premises, we resolve the clause on line 1 with the clause on line 3 to produce the clause on line 4. Then we resolve this clause with the clause on line 2 to derive the result on line 5. It's noteworthy that the resolution principle is not generatively complete. That is, it's not possible to find resolution derivations for all clauses that are logically entailed by a set of premise clauses. For example, given the clause P and the clause Q, there's no resolution derivation of the clause P or Q, despite the fact that it's logically entailed by the premises in this case. As another example, consider that valid clauses, such as P or not P, are always true, and so they are logically entailed by any set of premises, including the empty set of premises. However, propositional resolution requires some premises to have any effect. Given an empty set of premises, we would not be able to derive any conclusions, including these valid clauses. On the other hand, we can be sure of one thing. If a set delta of clauses is unsatisfiable, then there's guaranteed to be a resolution derivation of the empty clause from delta. And more generally, if a set delta of propositional logic sentences is unsatisfiable, then there's guaranteed to be a resolution derivation of the empty clause from the clausal form of delta. As an example, consider the clauses P or Q, P or not Q, not P or Q, and not P or not Q. There's no truth assignment that satisfies all 4 of these clauses. Consequently, starting with these clauses, we should be able to derive the empty clause. And we can. The resolution derivation is shown here. We resolve the clauses on lines 1 and 2 to produce P, and we resolve the clauses on lines 3 and 4 to produce not P. We then resolve these two results with each other to derive the empty clause. The good news is that we can use this fact to produce a method for determining logical entailment as well. Recall that the satisfiability theorem, or maybe it was called the unsatisfiability theorem, introduced earlier in the course, tells us that a set delta of sentences logically entails a sentence phi if and only if the set delta union not phi is inconsistent. So, to determine logical entailment, all we need to do is to negate our goal, add it to our premises, and use resolution to determine whether the resulting set is unsatisfiable. Let's capture this idea with some definitions. A resolution proof of a sentence phi from a set delta of sentences is a resolution derivation of the empty clause from the clausal form of delta union not phi. And a sentence phi is provable from a set of sentences delta by propositional resolution, if and only if there's a resolution proof of phi from delta. As an example of a resolution proof, consider one of the problems we saw in Chapter 3. We have the 3 premises shown here. We believe P, we believe P implies Q, and we believe that P implies Q implies Q implies R. Our goal is to prove that R is true. To this end, we negate our goal and add it to our premises, as shown here on the left, and we convert to clausal form, leading to the clauses shown here on the right. Note that the 3rd premise here leads to 2 clauses, not just 1. And a resolution proof is shown here, resolving the first clause with the second. We get the clause Q, shown on line 6. Resolving this with the 4th clause gives us R, shown on line 7. And resolving this with the clause on line 5 gives us the empty clause, thus proving our result. Here's another example, this time illustrating the way in which we can use resolution to prove valid sentences. Let's say that we have no premises at all, and we want to prove P implies Q implies P. which is an instance of the implication creation axiom schema we saw earlier. The first step is to negate this sentence and convert to clausal form. Here's a trace of the conversion process. We first eliminate the implication operators. We push the negations to the inside over several steps. We distribute. And finally, we convert the clauses, two clauses, ending up with three different clauses, P, Q, and not P. Finally, we take those clauses and produce a resolution derivation of the empty clause. In this case, it takes just one step. This exercise tests your understanding of the resolution method. In this segment, we're going to take a look at box logic. Unfortunately, we cannot do that here in the studio, so we're going to have to take a road trip. Today we're headed for Stanford University's renowned Logic Laboratory. Follow me. And here we are. This is the Logic Laboratory. It may not look like much, at least not superficially, but this is where we investigate some of the latest innovations in logic technology. Today our goal is to look at box logic. Now the language of box logic is pretty simple. There are really just three constants. There's large box, there's medium box, and there's small box. And they're all oriented one way or the other. Forming compound sentences from our constants is easy. If we want to negate a sentence, we just invert it. Not medium box, medium box. If we want to form a disjunction from our constants, we stack them up. So here we have small box or medium box. And a conjunction is formed simply by placing multiple boxes or stacks of boxes on our table. So it's effectively clausal form. Okay, now let's try to use our logic to solve some problems. How about the case of Mary, Pat, and Quincy? You recall that if it's Monday, Mary loves Pat or Quincy, and Quincy, if Mary loves Pat, Mary loves Quincy. Let's see how we can represent that information using our new language. So first of all, if Mary loves Pat, Mary loves Quincy. Let's let this medium-sized box represent the fact that Mary loves Pat. This one represents Mary loves Quincy, and the large one is going to be Monday. So we want to say, if Mary loves Pat, Mary loves Quincy. How do we do that? Recalling the rules for converting to clausal form, we know that P implies Q is equivalent to not P or Q. So if you wanted to write that, we would write not Mary loves Pat or Mary loves Quincy. So not Mary loves Pat or Mary loves Quincy. If Mary loves Pat, Mary loves Quincy. How about our other sentence? If it's Monday, then Mary loves Pat or Quincy. It's Monday. Let's see, we need to say not Monday or Pat or Quincy. So not Monday. More copies. Or Pat or Quincy. So there we have it. If it's Monday, Mary loves Pat or Quincy. If Mary loves Pat, Mary loves Quincy. Representing the premises of the problem. Now you may recall that the object of the problem was to show that if it's Monday, then Mary loves Quincy. So how could we do that? All we've done is represent things, but we can also do computation, deduction, with box logic. The rules are pretty simple. If we ever have one stack which has a constant, a literal, which is the complement of a literal in another stack, we can do resolution on them. So here we have one stack with medium box down, here one stack with medium box up. We can combine the two stacks, eliminate the complementary literals, and form this answer. Since this is a duplicate, we can throw that one away. And we're left with our conclusion. If it's Monday, Mary loves Quincy. Nifty. Okay, well, what's the point? The point is that the language of logic is not about particular sets of symbols. And the act of deduction doesn't mean necessarily that we're operating upon those particular symbols. Logic is an abstraction. Any instantiation of the symbols is equally good, and any operations on them is equally good, provided that it respects that basic abstraction. Okay, that's it for our visit to the Logic Laboratory today. We'll be back again later in the course with some additional demonstrations, and we'll see you then.
Propositional satisfiability, or SAT, is the problem of determining whether a set of propositional sentences is satisfiable. Many logic problems can be recast as SAT problems. For example, earlier in the course we saw that the logical entailment problem in propositional logic can be reduced or recast as a satisfiability problem in propositional logic. People have developed special purpose programs to solve these SAT problems. They're called SAT solvers. These SAT solvers are used in hardware design, software analysis, planning, mathematics, and many other areas. In this section, we will give a brief overview of SAT solving. Methods in SAT solving can be broadly categorized into two categories. They're the complete methods that are guaranteed to give you the correct answer. And then there are incomplete methods. These methods will give you the correct answer when they can, but may also fail to give you an answer. Let's look at a concrete example. Here we have the set of sentences phi, and the question is to determine whether phi is satisfiable. That is, does there exist a truth assignment that satisfies every sentence in phi? Now, in this whole section, we will assume that each sentence is written as a disjunction of atoms or negated atoms. We know that this is okay because every sentence in propositional logic can be rewritten as an equivalent sentence in this form. First, let's look at a truth table method. We should all be familiar with this method from all the way back in week 2 of the course. On the left-hand side, we have the first 3 columns giving us all the different truth assignments on P, Q, and R. Then we look at which of the sentences in phi evaluate to true and which to false. So if we look at the first row here, in the truth assignment assigning false to P, Q, and R, we see that P or Q is false, P or not Q is true, not P or Q is true, not P or not Q or not R is true, and finally, not P or R is false. And because some of the sentences in phi evaluate to false, we know that phi as a whole is not satisfied by this truth assignment. If we examine all the rows, we find that in every row there is at least one sentence in phi that evaluates to false. So we conclude that phi is not satisfied by any truth assignment. That is, it's unsatisfiable. The truth table method is complete because we examine every single truth assignment. It is also impractical, except for very small examples. In the example we just looked at, we had 3 propositions. And we need to examine 2 to the 3rd power, or 8, in number of truth assignments. That's very small. We did it by hand. If you had 10 propositions, you need to examine 1,000 truth assignments. That's still very small for a computer. But because the number of truth assignments grows exponentially in terms of the number of propositions, this quickly gets out of control. By the time you get to 40 propositions, there are about 1 trillion truth assignments to examine. So we need a better methods for larger problems. Observe here that sometimes we don't need to look at a complete truth assignment before we determine that phi is not satisfied. For example, if we look at an incomplete assignment here with P being true, Q being false, and R unknown, we can already tell that the sentence not P or Q is false, and that phi is not satisfied. So because we already know this from a partial assignment on P or Q, we don't actually need to go through the work of examining the two complete assignments to determine that in each complete assignment, phi is not satisfied. So let's consider searching partial assignments instead of only complete assignments. One way to do that is to use a tree like the one on the screen. We start at the top, at the empty assignment, where nothing is known. Then we make choices. For example, if we choose P to be false, we arrive at another partial assignment. And as we continue to make choices, we arrive at the bottom of the tree with the complete assignments. Now, at each partial assignment, we can evaluate whether the set of sentences phi is already falsified. For example, if at this partial assignment we find that phi is already falsified, we don't need to search all the assignments in the subtree below it, because we know that all those assignments would also falsify phi. In this particular case, we only save ourselves from searching 2 more assignments. But in general, when you have a greater number of propositions, this can be a huge subtree that we're pruning away from our search space. This idea gives rise to the basic backtracking search. I'll walk through a concrete example. We have in the blue box the set of sentences phi, and we start searching. First, we choose P to be false, and in this partial assignment, we cannot determine whether phi is satisfied. Next, we continue to make choices, choosing Q to be false. And under this partial assignment, we can already tell that one of the sentences in phi is falsified. So we label this node with an X, and we don't have to search any further under this branch. We backtrack to the most recent decision point and choose a different path. Let's say we choose Q to be true. Now, under this partial assignment, we find that another sentence in phi is falsified. So again, we don't need to search any further down this branch. Again, we backtrack to the most recent decision point where we could have made a different choice. We go all the way back to the empty assignment, and this time we choose P to be true. So far, we cannot determine whether phi is satisfied. So we continue making choices. Choosing Q to be false, we arrive at a partial assignment where we see that phi is falsified because one of the sentences is falsified. Backtracking again, we make a different choice of Q being true. Here, we cannot determine whether phi is satisfied, so we continue making choices. Searching the branch of R being false, we get to a truth assignment where phi is falsified. Backtracking again and making a different choice, we see again that phi is falsified. Now that we have closed off every branch of the search tree with an assignment that falsifies phi, we can conclude that there does not exist any truth assignment that satisfies phi. Again, we reach the same conclusion that phi is unsatisfiable. Comparing the tree we just explored to the full search tree, we see that we've been able to eliminate or prune away the need to search all these subtrees. And again, in this particular example, it's not a huge saving. But in a larger example, where we have more propositional variables, these could be huge subtrees we're pruning away. Let's look at a further optimization that can save us work. For example, when we're given a partial assignment, say P being true, Q and R unknown, we can simplify the set of formulas we're dealing with. A formula that's already satisfied, say P or Q, can be simply tossed away and ignored. A formula that contains a disjunct contradicted by the partial truth assignment can be eliminated, arriving at a simpler formula. Let's look at an example. We have the same set of formulas phi, and let's say we're exploring this node right here, partial assignment with P being true and others unknown. We can already simplify the set of formulas. The first two sentences can be ignored because we see that they're already satisfied. In the next three sentences, we can eliminate the disjunct saying P is false because it's contradicted by the current truth assignment. And we end up with a much simpler set of formulas we're dealing with right here. Being able to simplify the set of formulas is very nice, but it gives us something even more. Notice here that we end up with the formula Q without any other disjuncts. We call this a unit. And we know that the only way to satisfy the unit is to set Q to true. So from this partial assignment right here, we know to explore the branch Q being true while ignoring this whole other subtree involving Q being false. This can give us a major savings. Let's look at the same example we went through earlier, but this time with unit propagation and simplification. We start as before, choosing P to be false. And in blue box, we simplify using this partial assignment. We end up with the simplified set of sentences. We find that we have some units. Choosing one arbitrarily, we search accordingly. In this case, setting Q to be false. We simplify again, and we find that the set of sentences is falsified. Now we backtrack. Previously, we backtracked to this decision point right here, but because we use unit propagation right there, we don't have another decision to make. So we backtrack to the previous decision point where we still had a choice to make, all the way at the top in this case. So choosing P to be true, we simplify again. We find a couple units, and choosing one arbitrarily, we apply unit propagation, fix Q to be true, get to a new partial assignment, and we simplify again. We obtain some more units, and again choosing one to apply unit propagation. We fix R to be false. We determine that the set of sentences is falsified by this assignment. And now we've closed off every branch in the tree, determining again that phi is unsatisfiable. Compared with the search tree we went through using the basic backtracking search, simplification and unit propagation eliminated the need to explore all these subtrees that are grayed out in this picture. If we do the basic backtracking search with the unit propagation optimization we discussed and another optimization called pure literal elimination, we end up with what's essentially the classic DPLL method. And this is a very important method because most modern complete SAT solvers are based on some variation of DPLL with many more optimizations than we've discussed. And these SAT solvers are capable of solving large SAT problems. Some SAT problems are still impractical for complete SAT solvers. For example, some instances offer very little opportunity for early pruning. In these cases, one must consider methods that are incomplete. For example, an incomplete search. The basic idea here is to sample a subset of the truth assignments rather than exhausting them. And if in the sample you find a satisfying truth assignment, then you know that the set of sentences is satisfiable. But if you don't find a satisfiable truth assignment, the best you can conclude is that I don't know whether the set of sentences is satisfiable. There might be one satisfying assignment out there, but I haven't found it. We will not look at the details here, but I do encourage you to take a look at the incomplete search methods. Some takeaways. Decades of intense research and engineering has gone into crafting SAT solvers. And as a result, we now have modern SAT solvers that are capable of solving fairly large problems very efficiently. And active research continues in this area. Today, SAT solvers are used to solve many practical problems, and it is definitely a tool to consider when you need to automate problem solving.
Propositional logic does a good job of allowing us to talk about relationships among individual propositions. And it gives us the machinery to derive logical conclusions based on these relationships. Suppose, for example, we believe that if Jack knows Jill, then Jill knows Jack. And suppose we also believe that Jack knows Jill. From these two facts, we can conclude that Jill knows Jack using a simple application of implication elimination. Unfortunately, when we want to say things more generally, we find that propositional logic is inadequate. Suppose, for example, we wanted to say that in general now, if one person knows a second person, then the second person knows the first. And suppose as before that we believe that Jack knows Jill. How do we express our general fact in a way that allows us to conclude that Jill knows Jack? Here, propositional logic is inadequate. It gives us no easy way of encoding this more general belief in a form that captures its full meaning and allows us to derive such conclusions. Herbrand logic is an extension of propositional logic that solves this problem. The trick is to augment our language with two new linguistic features, namely variables and quantifiers. And with these new features, we can express information about multiple objects without explicitly enumerating those objects. And we can express the existence of objects that satisfy specified conditions without saying which objects they are. Incidentally, the logic is named after the logician Jacques Herbrand, who developed some of the key concepts. As Herbrand is French, it should properly be pronounced Herbrand. However, most people resort to the anglicized version, Herbrand. One exception to that is my colleague Stanley Peters, who was a little skeptical on first hearing about it and, for better or worse, chose to pronounce it harebrained. Okay, with all due respect to both of these luminaries, we will use the anglicized pronunciation from here on out, Herbrand. In this lesson, we proceed through the same stages as in our treatment of propositional logic. We start with syntax and semantics of the language. We then present a series of examples of increasing complexity that illustrate various features of that language. We then discuss the properties of Herbrand logic, the sentences individually, and we define logical entailment. Finally, we discuss the decidability of various questions in three subsets of Herbrand logic. We begin our discussion of syntax with a look at the basic words of our language. We then talk about how these words can be combined to form complex expressions called terms. And finally, we talk about how terms can be combined to form sentences. In propositional logic, sentences are constructed from a basic vocabulary of propositional constants. In Herbrand logic, there are no propositional constants. Instead, we have object variables and constants. In our examples here, we write both variables and constants as strings of letters, digits, and a few alphanumeric characters, mostly the underscore character. By convention, variables begin with letters from the end of the alphabet. Examples include U, V, W, X, Y, Z. By convention, all constants begin with other letters other than U, V, W, X, Y, Z, or digits. Examples include A, B, C, 1, 2, 3, Comp 225, Barack underscore Obama, and so forth. There are three types of constants in Herbrand logic: object constants, function constants, and relation constants. Object constants represent objects. For example, Joe, Stanford, USA, 2,345. Function constants represent functions on objects. For example, mother, father, the age of a person, plus, times, and so forth. Relation constants represent relations on objects. For example, knows and loves. Now, there's no distinction in spelling between object constants, function constants, and relation constants. The type of each such word is determined by its usage, or in some cases, in an explicit specification. As we shall see, function constants and relation constants are used in forming complex expressions by combining them with an appropriate number of arguments. Accordingly, each function constant and relation constant has an associated arity, that is, the number of arguments with which the function constant and relation constant can be combined. Function constant relation constant that can be combined with a single argument is said to be unary. One that can be combined with two arguments is said to be binary. One that can be combined with three arguments is said to be ternary. More generally, a function or relation constant that can be combined with n arguments is said to be n-ary. A signature consists of a non-empty set of object constants, a possibly empty set of function constants, and a non-empty set of relation constants, and an assignment of arities for each of the function constants and relation constants. For example, we might have a signature consisting of the object constants a and b, the unary function constant f, the binary function constant g, the unary relation constant p, and the binary relation constant q. A term is defined to be a variable, an object constant, or a functional term, as we'll define in a minute. Terms typically represent objects that are presumed or hypothesized to exist in the world, and as such they are analogous to noun phrases in natural language. For example, Joe, or the car's left front wheel. A functional term is an expression formed from an n-ary function constant and n terms, enclosed in parentheses and separated by commas. For example, if G is a binary relation constant, and if A and Y are terms, then G of AY is a functional term, as are G of AA and G of YY. Note the functional terms can be nested inside of other functional terms. For example, we can apply the function constant G to the functional term G of AY and the functional term G of YA to form a more complex functional term. There are three types of sentences in Herbrand logic. There are relational sentences, which are analogous to propositions in propositional logic. There are logical sentences, which are analogous to the logical sentences of propositional logic. And there are quantified sentences, which express the significance of variables. A relational sentence is an expression formed from an n-ary relation constant and n terms. For example, if Q is a relation constant with arity 2, and if A and Y are terms, then the expression shown here is a syntactically legal relational sentence. Note that, unlike functional terms, relational sentences may not be nested within other relational sentences. So it would be inappropriate to say Q of A and Q of AY. Logical sentences in Herbrand logic are defined the same as logical sentences in propositional logic. There are negations, conjunctions, disjunctions, implications, and equivalences or biconditionals. The syntax is exactly the same, except that the elementary components are relational sentences and equations and so forth, rather than proposition constants. There are two types of quantified sentences: universally quantified sentences and existentially quantified sentences. The universally quantified sentence is used to assert that all objects have a certain property. For example, the expression shown here is a universally quantified sentence asserting that if P holds of an object, then Q holds of that object and itself. The universal quantifier is notated by this upside down A. An existentially quantified sentence is used to assert that there are objects having a certain property. For example, the middle expression here is an existentially quantified sentence asserting that there's an object that satisfies P and, when paired with itself, satisfies Q as well. The existential quantifier is denoted by an E rotated through 180 degrees, as shown here. Note that quantified sentences can be nested within other sentences. For example, in the first sentence here in the bottom, we have a quantified sentence inside of a disjunction. And in the second sentence at the bottom, we have a quantified sentence nested inside of another quantified sentence. As with propositional logic, we can drop unneeded parentheses in Herbrand logic, relying on precedence to disambiguate the structure of unparenthesized sentences. In Herbrand logic, the precedence relations of the logical operators are the same as in propositional logic, and quantifiers have higher precedence than logical operators. The examples here show how to parenthesize sentences with both quantifiers and logical operators. Sentences on the right are partially parenthesized versions of the sentences on the left. To be fully parenthesized, we would need to add parentheses around each of the sentences as a whole as well. Notice that in each case, the quantifier applies only to the sentence to its right, even though the other sentence also contains occurrences of the quantified variable. Okay, this exercise tests your grasp of these rules of syntax by asking you to determine whether various expressions are syntactically legal sentences in Herbrand logic. Before we leave our look at syntax, we need to define some additional useful concepts. An expression in the language of Herbrand logic is said to be ground if and only if it contains no variables. For example, the sentence P of A is ground, whereas the sentence for all x P of x is not ground because it contains a variable. An occurrence of a variable in a sentence is bound if and only if it appears in the scope of a quantifier of that variable. Otherwise, it's said to be free. For example, x is free and y is bound in the sentence shown here. And finally, we say a sentence is open if and only if it has free variables. Otherwise, it's closed. For example, the first sentence here is open, and the second one is closed. The Herbrand base for Herbrand language is the set of all ground atomic sentences that can be formed from the vocabulary of the language. Let's look at some examples. For a schema with object constants a and b, no function constants, and relation constants p and q, where p has arity 1 and q has arity 2. The Herbrand base is shown here. We have one p sentence for each object constant, and we have one q sentence for each of the 4 possible pairs of object constants. It's worthwhile to note that for a given relation constant and a finite set of terms, there's an upper bound on the number of possible ground relational sentences that can be formed using that relation constant. In particular, for a domain of size b, There are b to the n distinct n tuples of object constants, and hence there are b to the n ground relational sentences for each n-ary relation constant. Since the number of relation constants in a signature is finite, this means that the Herbrand base is also finite. Of course, not all Herbrand bases are finite. In the presence of function constants, the number of ground terms is infinite, and so the Herbrand base is infinite. For example, in a language with a single object constant and a single unary function constant f and a single unary relation constant p, the Herbrand base consists of the sentences p of a, p of f of a, p of f of a, and so forth. The truth assignment for Herbrand logic language is a function that maps each ground relational sentence in the Herbrand base to a truth value. As in propositional logic, we use the digit 1 as a synonym for true and 0 as a synonym for false. And we refer to the value assigned to a ground atom by writing the atom within the name of the truth assignment as a superscript. The truth assignment I defined here is an example for the case of the language we just saw. This exercise tests your understanding of these concepts by asking you to answer some simple counting questions. As with propositional logic, once we have a truth assignment for the ground relational sentences of a language, the semantics of our language prescribes a unique extension of that assignment to the other sentences of the language. The rules for logical sentences in Herbrand logic are the same as those for logical sentences in propositional logic. A truth assignment satisfies a negation if and only it does not satisfy the target of the negation. The truth value of a conjunction is true under a truth assignment if and only if the truth value of its conjuncts are both true. Otherwise, the truth value is false. The truth value of a disjunction is true if and only if the truth value of at least one of its disjuncts is true, and otherwise the truth value is false. A truth assignment satisfies an implication if and only if it does not satisfy the antecedent or it does satisfy the consequent. And a truth assignment satisfies a biconditional if and only if the truth values of the component sentences are the same. In order to define the truth assignments in quantified sentences, we need the notion of instances. An instance of an expression is an expression in which all variables have been consistently replaced by ground terms. Consistent replacement here means that if one occurrence of a variable is replaced by a ground term, then all occurrences of that variable are replaced by the same ground term. A universally quantified sentence is true for a truth assignment if and only if every instance of the scope of the quantified sentence is true for that assignment. An existentially quantified sentence is true for a truth assignment if and only if some instance of the scope of the quantified sentence is true for that assignment. As an example of these definitions, consider the sentence, for all x, p of x implies q of x, x. What's the truth value under the truth assignment shown here? According to our definition, a universally quantified sentence is true if and only if every instance of its scope is true. For this language, there are just two instances shown here at the bottom. We know that P of A is true, and we know that Q of AA is true. So the first instance is true. Q of BB is false, but then again, so is P of B. So the second instance is true as well. Since both instances are true, the quantified sentence is also true. Now let's consider a case with nested quantifiers. Is for all x there exists a y, q of xy true or false for the truth assignment shown here? As before, we know that this sentence is true if every instance of its scope is true. The two possible instances are shown here. To determine the truth of the first of these existential sentences, we must find at least one instance of its scope that's true. The possibilities are shown here on the left. Of these, the first is true, and so the first existential sentence is true. Now we do the same for the second existentially quantified sentence. The possible instances are shown here on the right. Of these, again, the first is true, and so the second existential sentence is true. Since both existential sentences are true, the original quantified sentence must be true as well. A truth assignment satisfies a sentence with free variables if and only if it satisfies every instance of that sentence. In other words, we can think of all free variables as being universally quantified. And finally, a truth assignment satisfies a set of sentences if and only if it satisfies every sentence in the set. This exercise tests your grasp of semantics by asking you to evaluate some Herbrand logic sentences. Let's look at an example to make all of these concepts concrete. Consider once again the sorority world example introduced in the first lesson. Recall that this world focuses on the interpersonal relations of a small sorority. There are just 4 members, Abby, Bess, Cody, and Dana. Our goal is to represent information about who likes whom. The table here shows one possible configuration. Abby likes Cody, Bess likes Cody, and so forth. In order to encode this information in Herbrand logic, we adopt a signature with 4 object constants, Abby, Bess, Cody, and Dana, and one binary relation, likes. The Herbrand base in this case contains 16 ground relational sentences, one for each pair of object constants. Given complete information about the likes and dislikes of the girls, we could completely characterize the state of affairs as a set of ground relational sentences, or negations of ground relational sentences, like the ones shown here. One sentence for each member of the Herbrand base. To make things more interesting, let's assume that we don't have complete information like this, but only fragments of information about likes and dislikes. And let's see if we can encode such fragments in the language of Herbrand logic. Let's start with a simple case. Abby likes everyone Bess likes. Paraphrasing the sentence helps in the translation. If Bess likes a girl, then Abby also likes her. Since this is a fact about everyone, we use a universal quantifier. For all y, if Bess likes y, then Abby likes y. Next case. Cody likes everyone who likes her. In other words, if some girl likes Cody, then Cody likes that girl. Again, we use a universal quantifier. For all x, if x likes Cody, then Cody likes x. Cody likes somebody who likes her. The word somebody here is a tip-off that we need an existential quantifier. There is some y such that Cody likes y and y likes Cody. Nobody likes herself. The use of the word nobody here suggests the negation. Good technique in such cases is to rewrite the English sentence as the negation of a positive version of the sentence before translating to Herbrand logic. There does not exist an x such that x likes x. Everybody likes somebody. Here we have a case requiring 2 quantifiers, one universal and one existential. And the key to this case is getting the quantifiers in the right order. For all x, there's a y such that x likes y. And there's someone everyone likes. The preceding sentence tells us that everyone likes someone, but that someone can be different for different people. This sentence tells us that everybody likes the same person. To understand the difference between these 2 sentences, let's diagram the situation. We have 4 girls, Abby, Bess, Cody, and Dana. First sentence tells us that everybody likes somebody. For example, it could be the case that Abby likes Bess, Bess likes Abby, Cody likes Dana, and Dana likes Cody. Everybody likes somebody. This is little too idealistic. Let's be a little more realistic. We have Abby, Bess, Cody, and Dana. Abby likes Bess. Bess likes Cody. Cody likes Dana. Dana likes herself. Well, let's say something like this at any rate. But every person has somebody they like. But that can be different depending on who the liker is. Now, by contrast, the second sentence says there is some one person whom everybody likes. Again, with the four girls, all like, but in this case, all like the same person. Let's say Dana. Abby likes Dana, Bess likes Dana, Cody likes Dana, and of course we have the narcissistic Dana. This exercise tests your understanding of these concepts by asking you to select truth values for Herbrand logic sentences in a given state of the sorority world. The blocks world is a popular application area for illustrating ideas in the field of artificial intelligence. Typical blocks world scene is shown here. Now, most people looking at this figure interpret it as a configuration of 5 toy blocks. Some people conceptualize the table in which the blocks are resting as an object as well, but for simplicity, we're going to ignore it. In order to describe this scene, we adopt a signature with 5 object constants. A, B, C, D, and E, with 1 object constant for each of the 5 blocks in the scene. The intent here is for each of these object constants to represent the block marked with the corresponding capital letter in the scene. In a spatial conceptualization of the blocks world, there are numerous meaningful relations. For example, it makes sense to talk about the relationship that holds between 2 blocks if and only if one is resting on the other. In what follows, we're going to use the relation constant on to refer to this relation. We might also think about the relation that holds between 2 blocks if and only if one is anywhere above the other. In other words, the first is resting on the second, or is resting on a block that is resting on the second, and so forth. And in what follows, we'll use the relation constant above to talk about this relation. Then there's the relation that holds of 3 blocks that are stacked one on top of the other. We use the relation constant stack as a name for this relation. And we use the relation constant clear to note the relation that holds of a block if and only if there is no block on top of it. And we use the relation constant table to denote the relation holds of a block if and only if that block is resting directly on the table. All right, now given this signature, we can describe our blocks world configuration by writing ground literals that state which relations hold of which objects or groups of objects. Let's start with on. The sentences here tell us directly for each ground relational sentence involving the on relation whether it is true or false. So in this case, A is on B, B is on C, D is on E, and the rest are all false. We can do the same for the other relations. However, there's an easier way. Each of the remaining relations can be defined in terms of on. These definitions, together with our facts about the on relation, then logically entail every other ground relational sentence, or its negation. Hence, given these definitions, we do not need to write out all of these additional ground relational sentences. So, for example, we can define the concept of clear as shown here. A block satisfies the clear relation if and only if there is nothing on it. For all y, clear of y is true if and only if there does not exist an x, such that on xy. And a block satisfies the table relation if and only if it is not on some other block. For all x, x a table of x if and only if there does not exist a y, such that on xy. 3 blocks satisfy the stack relation if and only if the first is on the second and the second is on the third. The above relation is a bit tricky to define correctly. One block's above another block if and only if the first is on the second, or it is on another block and that block is above the second. Also, no block can be above itself. Given a complete definition for the on relation, these 2 sentences determine a unique above relation. The main lesson to be taken from this example is the way that logical sentences can be used to define new relations in terms of existing relations, and thereby save us the effort of writing out all the ground atomic sentences that we would have to write out otherwise. This exercise tests your understanding of these concepts by asking you to say what happens when we drop the second sentence in the definition of above. In this example, we show how to characterize modular arithmetic in the language of Herbrand Logic. In modular arithmetic, there are only finitely many objects. For example, in modular arithmetic with modulus 4, we would have just 4 integers, 0, 1, 2, and 3, and that's all. Our goal here is to define the addition relation. Now, admittedly, this is a modest goal, but once we see how to do this, we can use the same approach for defining other arithmetic relations as well. In order to describe modular arithmetic in Herbrand Logic, we adopt a signature with 4 object constants, 0, 1, 2, and 3. We use the binary relation constant next to relate each number to the next larger number. And we use the ternary plus relation constant to relate 2 numbers to their sum. I'll suggest it here. Representing addition using a relation constant rather than a function constant, admittedly, is a bit unconventional. However, it avoids some problems that we will discuss and solve in a later lesson. Let's start our formalization with the same relation. Here we've written out all ground sentences involving same. One positive sentence for each number and itself, and negative sentences for all other combinations. We can define next in a similar fashion. Next of 0, 1, next of 1, 2, next of 2, 3, next of 3, 0. Note that in modular arithmetic, we wrap back to 0 after we get to 3. And all the other ground atoms are false. Here we've written, here's another alternative to doing next. In this case, we've written out just the positive relational sentences involving this relation, one for each number and its successor. We can dispense with the negative cases, in fact, by writing just a single logical sentence. The functionality axiom shown here asserts that next is a functional relation. That is, for each number, there is just one successor. In order to see why this saves us the work of writing out the negative literals, we can write this axiom in the equivalent form shown here at the bottom. If next is true of x and an object y, then it's false of x and every other object z. Having defined same and next, we turn our attention now to plus. The addition table for modular arithmetic is the usual addition table for arbitrary integers, except that, as I mentioned before, we wrap around whenever we get past 3. For such a small arithmetic, it's really easy to write out the ground relational sentences for addition in this, as we see here. However, as with next, we can write a functionality axiom to take care of the negative sentences. Plus of xyz and plus of xyw implies that z is the same as w. That's one way to do things, but we can do, in fact, even better than that. Rather than writing out all of those ground relational sentences, we can use the language of Herbrand Logic to define plus in terms of next and use that definition to deduce those other sentences. The definition is shown here. First, we have an identity axiom. Adding 0 to any number results in the same number. Next, we have a successor axiom. If z is the sum of x and y, then the sum of the successor of x and y is the successor of z. And finally, we have our functional axiom, as before. One advantage of doing things this way is economy. With these sentences, we do not need the ground relational sentences about plus. They're all logically entailed by our sentences about next and these definitional sentences. A second advantage is versatility. Our sentences define plus in terms of next for arithmetic with any modulus, not just the modulus 4. The main lesson to be learned from this example is the use of equality, same in this case, in defining functionality and the importance of functionality in formalizing information in applications like arithmetic. Now let's look at the problem of encoding arithmetic for all of the natural numbers. Since there are infinitely many natural numbers, we need infinitely many terms. One way to get infinitely many terms is to have a signature with infinitely many object constants. These constants are the only ground terms in our language. There's nothing wrong with this in principle. However, it makes the job of axiomatizing arithmetic effectively impossible, as we would have to write out infinitely many literals to capture our successor relation. An alternative approach is to represent numbers using a single object constant, let's say 0, and a single unary function constant, let's say s for successor. We can then represent every number n by applying the function constant s to 0 n times. In this encoding, for example, s of 0 represents 1, s of 0 represents 2, and so forth. With this encoding, we automatically get an infinite universe of terms, and we can axiomatize arithmetic with only finitely many sentences. From what follows, we're going to use this second approach. Here's our signature. As we said, we have a single object constant 0 and a successor function s. We have one binary relation constant, same, which holds two terms if and only if they're identical. And we have two ternary relation constants, one for plus and one for times. Unfortunately, axiomatizing Peano arithmetic is a bit more challenging than axiomatizing modular arithmetic. We cannot just write out the ground relational sentences to characterize our relations, because there are infinitely many cases to consider. For Peano arithmetic, we must rely on logical sentences and quantified sentences, not just because they're more economical, but because they're the only way we can characterize our relations in finite space. Let's look at the same relation first. The axioms here define the same relation in terms of 0 and the successor function. For all x, same of x, x. For all x, 0 is not the same as s of x, and s of x is not the same as 0. And for all x and for all y, if x is not the same as y, then s of x is not the same as s of y. It's easy to see that these axioms completely characterize the same relation. By the first axiom, the same relation holds of every term and itself. The other axioms tell us what's not true. The second axiom tells us that 0 is not the same as any composite term. It's also true of with the arguments reversed. And the third axiom builds on these results to show that non-identical composite terms of arbitrary complexity do not satisfy the same relation. Viewed the other way around, to see that two non-identical terms are not the same, we just strip away occurrence of s from each term until one of the two terms becomes 0 and the other one is not 0. And then by the second axiom, these are not the same, and so the original terms are not the same. Okay, now once we have the same relation, we can define the other relations in our arithmetic. The axioms here define the plus relation in terms of s, 0, and same. Adding 0 to any number results in that number. If adding a number x to a number y produces a number z, then adding the successor of x to y produces a successor of z. And finally, using same, we can write a functionality axiom for plus. The axiomatization of multiplication is analogous. Multiplying by 0 produces 0. If a number z is the product of x and y, and w is the sum of y and z, then w is the product of the successor of x and y. And once again, we have a functionality axiom. And that's all we need, just 3 axioms for same and 3 axioms for each of our arithmetic relations. Before we leave our discussion of Peano arithmetic, it's worthwhile to look at the concept of Diophantine equations. A polynomial equation is an algebraic expression composed using only addition, multiplication, and exponentiation with fixed exponents. That is numbers, not variables. For example, 3x squared plus 2y plus 2z cubed is a polynomial. A natural Diophantine equation is a polynomial equation in which the variables are restricted to the natural numbers. For example, the polynomial equation here is also a Diophantine equation and happens to have a solution to the natural numbers, namely x equals 2, y equals 2, and z equals 2. Diophantine equations can be readily expressed as sentences in Peano Arithmetic. For example, we can represent the Diophantine equation 3x squared equals 1 with the sentence for all x, y, and z. If x times y, x is y, and 3 times y is z, then z is the same as 1. Okay, now I grant this is a little messy, but it's doable. And we can always clean things up by adding a little syntactic sugar to our language to make it look like traditional math notation. For example, the expression shown here at the bottom. Once this mapping is done, we can use the tools of logic to work with these sentences. In some cases, we can find solutions, and in some cases, we can prove that solutions do not exist. This has practical value in some situations, and also has significant theoretical value in establishing important properties of Herbrand logic, a topic we'll discuss in a later segment. A list is a finite sequence of objects. Lists can be flat, like the first list shown here. Lists can also be nested within other lists, as in our second example. A linked list is a way of representing nested lists of variable length and depth. Each element is represented by a cell containing 2 items. The first is either an object or a nested list. The second item is either empty or is the remainder of the list. For example, the structure shown here is a linked list representation of the nested list above it. Our goal in this example is to formalize linked lists and define some useful relations on such structures. First step, as always, is representation. To talk about linked lists, we use the binary function constant cons, and we use the object constant nil to refer to the empty list. With this function constant, we can encode the list A, B, C, D, as shown here. Cons of A onto cons of B, onto cons of C, onto cons of D, onto the empty list nil. The signature for our language consists of some object constants, A, B, C, D, and nil, to denote the atomic elements, and a single constant binary function constant, cons. And we'll define 3 relation constants: member, among, and append. Let's start with the member relation, which holds of an object in a list if the object is a top-level element of the list. For example, B is the member of the list consisting of A, B, and C. Using the function constant cons, we can define the member relation as shown here. The first sentence states that an object is a member of a list if it's its first member. For all x and y, if x is a member of cons xy, member x is a member of cons xy. The second sentence states that an object is a member of a list if it's a member of the rest of the list. For all x, y, z, x is a member of z means that x is a member of cons of y and z. Now let's look at concatenation. The result of appending the lists A, B, and C, D would be A, B, C, D. Once again, our definition consists of 2 sentences. The first sentence says that appending an empty list to any list results in that list. The second sentence says that appending a list with x as the first element and y as the remainder to a list Z results in the list with x as the first element, with the remainder being appended to Z. It's worth noting there's a similarity between this definition and the definition of plus in Peano Arithmetic. Here we have an identity nil instead of 0, and here we have cons instead of s. Otherwise, the definitions are very similar. We can also define relations that depend on the structure of the elements of a list. For example, the among relation is true of an object and a list if the object is the list itself, if it's a member of the list, if it's a member of a member, and so forth. In the example shown here, C is not a member of the list itself, supplied as the second argument, but it's among the list because it is a member of the second element of that list. The main lesson to be learned from this example is the use of binary functions in defining complex data structures. Also, lists are extremely versatile representational device, and it's good to become as familiar as possible with the techniques for writing definitions for functions and relations on lists. As is true of many tasks, practice is the best approach to gaining skill. Pseudo-English is a formal language that's intended to approximate the syntax of English language. We want our formal language to include syntactically legal sentences like the ones shown here at the top. Mary likes Pat. Mary likes Pat and Quincy. Pat and Quincy like Mary. At the same time, we'd like to avoid expressions that are not legal sentences like the ones shown here at the bottom. Mary, Pat likes. Likes and Mary, Pat, Quincy, and so forth. One way to define the syntax of English is to write grammatical rules in Backus-Naur form, or BNF. Rules shown here illustrate this approach for a small subset of pseudo-English. Sentence is a noun phrase followed by a verb phrase. A noun phrase is either a noun or two nouns separated by the word and. Verb phrase is a verb followed by a noun phrase. A noun is either the word Mary or the word Pat or the word Quincy. A verb is either like or likes. Alternatively, we can use Herbrand Logic to formalize the syntax of pseudo-English. Sentences here express the grammar described in our BNF rules. If X is a noun phrase and Y is a verb phrase, and Z is the result of appending X to Y, then Z is a sentence. Here we're using the append relation defined in the segment on lists. A noun is a noun phrase. A noun followed by another noun and with and in between is a noun phrase. A verb followed by a noun phrase is a verb phrase. Mary, Pat, and Quincy are nouns. Like and likes are verbs. Okay, now taking these logical definitions as premises, we can use logical entailment procedures to validate syntactically legal sentences and hopefully fail to validate expressions that are not syntactically legal. So, for example, Mary likes Pat, we'll find follows by logical entailment that it is a sentence from the axioms we've just seen. Similarly for the other two correct sentences, and we would not be able to logically entail the non-grammatical sentences. One weakness of our BNF grammar and the corresponding axiomatization is that there's no concern for agreement in number between subjects and verbs. Hence, with these rules, we can get the following expressions, which in natural English are ungrammatical. The grammatical ones, Mary likes Pat and Quincy like Mary. The ungrammatical, Mary like Pat and Quincy likes Mary. Neither of those is a good sentence. So how do we enforce this subject-verb-number agreement? Fortunately, we can fix it by elaborating our rules just a bit. In particular, we add an argument to some of our relations to indicate whether the expression is singular or plural. Here 0 means singular and 1 means plural. Like is a plural verb and likes is a singular verb. A verb with number W leads to a verb phrase with number W. A single noun is a singular noun phrase. A conjunction of nouns is a plural noun phrase. Finally, we use these numbers to ensure that only noun phrases and verb phrases with the same number go together in sentences. With these rules, the syntactically correct sentences shown earlier are still guaranteed to be sentences, but the ungrammatical sentences are blocked. Other grammatical features can be formalized in similar fashion. For example, gender agreement in pronouns, he versus she, and possessive adjectives, his versus her, reflexes, like, herself, and so forth. Throughout this course, we've been writing sentences in English about sentences in logic. when writing informal proofs in English about formal proofs in logic. The natural question to ask is whether logic can be used to describe logic itself. Interestingly, the answer is yes. In this lesson, we're going to look at a small subset of this problem, namely the use of Herbrand logic to formalize information about propositional logic. Basic idea is this. We represent expressions in propositional logic as terms in Herbrand logic. We write Herbrand logic sentences to define basic concepts of propositional logic, and then we prove meta-theorems as formal theorems in Herbrand logic. Ultimately, we can extend this to formalizing information about Herbrand logic as well. Formalization is a bit messier, and some nasty problems need to be handled, notably the problem of paradoxes, but it can be done. And what follows, as I said, we're going to make each proposition constant in our propositional language an object constant in Herbrand logic formalization. For example, if our propositional language has relation constants p, q, and r, then we will use p, q, and r as object constants in our Herbrand logic formalization. Next, we'll introduce function constants to represent constructors of complex sentences. There's one function constant for each logical operator. NOT, not, for negations, and for conjunctions, or for disjunctions, if for implications, and IFF, if and only if, for biconditionals. Using these function constants, we can then represent propositional logic sentences as terms in our Herbrand logic language. For example, we can use the term and of PQ to represent the propositional logic sentence P and Q, and so forth. Finally, we introduce a selection of relation constants to express the types of various expressions in our propositional logic language. We use the unary relation constant proposition to assert that an expression is a proposition. We use the unary relation constant negation to assert that an expression is a negation. We use the unary relation constant conjunction to assert that an expression is a conjunction. We use the unary relation constant disjunction to assert that an expression is a disjunction. And similarly, we use implication for implications and biconditional for biconditionals. And we use the unary relation constant sentence to assert that an expression is a legal sentence. With this vocabulary, we can characterize the syntax of our language as shown here. We start with the declarations of our proposition constants. P is a proposition constant, ditto for Q and R. Next, we define the types of the expressions involved using our various logical operators. If X is a sentence, then not of X is a negation. And of XY is a conjunction if X and Y are sentences, and so forth. Finally, a sentence is either a proposition, or a negation, or a conjunction, or a disjunction, or an implication, or a biconditional. And that's all. Now, with a solid characterization of our syntax, we can formalize our rules of inference. We start by representing each rule of inference as a relation constant. For example, we use the ternary relation constant AI to represent and introduction. And we use the binary relation constant AE to represent and elimination. With this vocabulary, we can define these relations as shown here. If X and Y are sentences, then using and introduction, we can deduce their conjunction. If X and Y are sentences, then using and elimination, we can deduce X, and we can also deduce Y. And the other rules of inference can be formalized in similar fashion. Continuing in this vein, we can define proofs, both linear and structure. We can even define truth assignments, satisfaction, and the properties of validity, satisfiability, and so forth. And having done all this, we can state various meta-theorems, such as the validity of sentences, the soundness of our proof methods, and so forth. And we can use proof methods discussed in the next lessons to prove these meta-theorems formally. We can use a similar approach to formalizing Herbrand logic within Herbrand logic. However, in that case, we need to be very careful. If done incorrectly, we can write paradoxical sentences, that is, sentences that are neither true nor false. For example, a careless formalization leads to formal versions of sentences like "this sentence is false," which is self-contradictory and therefore cannot be true and cannot be false. Fortunately, with care, it's possible to avoid such paradoxes and thereby get some useful work done. Although the languages of propositional logic and Herbrand logic are different, many of the key concepts are the same. Notably, the concepts of satisfiability, validity, contingency, and logical entailment are the same in Herbrand logic as in propositional logic. A sentence is valid if and only if it is satisfied by every truth assignment. A sentence is unsatisfiable if and only if it is not satisfied by any truth assignment. A sentence is contingent if and only if there is some truth assignment that satisfies it and some truth assignment that falsifies it. A sentence is satisfiable if and only if it is valid or contingent, that is, if and only if there's at least one truth assignment that satisfies it. A sentence is falsifiable if and only if it is either contingent or unsatisfiable. That is, if and only if there's at least one truth assignment that falsifies it. Not only are the definitions of these concepts are the same, some of the results are the same as well. If we substitute ground relational sentences for propositions, we get similar results for the two logics. A ground sentence in Herbrand logic is valid, contingent, satisfiable, if and only if the corresponding sentence in propositional logic is valid, contingent, or satisfiable. Here, for example, are Herbrand logic versions of some common propositional logic validities. The law of the excluded middle, P of A or not P of A. Double negation, P of A if and only if not P of A. And De Morgan's laws for distributing negation over conjunction and disjunction. Of course, not all sentences in Herbrand logic are ground. Here are some valid non-ground sentences of Herbrand logic for which there are no corresponding sentences in propositional logic. The common quantifier reversal axioms shown here tell us that reversing quantifiers of the same type has no effect on truth assignment. Existential distribution allows us to move an existential quantifier inside of a universal quantifier. However, note that the reverse is not true. Finally, negation distribution allows us to distribute negation of quantification of either type by flipping the quantifier and negating the scope of the quantified sentence. This exercise tests your understanding of these concepts by asking you to say whether various sentences in Herbrand logic are valid, contingent, or unsatisfiable. A set of sentences delta logically entails the sentence phi, written delta double turnstile phi, if and only if every truth assignment that satisfies delta also satisfies phi. As with validity and contingency and satisfiability, this definition is the same for Herbrand logic as for her propositional logic. As before, if we treat ground relational sentences as propositions, we get similar results. In particular, a set of ground premises in Herbrand logic logically entails a ground conclusion in Herbrand logic, if and only if the corresponding set of propositional logic sentences logically entails the corresponding propositional logic conclusion. For example, the sentence P of A logically entails the sentence P of A or P of B. On the other hand, the sentence P of A does not logically entail P of A and P of B. And any set of sentences containing both P of A and P of B logically entails the single sentence P of A and P of B. The presence of variables allows for additional logical entailments. For example, the premise there exists a y for all x, q of xy, logically entails the conclusion for all x there exists a y, q of xy. If there's some object y that is paired with every x, then every x is some object y that it pairs with, namely y. premise for all x for all y, q of xy logically entails the conclusion for all y for all x, q of xy. First sentence that q is true for all pairs of objects, and the second sentence says the exact same thing. In cases like this, we can just interchange variables. And the premise for all x for all y, q of xy also logically entails the conclusion for all x for all y, q of yx. Same argument. Understanding logical entailment for Herbrand logic is complicated by the fact that it's possible to have free variables in Herbrand logic sentences. Consider, for example, the premise q of xy and the conclusion q of yx. Does q of xy logically entail q of yx or not? If we assume that the x on the left is the same as the x on the right and the y on the left is the same as the y on the right, the answer is no. However, in talking about logical entailment, we do not connect the variables in the premises to the variables in the conclusion in this way. In fact, our definition for logical entailment and the semantics of Herbrand logic give a very clear answer to this question. Logical entailment holds if and only if every truth assignment that satisfies the premises satisfies the conclusion. A truth assignment satisfies a sentence with free variables if and only if it satisfies every instance. In other words, a sentence with free variables is equivalent to a sentence with all of the free variables universally quantified. So the two questions here shown here are the same. This exercise tests your understanding of these concepts by asking you to say whether various sets of premises logically entail various conclusions. Finite Herbrand logic is that subset of Herbrand logic in which the Herbrand base is finite. In order to guarantee a finite Herbrand base, we must restrict ourselves to signatures in which there are at most finitely many object constants and no function constants whatsoever. One interesting feature of FHL, finite Herbrand logic, is that it's expressively equivalent to propositional logic. For any FHL language, we can produce a pairing between the ground relational sentences in that language and the proposition constants in a propositional logic language. And then, given this correspondence, for any set of arbitrary sentences in our FHL language, there is a corresponding set of sentences in the language of PL, such that any FHL truth assignment that satisfies our FHL sentences agrees with the corresponding PL truth assignment applied to the PL sentences. The procedure for transforming our FHL sentences to PL has multiple steps, but each step is really easy. First, we convert to prenex form, then we ground the result, and finally we rewrite in propositional logic. So let's take a look at these steps in turn. Sentences in prenex form, if and only if, first of all, it's closed, and all of the quantifiers are on the outside of all of the logical operators. For example, the first sentence here is in prenex form. The two sentences at the bottom are not. The first fails because the quantifiers are inside of logical operators. The second fails because the sentence contains a free occurrence of the variable y. Converting a set of sentences to a logically equivalent set in prenex form is really easy. First, we rename the variables in different quantified sentences to eliminate any possible duplicates. So in the example shown here, we rename the variable y in the second disjunct. In the second step, we apply quantifier distribution rules to move quantifiers outside of logical operators. Here we move the two quantifiers out. Finally, we universally quantify any free variables in our sentence. In this case, the variable x is free in the sentence, and so we add a universal quantifier for x. Once we have our sentences in prenex form, we compute the grounding. The procedure is described here. We start with our initial set delta of sentences, and we incrementally build up our grounding gamma. On each step, we process the sentence in delta using the rules shown here. The procedure terminates when delta becomes empty. Set gamma at that point is the grounding of the input. The first rule covers the case when the sentence being processed is ground. In this case, we remove the sentence from delta and add it to gamma. Okay, let's look at an example. Suppose we have a language with just two object constants, A and B. And suppose we have the set of sentences shown here. We have one ground sentence, one universally quantified sentence, and one existentially quantified sentence, all are in pre-next form. On the first step, we remove the ground sentence P of A from delta and add it to gamma. On the second step, we remove the universally quantified sentence from delta and add all of its instances to delta. Note that we don't add the instances directly to gamma in general because they might contain nested quantifiers, which then have to be removed as well. Here, however, that's not the case, and on the next two steps, we simply move the two instances to gamma. At this point, we have just the existential sentence to process. We remove it from delta and replace it with disjunction of the target with one disjunct for each constant in our language. And then finally, we remove this ground sentence to gamma, and we're done. Once we have a grounding, gamma, we replace each ground relational sentence in gamma by a propositional constant. Resulting sentences are all in propositional logic, and the set is equivalent to the sentences in the original delta. This delta in that any FHL truth assignment that satisfies our FHL sentence agrees with the corresponding propositional logic truth assignment applied to the propositional logic sentences. For example, let's represent the FHL sentence P of A with a proposition PA. Let's represent P of B with PB. And let's represent Q of A with QA. Let's represent Q of B with QB. So with this correspondence, we can represent the sentences in our grounding with the propositional logic sentences shown here at the bottom. Since the question of unsatisfiability for propositional logic is decidable, then the question of unsatisfiability for FHL is also decidable. Since logical entailment and unsatisfiability are correlated, we also know that the question of logical entailment for FHL is decidable. One other consequence of this correspondence between FHL and PL is that, like PL, FHL is compact. That is, every unsatisfiable set of sentences contains a finite subset that is unsatisfiable. It's important because it assures us that we can demonstrate the unsatisfiability of a set of sentences with just a finite set of sentences. Also, as we shall see in the next lesson, logical entailment can be demonstrated with finite proofs. Omega Herbrand logic, or OHL, is function-free Herbrand logic. Like FHL, there are no function constants, but unlike FHL, we can have infinitely many object constants. And recall that a logic is compact if and only if every unsatisfiable set of sentences has a finite unsatisfiable subset. Unlike propositional logic in FHL, OHL is not compact. There's an infinite set of sentences that is unsatisfiable, yet every finite subset is satisfiable. Suppose that the signature for our language contains the object constants 1, 2, 3, and so forth, and the unary relation constant p. We take the sentences p of 1, p of 2, p of 3, p of 4, p of 5, and so forth. And then we add the single sentence, there exists an x, not p of x. So that's clearly unsatisfiable. Our ground atoms say that p is true of everything, but our existentially quantified sentence says there's something for which p is not true. However, if we were to remove any single one of these sentences, the set as a whole would be satisfiable, and therefore every finite subset is satisfiable. Okay, although it's not compact, OHL is well behaved in one important way. In particular, the question of unsatisfiability for finite sets of sentences is semi-decidable. That is, there's a procedure that takes a finite set of sentences in OHL as argument and is guaranteed to halt in a finite amount of time with a positive answer if the set is unsatisfiable. The procedure may halt with a negative answer. However, this is not guaranteed. If the input set is satisfiable, the procedure might possibly run forever. Okay, the first step of the procedure is to convert our sentences, let's call them delta, to pre-next form using the technique we just talked about in the section on finite Herbrand logic. We then ground the result And finally, we examine finite subsets of the grounding for unsatisfiability. Unfortunately, the grounding technique for FHL does not quite work for OHL, since we can have infinitely many object constants in OHL. In dealing with an existentially quantified sentence, we would have to generate an infinitely large disjunction, and sentences of infinite size are not permitted in our language. Fortunately, there's an alternative form of grounding called omega grounding, which serves our purpose without this defect. It's a little more complicated, however. Okay, so here's the omega grounding. Once we have a set delta of sentences in prenex form, we compute the omega grounding as follows. We start with our set delta, an empty set lambda, and an empty set gamma. And we repeatedly apply the following transformations to the sentences in delta one at a time, processing sentences in the order in which they were added to delta. Our first rule here deals with ground sentences. If a sentence phi in delta is ground, we would simply remove it from delta and add it to gamma, same as with FHL. If our sentence is universally quantified, we remove it from delta, add it to lambda, and also add all instances of the target for each constant that appears in any of our data sets so far. And if our sentence is existentially quantified, we remove it from delta and add an instance of the target for some brand new unused constant. There's always got to be an unused constant. At each point in time, we've only finitely many sentences, while the language has infinitely many constants. So we just take any one of the ones that has not yet been used. We also add to delta instances of the targets of all universally quantified sentences in lambda using this new constant. Here it's called tau. If delta ever becomes empty, the process terminates. In any case, the omega grounding of the initial delta is the union of all the gamma sub I sets. Okay, let's look at an example with the set of sentences shown here. We have one ground sentence, one universally quantified sentence, and one existentially quantified sentence. All are in prenex form. Computation goes as follows. First sentence is ground, so we remove it from our input set and add it to gamma. Second sentence is universally quantified, so we add it to lambda, and we replace it on delta with a copy with the single object constant we have, namely 1, substituted for the universally quantified variable. Next, we focus on the existential sentence. We drop the sentence from delta and add an instance in its place. Here we have replaced the existential variable with the previously unused constant 2. We also use 2 in another instantiation of the quantified sentence in lambda. Okay, at this point, everything in delta is ground, so we just move all the sentences down to gamma. At this point, since we have run out of sentences in delta, the procedure's finished, and gamma 6 here is the omega grounding for the initial set of sentences. Okay, note that when there's an existentially quantified sentence nested within a universally quantified sentence, the result of this procedure can be infinite in size. Okay, let's look at this example. Set of sentences here is shown here is of a sort. Okay, the procedure goes as follows. First sentence is ground, so we remove it from delta and add it to gamma. The next sentence is universally quantified, so we add it to lambda and replace it in delta with a copy for each constant mentioned in our sentences. In this case, there's just the one constant, namely 1. Next, we ground the existential sentence using a new constant, in this case 2, and add that result to delta. We also add a corresponding instance of the universally quantified sentence in lambda. Our ground sentence is then moved to gamma. Again, we ground our existential sentence, in this case using the constant 3. And again, we instantiate the universally quantified sentence in lambda. As before, we move the ground sentence to gamma. The construction in this case goes on repeatedly. The union of this infinite set of gamma sub I sets is the omega grounding for delta. Although the set in principle is finite, we don't actually need to compute the entire grounding, just subsets of increasing size. Okay, so now note that the omega grounding for a finite set of OHL sentences is all ground. We know that if the set of a ground sentence is unsatisfiable, then there must be a finite subset that's unsatisfiable. Hence, to determine unsatisfiability, we can just check finite subsets of our omega grounding as it is being generated. If the set is unsatisfiable, we will eventually encounter an unsatisfiable set in this process. Otherwise, it might run forever. In any case, it demonstrates the semi-decidability of OHL. So we've seen finite Herbrand logic is very well behaved. All questions are decidable. With omega Herbrand logic, we can say more. Admittedly, we lose decidability, though we retain semi-decidability. What happens when we relax our restrictions and look at general Herbrand logic, GHL? That is Herbrand logic without any restrictions whatsoever. Good news about GHL is that it's highly expressive. We can formalize things in GHL that cannot be formalized, at least not in finite form, in the other subsets we've looked at so far. For example, in an earlier segment, we showed how to formalize addition and multiplication in finite form. It's not possible with restricted forms of Herbrand logic, like FHL and OHL, and it's not possible in other logics, such as first-order logic. The bad news is that the question of unsatisfiability for GHL is not even semi-decidable. Explaining this in detail is beyond the scope of this course. However, we can give a line of argument that suggests why it is true. The argument reduces the question of decidability, of satisfiability, logical entailment, and so forth for GHL to a question as broadly accepted to be undecidable. So if our logic were decidable, then this other question would be decidable, and since it's known to be undecidable, logical entailment for GHL must also be undecidable. Okay, as we know, Diophantine equations can be readily expressed as sentences in GHL. For example, we can represent the solvability of the Diophantine equation 3x squared equals 1 with the sentence there exists an x such that x times x is, there exists an x and a y such that x times x is y and 3 times y is 1. We can represent every Diophantine in an analogous way. And we can express the unsolvability of a Diophantine equation by negating that sentence, saying there does not exist such an x and a y. We can then ask the question of whether the axioms of arithmetic logically entail this negation, or equivalently, whether the axioms of arithmetic together with the unnegated sentence are unsatisfiable. Problem is that it's well known that determining whether the natural Diophantine equations are unsolvable is not semi-decidable. If we could determine the unsatisfiability of our GHL encoding of a Diophantine equation, we could decide whether it's unsolvable, contradicting the non-semi-decidability of that problem. Note that this does not mean that GHL is useless. In fact, it's great for expressing such information. And as we'll see, we can prove many results, even though in general we cannot prove everything that follows from an arbitrary set of sentences in Herbrand logic. We're going to discuss this issue further in future lessons. Logical entailment for Herbrand logic is defined the same as for propositional logic. A set of premises logically entails a conclusion if and only if every truth assignment that satisfies the premises also satisfies the conclusion. In the case of propositional logic, we can check logical entailment by examining a truth table for the language. With finitely many proposition constants, the truth table can be large, but it's still finite. For Herbrand logic, things are not so easy. It's possible to have Herbrand bases of infinite size, for example, when the language contains function constants. In such cases, truth assignments are infinitely large, and there are infinitely many of them, making it impossible to check logical entailment using truth tables. Fortunately, all is not lost. As with propositional logic, we can define a proof system for Herbrand logic. And interestingly, it's possible to show that, with a few simple restrictions, a set of premises logically entails a conclusion if and only if there's a finite proof of the conclusion from the premises, even when the Herbrand base is infinite. Moreover, it's possible to find such proofs in finite time. Sadly, things are not quite perfect, though. If a set of sentences does not logically entail a conclusion, then the process of searching for a proof might go on forever. And moreover, if we remove the restrictions I mentioned earlier, we even lose the guarantee of finite proofs. Still, this relationship between logical entailment and finite provability, given those restrictions I mentioned, is a very powerful result and has enormous practical consequences. In this lesson, we start by defining a proof system for Herbrand logic based on Fitch. We then illustrate the system with a few examples. And finally, we talk about the soundness and completeness of the proof system given various restrictions. Formal proofs in Herbrand logic are similar to formal proofs in propositional logic. The main difference is that there are additional mechanisms for dealing with quantified sentences. In the Fitch system for Herbrand logic, we include all 10 of the rules of inference for propositional logic. We have negation and introduction and negation elimination, implication introduction, implication elimination, biconditional introduction, biconditional elimination, and we have introduction and elimination rules for both conjunctions and disjunctions. In addition to these logical rules of inference for logical operators, we have 4 new rules of inference for quantified sentences, introduction and elimination rules for both universal and existential sentences. Let's look at these in turn. Now, if you're like me, the prospect of going through a discussion of 4 rules of inference sounds a little bit repetitive and boring. However, it's not so bad. Each of the rules has its own quirks and idiosyncrasies, its own personality, if you will. In fact, a couple of the rules suffer from what I might characterize as a distinct excess of personality. For we to use the rules correctly, however, we need to understand these little idiosyncrasies. Universal introduction, or UI, allows us to reason from arbitrary sentences to universally quantified versions of these sentences, subject to a constraint that we're going to discuss shortly. Typically, UI is used on sentences with free variables to make their quantification explicit. For example, if we have the sentence, hates Jane X, then we can infer, for all X hates Jane X. Note that we can also apply the rule to sentences that do not contain the variable that's quantified in the conclusion. For example, from the sentence, hates Jane Jill, we can infer, for all X hates Jane Jill. And from the sentence, hates Jane Y, we can infer, for all X hates Jane Y. These are not particularly sensible conclusions. However, the results are correct, and the deduction of such results is necessary to ensure that our proof system is complete. Now, there's one important restriction on the use of universal introduction. If the variable being quantified appears in the sentence being quantified, it must not appear free in any active assumption. That is, an assumption in the current subproof or any superproof of that subproof. For example, if there's a subproof with assumption P of X, and from that we have somehow managed to derive Q of X, then we cannot just simply write for all X, Q of X. If we want to quantify a sentence in this situation, we must first use implication introduction to discharge the assumption, and then we can apply UI. In the example here, we first apply implication introduction to derive the result P of X implies Q of X, in the parent of the subproof containing our assumption, and then we apply universal introduction to derive for all x, p of x implies q of x. Our second rule of inference is universal elimination, or UE. Universal elimination allows us to reason from the general to the particular. It states that whenever we believe a universally quantified sentence, we can infer a version of the target of that sentence in which the universally quantified variable is replaced by an appropriate term. I'll explain this condition in a minute, but first some examples. Consider the sentence, for all x hates Jane X. Jane hates everyone. From this premise, we can infer that Jane hates Jill. We can also infer that Jane hates her mother. And we can even infer that Jane hates herself. In addition, we can use universal elimination to create conclusions with free variables. For example, we can infer hates Jane X, or equivalently, hates Jane Y. In using universal elimination, we have to be careful, though, to avoid conflicts with other variables and quantifiers in the quantified sentence. This is the reason for that constraint on the replacement term that we saw earlier. Consider the sentence, for all x, there exists a y, hates xy. In other words, everybody hates somebody. From this sentence, it makes sense to infer there exists a y such that hates Jane Y. In other words, Jane hates somebody. However, we do not want to infer there exists a y hates y. In other words, there's somebody who hates herself. The problem here is that the quantifier in the sentence has captured the variable being substituted, and we need to avoid this. Let's formalize this notion of capture. An occurrence of a variable nu in an expression phi captures a term tau if and only if tau contains a variable mu, and the occurrence of nu lies in the scope of a quantifier of mu. What? That's a fairly complicated definition. Fortunately, it's really easy to understand via an example. Suppose you want to substitute mother of x for y, and there exists an x hates xy. We cannot, because the occurrence of y in there exists an x hates xy captures mother of x. Why? Because mother of x contains a variable x, and the occurrence of y lies in the scope of a quantifier of x. What follows, we say that a term is substitutable for a variable nu in phi if and only if there's no free occurrence of nu that captures tau. Some texts say that tau is free for nu in phi. Let's look at some examples. Mother of Jane is free for y and hates Jane Y, since the term contains no variables at all. The term mother of x contains variables, but it's free for y and hates Jane Y, since there are no quantifiers. The term mother of x is free for y and there exists an x hates zy, because it does not contain a variable that is quantified. Here's a tricky case. The term mother of x is not free for y, and there exists x hates xy, because there is an occurrence of y in the sentence that lies within the scope of a variable contained in mother of x. And finally, mother of x is free for y in this complex sentence here at the bottom. Although there's a quantifier of x in the sentence, it's okay because the only free occurrence of y lies outside the scope of this quantifier. Avoiding conflicts of this sort is the main reason for the substitutability condition in the definition of universal elimination. When using the rule, if we obey the law, we won't get into trouble. Existential introduction's easy. Not much personality here. If we believe a sentence involving a ground term tau, then we can infer an existentially quantified sentence in which one, some, or all occurrences of tau have been replaced by the quantified variable, with the assumption that tau does not occur in phi. For example, from the sentence hates Jill, we can infer that there is someone who hates herself. There exists X hates XX. We can also infer that there is someone Jill hates. In other words, there exists X hates Jill X, and there's someone who hates Jill. In other words, there exists X hates X Jill. And by two applications of existential introduction, we can infer that someone hates someone. There exists X, there exists Y, hates XY. Note, however, that it's important in existential introduction to avoid variables that appear in the sentence being quantified. Without this restriction, starting from there exists X hates Jane X, we might deduce there exists an X such that there exists an X hates XX. It's a kind of odd sentence since it contains nested quantifiers of the same variable. However, it's a legal sentence and it states that there is someone who hates herself, which does not follow from the premise in this case. Finally, existential elimination. Suppose we have an existentially quantified sentence with scope phi, and suppose we have a universally quantified implication in which the antecedent is the same as the scope of our existentially quantified sentence, and the conclusion does not contain any occurrence of the quantified variable. Then we can use existential elimination to infer the consequent. For example, if we have the sentence there exists X hates Jane X, and we have the sentence for all X hates Jane X implies not nice of Jane, then we can conclude not nice of Jane using one application of existential elimination. As an illustration of these concepts, consider the following problem. Suppose we believe that everybody loves somebody, and suppose we believe that everyone loves a lover. Our job is to prove Jack loves Jill. First, we need to formalize our premises. Everybody loves somebody. For all y, there exists a z such that loves y, z. Everybody loves a lover. If a person is a lover, then everybody loves him. If a person y loves another person, he's a lover, and therefore everyone loves y. For all x and for all y and for all z, loves of yz implies loves of xy. Okay, here's our proof. The sentence on line 3 is the result of applying universal elimination to the sentence on line 1, substituting Jill for y. Jill's the lover in our problem. The sentence on line 4 is the result of applying universal elimination to the sentence on line 2, substituting Jack for x. Jack is the person who loves Jill. The sentence on line 5 is the result of applying universal elimination to the sentence on line 4, substituting Jill for y. Finally, we apply existential elimination to produce the conclusion on line 6. Now let's consider a slightly more interesting version of this problem. Start with the same premises. However, our goal now is to prove the somewhat stronger result that everybody loves everybody. For all x and for all y, x loves y. The proof here is analogous to the proof we just saw. As always, we start with our premises. These are the same as before. Once again, we use universal elimination to produce the result on line 3, but this time the result contains the free variable y instead of Jill. We get the results on lines 4 and 5 by successive application of universal elimination to the sentence on line 2. And as before, we deduce the result on line 6 using existential elimination. Finally, we use two applications of universal introduction to generalize our result and produce the desired overall conclusion. This exercise is a chance to develop your proof skill by asking you to do a proof similar to the ones we just saw. Here we have another example of our proof system in action, this time introducing a trick for using existential sentences in proofs. We know that horses are faster than dogs, and we know there is at least one greyhound that is faster than every rabbit. We know that Harry's a horse and Ralph is a rabbit. Our job is to prove that Harry is faster than Ralph. First of all, we need to formalize our premises. The relevant sentences are shown here. Horses are faster than dogs. For all x, y, if x is a horse and y is a dog, then x is faster than y. There is some greyhound that can outrun every rabbit. There is a y, such that y is a greyhound. And for all z, if z is a rabbit, then y is faster than z. Greyhounds are dogs. For all x, g of x implies d of x. Outrunning, the faster than relation, is transitive. For all x, y, z, if x is faster than y, y is faster than z, then x is faster than z. And finally, Harry's a horse and Ralph is a rabbit. Note that we've added these two facts about the world not stated explicitly in the problem, namely that greyhounds are dogs and that the faster relationship is transitive. Now note this existential sentence in line 2. The trick for using such a sentence is to start a subproof, assume the scope of the existential sentence, derive a conclusion in the subproof, and then use implication introduction, universal introduction, and existential elimination to promote the conclusion to the top level. Let's see how that works in practice. On line 7, we start our subproof with an assumption corresponding to the scope of the existential on line 2. G of y and, for all z, r of z implies f of y, z. Lines 8 and 9 come from and elimination applied to line 7. Line 10 is the result of applying universal elimination to the sentence in line 9. And on line 11, we use implication elimination to infer that y is faster than Ralph. Next, we instantiate the sentence about greyhounds and dogs and infer that y is a dog. Then, we instantiate the sentence about horses and dogs, and we use and introduction to form a conjunction matching the antecedent of this instantiated sentence. Harry is a horse and y is a dog, and we infer, therefore, that Harry is faster than y. Now we have y is faster than Ralph and Harry is faster than y. We're almost there. Here we instantiate the transitivity sentence for the faster than relation with 3 applications of universal elimination. We form the necessary conjunction and infer the conclusion that Harry is faster than Ralph. Unfortunately, it's still in a subproof, and we need to get it to the top level to eliminate the assumption that allowed us to produce this result. So, we use implication introduction to discharge our subproof. We use universal introduction to universalize this result. And we use existential elimination to produce our overall conclusion. The main thing to take away from this example is how we assumed the scope of the existential in the second line, then proved our results, and then used existential elimination to promote those results to the top level.
In this section, we use our proof system to prove some basic results involving quantifiers. While doing so, I will also demonstrate the proof editor you will use this week. Given for all x, for all y, if p of x, y, then q of x. We know that for all x, if there exists y, p of x, y, then q of x. In general, given a universally quantified implication, it is okay to drop the universal quantifier outside the implication and apply an existential quantifier of the same variable in the antecedent of the implication, provided that the variable does not occur in the consequence of the implication. Now let's move on to a Fitch proof. First, we input the premise. We use the uppercase A for the universal quantifier, uppercase letters for variables, and a colon symbol to separate a quantification from a quantified sentence. Our strategy is to first prove the implication that if there exists y, p of xy, then q of x. And then using universal introduction, we can obtain our goal. So here we go. First, we assume the antecedent of our desired conclusion. We apply universal elimination to strip away the outer quantifier from our premise. We use existential elimination to conclude q of x. Now we use implication introduction to obtain the implication we wanted. Finally, we finish by introducing the universal quantifier in our goal. And we're done. The relationship holds the other way around as well, given that for all x, if there exists y, p of xy, then q of x. We know that for all x, for all y, if p of xy, then q of x. We can convert an existential quantifier in the antecedent of an implication into a universal quantifier outside the implication. Now, let's look at a Fitch proof. As usual, we start with the premise. Our strategy is to first prove the implication that if p of xy, then q of x. Then we can introduce two universal quantifiers to obtain our goal. So here we go. First, we assume the antecedent of our desired implication. We use universal elimination to strip away the universal quantifier of our premise. We use existential introduction to form the antecedent of line 3. Now we can apply implication elimination to obtain q of x. We use implication introduction to get the implication we want. Finally, we use universal introduction twice to obtain our goal. Once on the inner variable, then on the outer variable. And we're done.
One of the problems of natural deduction systems like Fitch is that there are rules that require that we choose from infinitely many possible instances. For example, the assumption rule allows us to assume any legal sentence. And the universal elimination rule allows us to substitute almost any legal term for the variables in universally quantified sentences. Herbrand Resolution is a proof system for Herbrand Logic that does not have this problem. As we shall see, Herbrand Resolution allows us to derive conclusions from premises without making arbitrary substitutions. Like propositional resolution, Herbrand Resolution relies on a single rule of inference called the resolution principle. Using the resolution principle alone, without axiom schema or any other rules of inference, it's possible to build a reasoning system that's able to prove everything that can be proved in Fitch. Moreover, the search space using the resolution principle is smaller than the search space for generating Fitch proofs. This lesson is devoted entirely to Herbrand Resolution. We start with a look at Clausal Form, a variation of the language of Herbrand Logic. We then discuss unification, which is the key to the power of Herbrand Resolution. And then we examine the resolution rule of inference in detail. Finally, we show how it's used in determining unsatisfiability, checking logical entailment, and in extracting answers to fill-in-the-blanks type questions. As with propositional resolution, Herbrand resolution works only on expressions in clausal form. Fortunately, it's possible to convert any set of Herbrand logic sentences into an equi-satisfiable set of expressions in clausal form. The definitions here are analogous to those for propositional resolution. A literal is either a relational sentence or a negation of a relational sentence. A clausal sentence is either a literal or a disjunction of literals. And a clause is a set of literals, and as in propositional logic, represents a disjunction of the literals in the set. As with propositional clausal form, the empty set is also a clause. It's equivalent to the empty disjunction and therefore is unsatisfiable. The procedure for converting relational sentences to clausal form is similar to that for propositional logic. It goes by the catchy name of INCEDO, which is an acronym for the steps of the procedure. Some of the rules are the same as those for propositional logic. However, there are a few additional rules to deal with variables and quantifiers. In the first step, implications out, we eliminate all occurrences of the implication and biconditional operators by substituting equivalent sentences involving only and, or, and not. In the second step, negations in, negations are distributed over other logical operators and quantifiers until each operator applies to a single atomic sentence. The replacement rules shown here do the job. We eliminate double negations. We use De Morgan's laws to distribute negations over conjunctions and disjunctions. And we distribute negations over quantifiers. When this step is done, any remaining negations are applied directly to atomic sentences. In the third step, standardized variables, we rename variables so that each quantifier has a unique variable. That is, the same variable is not quantified more than once within the same sentence. For example, in the case shown here, we rename the variable x in the second disjunct to y. In the fourth step, existentials out, we eliminate all existential quantifiers. Now, the methods for doing this is a little complicated, and there are two cases. If an existentially quantified sentence does not contain any free variables and does not occur within the scope of a universal quantifier, we simply drop the existential quantifier and replace all occurrences of the quantified variable by a new object constant, that is, one that's not part of the language. The constant used to replace the existential variable in this case is called a Skolem constant. In the example shown here, we've replaced x by a, when the assumption a was not in the original language. If an existentially quantified sentence contains free variables, or if it lies within the scope of any universal quantifiers, there's the possibility that the value of the existential variable depends on the values of the associated universal variables. Consequently, we cannot replace the existential variables with a single constant. Instead, the general rule is to drop the existential quantifier and to replace the associated variable by a term formed from a new function symbol applied to the variables associated with the free variables, and universally quantify variables in the target. Any function defined in this way is called a Skolem function. So the example here illustrates the transformation. It assumes f is not part of the language. In the case shown here, the existentially quantified sentence contains a universally quantified variable x and a free variable y. And so we create a term by taking f and applying it to x and y. In the fifth step, all's out, we drop all universal quantifiers. Because the remaining variables at this point are all universally quantified, this does not introduce any ambiguities. In the sixth step, disjunctions in, we put the expression into conjunctive normal form. That is a conjunction of disjunctions of literals. It's accomplished by repeated use of the distribution rules listed here, same as in propositional logic. And in the seventh and final step, operators out, we eliminate operators by separating any conjunctions into its conjuncts and writing each disjunction as a separate clause. Okay, that's it for the general procedure. Now, as an example of this conversion process, consider the problem of transforming the expression shown here to clausal form. The initial expression appears on the top line. The expressions in the labeled lines below it are the results of the corresponding steps of the conversion procedure. On the I step, we get rid of the implication operator. The N step has no effect since the only negation in the sentence is already applied to an atomic sentence. The S step has no effect because there are no duplicate variables. On the E step, we notice that the quantified sentence contains no free variable, so we simply replace the quantified variable by a new constant, in this case Greg. The A step and the D step have no effect. And finally, on the O step, we convert our conjunction into two separate clauses. Okay, here's another example. In this case, starting sentence is almost the same. The only difference is the leading not operator. But the result looks quite different. As before, on the I step, we get rid of the implication operator. This time, the N step's a little more interesting. We need to push that negation sign down through all of the sub-expressions. First, distribute over the existential, flipping it to a universal and negating the target. We then distribute the negation over the conjunction, leading to a disjunction of negated disjuncts. We distribute the negation in the second disjunct over the universal quantifier, flipping it to an existential and negating the target. We distribute that negation over the disjunction, and finally we eliminate the double negation. The S step here has no effect. On the E step, we note that the existentially quantified sentence does contain a free variable, so we replace the existentially quantified variable, in this case with a term consisting of a Skolem function and the free variable y. On the A step, we drop the universal quantifier. On the D step, we distribute the disjunction over the conjunction. And finally, in the O step, we convert our conjunction of disjunctions to two separate clauses. In propositional logic, the clausal set corresponding to any sentence is logically equivalent to that sentence. In Herbrand logic, this is not necessarily the case. For example, the clausal form of the sentence, there exists an x, p of x, is something like p of a. This is not logically equivalent. It's not even in the same language. Since the clause exists in a language with an additional object constant, there are truth assignments that satisfy the sentence but not the clause. On the other hand, the clause is effectively equivalent to the original sentence in the sense that it's satisfiable in the expanded language if and only if the original sentence is satisfiable in the original language. And as we'll see, in resolution, this equivalence of satisfiability is really all we need. Unification is the process of determining whether two expressions can be unified, that is, made identical by appropriate substitutions for their variables. As we'll see shortly, making this determination is an essential part of resolution. A substitution is a finite mapping of variables to terms. In what follows, we'll write substitutions as sets of replacement rules, like the one shown here. In each rule, the variable to which the arrow is pointing is to be replaced by the term from which the arrow is pointing. In this case, x is to be replaced by a, y is to be replaced by f of b, and v is to be replaced by w. The result of applying a substitution, it's called sigma, to an expression phi, is the expression written phi sigma, obtained from phi by replacing every occurrence of every variable in sigma by the term with which it is associated. For example, applying our substitution to the expression p of x, x, y, z yields p of a, f of b, and z. Given two or more substitutions, it's possible to define a single substitution that has the same effect as applying those substitutions in sequence. For example, the substitutions x gets a, y gets f of u, z gets v, and u gets d, v gets e, and z gets g can be combined to form the single substitution x gets a, y gets f of d, z gets e, u gets d, and v gets e. And the single substitution has the same effect as the first two substitutions when applied to any expression whatsoever. Computing the composition of a substitution sigma and a substitution tau is easy. Okay, there are three steps. First, we take tau and apply it to the replacements in sigma. Having done that, we join to sigma all pairs from tau which have different variables than those in sigma. Notice that in this case, we did not include the binding of z to g from tau because we already had a binding of z to e in sigma. Finally, in the third step, we delete any assignments of variables to themselves. No examples of that in this case. Okay, now why do we care about substitutions? Well, it's the first step in unification. Say a substitution sigma is a unifier for an expression phi and expression psi if and only if phi sigma is the same as psi sigma. In other words, sigma applied to phi and sigma psi applied to psi produce the same expression. If two expressions have a unifier, they're said to be unifiable, and otherwise they're non-unifiable. So an example of non-unifiable expressions shown here would be p of x, x on the one hand, and p of a, b on the other. There's no way to bind x so that it's the same as a and at the same time the same as b. Okay, now although the substitution unifies two expressions, it may not be the only unifier. We don't have to substitute b for y and v to unify two expressions. We can equally well substitute c or d or f of c or f of w. In fact, we can unify the expressions without changing v at all by simply replacing y by v. Now, in considering these alternatives, it should be clear that some substitutions are more general than others. In fact, we're going to enshrine that with a definition. We say that a substitution sigma is as general as or more general than a substitution tau, if and only if there's another substitution, delta, such that tau is the composition of sigma and delta. For example, the substitution at the bottom here is more general as or more general than the other two, since each of the first two can be contained by composing unifier at the bottom with another substitution. And in fact, the substitution at the bottom is more general than the other two in that the reverse does not hold. There's no way to convert either one of the first two into the third unifier by applying an additional substitution. Now, in resolution, we're interested only in unifiers with maximum generality. It's called a most general unifier, or MGU. And it's defined as follows. An MGU sigma of two expressions has the property that is as general as or more general than any other unifier. Now, it's possible for two expressions to have more than one most general unifier. However, even though this is the case, all of the most general unifiers are structurally the same. In other words, they're unique up to variable renaming. For example, p of x and p of y can be unified by either the substitution x gets y or by the substitution y gets x. And either of these substitutions can be obtained from the other by applying a third substitution. It's not true of those unifiers we saw earlier. Okay, one good thing about our language is that there is a simple and quite inexpensive procedure for computing the most general unifier of any two expressions, provided that there is one. The procedure assumes a representation of expressions as sequences of sub-expressions. For example, the expression P of A, F of B, and Z can be thought of as a sequence with four elements, namely the relation constant P, the object constant A, the term F of BC, and the variable Z. The term F of BC can in turn be thought of as a sequence of three elements, namely the function constant F, the object constant B, and the object constant C. Okay, given that representation, we can describe the procedure in detail. We start with two sub-expressions and a substitution, which is initially empty. We then recursively process the two expressions, comparing the sub-expressions of those expressions at each point. Along the way, we expand the substitution with variable assignments, as we'll see. If we fail to unify any pair of sub-expressions at any point in the process, the procedure as a whole fails. If we finish the recursive comparison of the expressions, the procedure as a whole succeeds, and the accumulated substitution at that point is our most general unifier. Okay, the rules are these. If two expressions being compared, or two sub-expressions being compared, are identical, we succeed on that step. If neither one is a variable, and at least one is a constant, then we fail. If at least one of the expressions is a variable, we proceed as described in just a moment. However, if both expressions are sequences, neither variables nor constants, then we iterate across the expressions comparing sub-expression to sub-expression as just in the same manner as just described. Okay, now what about the case where we have at least one of the expressions being a variable? Right, in this case, we first check whether the variable has a binding in the current substitution. If so, we try to unify that binding with the other expression. If there's no binding, we can give it a binding, but first we check whether the second expression contains the variable to which we're binding it. If the variable occurs within the expression, we fail. Otherwise, we set the substitution to the composition of the old substitution and a new substitution which we bind the variable to that second expression. This will all become a lot clearer when you look through some examples right now. So here's our first example. Consider the computation of the most general unifier for the expressions P of xb and P of ay with the initial substitution empty. The trace of the execution of the procedure for this case is shown here. We show the beginning of a comparison with a line labeled call, together with the expressions being compared and the input substitution. And we show the result of that comparison with a line labeled exit. At each point here, the indentation shows the depth of recursion of the procedure. Okay, so here on the first nested step, we compare the first element of the first expression with the first element of the second expression. Since they're identical in this case, we succeed with no changes to our substitution. We then compare the variable x to the constant a, in this case leading to a binding of x to a. And finally, we compare b to y. In this case, we compose the current variable assignment, x gets a, with assignment of y to b, which produces the joint assignment, x gets a, y gets b. At this point, having reached the ends of both expressions, we're done. Okay, here's another example. Consider unifying the expressions P of xx and the expression P of ay. Here's our trace. The main interest in this case is in the step involving x and y. So at this point, x has a binding to a, and so we recursively compare that binding of y, the replacement, which is a in this case, to y. In this case, we can bind y to a. We compose that substitution with the original substitution to produce the resulting composite substitution, x gets a and y gets a. And again, since we're done processing all of the sub-expressions, the substitution at this point is the most general unifier. Okay, here's an example where two expressions do not unify. Start the same as before. This time, when we compare the second x to b, we get a different result. As before, we retrieve that binding of x, namely a, and try to unify a with b. Since these are two different constants, we fail, and unification as a whole fails. Okay, here's one more example. This one's similar to that last one, except that the second term in the second expression is the functional term that contains y. After unifying the first two arguments, we find ourselves trying to unify x and f of y with the substitution where x is bound to y. Now, in order for this to work, we would have to unify y and f of y. We'd have to bind y to f of y. But now remember back to the condition that I mentioned on variable assignments. We must not ever bind a variable to a term which contains itself. Since f of y contains y, the substitution, the unification process in this case fails, and the unification process as a whole fails. Okay, now you might be wondering why exactly we have this condition that a variable may not be bound to itself. Okay, well, one reason is this. If we were to allow bindings of variables to expressions that contain those variables, it would lead to circular bindings. Now, this in itself is not a problem, though it does raise the question of how many times the substitution needs to be applied. More importantly, though, it can create a situation where the substitution does not actually unify the input expressions, no matter how many times it's applied. Okay, as we see here, applying the substitution does not lead to the same result, and it fails no matter how many times we apply it. The second argument in the second case always has one additional application of f, and so these expressions will never look alike. It's the reason why we check whether variables contained in an expression before creating a binding. And it has a name, it's so important, this condition. It's called the occur check, for obvious reasons. Interestingly, though, not all logical systems do this occur check. Prolog, programming language Prolog, is notable for not performing the occur check, or at least not by default in most systems. Programmatically, it's useful as a way of generating circular data structure, or logically, it can lead to errors, and so in logic, we always do the occur check in resolution. In propositional logic, if we have a clause containing a literal phi and another clause containing a literal not phi, we can use propositional resolution to derive a new clause by collecting together the literals from both clauses, except for this complementary pair of literals. Resolution for Herbrand logic is similar, except that the positive literal and the target of the negative literal do not need to be identical. It suffices that they are unifiable. A slightly simplified version of the rule is shown here. Given a clause with a literal phi and a second clause with a literal not psi, such that phi and psi have a most general unifier sigma, we can derive a new clause by collecting together the remaining literals from each of the parent clauses and applying sigma to the result. Here's an example. Supposing we have a clause containing the literal p of ay and another clause containing the literal not p of xb. We can unify p of ay and p of xb with the most general unifier x gets a and y gets b. Hence, we can resolve these two clauses. We form a new clause consisting of the remaining literals from each clause, in this case r of y and s of x. We apply the most general unifier to this clause, and we thereby produce the resolvent, namely the clause consisting of the literals r of b and s of a. Okay, we'll see how to use resolution to solve some interesting problems in the next segment, but first we need to refine our definition a bit to deal with a couple of shortcomings of this simplified definition. Consider the two clauses shown here. Given the meaning of these two clauses, it should be possible to resolve them to produce the empty clause. However, the two atomic sentences don't unify. The variable x must be bound to a and b at the same time, and that's not possible. Fortunately, this problem can be solved by extending the resolution principle just slightly, as shown here. Before trying to resolve the two clauses, we select one of the clauses and rename any variables of the clause has in common with the other clause. Renaming solves our problem. We simply change the variables in one of our clauses before attempting to resolve them. After renaming, we see that the positive literal and the target of the negative literal can be unified, hence they can be resolved, in this case leading to the empty clause. Okay, unfortunately we're still not quite done. There's one more technicality that must be addressed to finish the story. As stated, even with variable renaming, the rule is not quite good enough. Given the clauses shown here, we should be able to infer the empty clause. However, again, this is not possible with the preceding definition. The clauses can be resolved in various ways as shown here, but the result is never the empty clause. If a subset of literals in a clause phi has the most general unifier gamma, then the clause phi obtained by applying gamma to phi is called a factor of phi. For example, the literals p of x and p of f of y have a most general unifier x gets f of y. So the clause p of x, p of f of y, p of f of y, r of f of y, y is a factor of p of x, p of f of y, r of x, y. Note that any clause is trivially a factor of itself as well. Using the notion of factors, we can give a complete definition of the resolution principle that solves all of our little problems. Supposing that capital phi and capital psi are two clauses. If there is a literal little phi in some factor of capital phi, after renaming, and there is a literal not little psi in some factor of capital psi, such that little phi and little psi have a most general unifier, then we can reform a resolvent of these two clauses as shown here. And using this enhanced definition of resolution, we can solve the problem mentioned above. Once again, consider the premise p of x, y, p of x, p of y, and the premise not p of u, not p of v. The first premise has the factor p of x, the second has the factor not p of u, and these two factors resolve to produce the empty clause in a single step. Note that we can't just replace a clause by its factors. You have to retain the original clauses as well. All right, this example shows what goes wrong if we try to replace a clause by its factor. The three premises at the top here lead to the empty clause after two steps of resolution. Resolve 1 and 2 to produce the clause on line 4, and then we resolve 3 and 4 to produce the clause on the empty clause on line 5. If we were to discard the clause on line 1, even though because it has a factor, and replace it by that factor, we'd find ourselves stuck. There would be no further resolutions. The upshot of this is that factoring is useful. It allows us to derive conclusions we would not otherwise be able to produce. However, we must consider resolutions with unfactored clauses as well if we want to be sure to produce all possible conclusions. Okay, that's it for our treatment of the resolution rule. Now it's time to put it to work solving some logic problems. And as it turns out, there's quite a bit we can do with it. Simplest use of resolution is in demonstrating unsatisfiability. In Clausal Form, a contradiction takes the form of the empty clause, which is equivalent to the disjunction of no literals. Thus, to automate the determination of unsatisfiability, all we need to do is to use resolution to derive consequences from the set to be tested, terminating when the empty clause is finally generated. Let's start with a simple example. Suppose we have four premises which are jointly unsatisfiable. P of A or B or Q of AC. P of xy implies R of x, Q of xy implies R of x, and not R of z. The derivation of the empty clause in this case is easy. We resolve the first clause with the second to get the clause shown on line 5. In this case, x is bound to A, y is bound to B. Next, we resolve the result with the third clause to get the unit clause on line 6. Note that R of A is the remaining literal from clause 3 after the resolution, and R of A is also the remaining literal from clause 5 after the resolution. Since the two clauses literals are identical, they appear only once in the result, because of course the result is a set of literals. Finally, we resolve this result with the clause in line 4 to produce the empty clause. The resolution derivation of a clause phi from a set delta of clauses is a sequence of clauses terminating in phi, in which each item is a member of delta or the result of applying resolution to earlier items. We define a resolution proof to be a derivation of the empty clause from the clausal form of the premises and the negation of the desired conclusion. And we say that a sentence phi is provable from a set of sentences delta by resolution, if and only if there's a derivation of the empty clause from the clausal form of delta together with not phi. As an example of using Herbrand resolution to determine logical entailment, let's consider the case we saw earlier. Premises are shown here. We know that everybody loves somebody, and everybody loves a lover. Our goal is to show that everybody loves everybody. So we negate this conclusion and add it to our set of premises. Next, we convert to clausal form, leading to the clauses shown here at the bottom. Note the use of the Skolem function in the first clause, and use of Skolem constants in the clause derived from the negated goal. In order to prove the result, we start with our premises. We resolve the clause on line 1 with the clause on line 2 to produce the clause on line 4. And then we resolve the clause on line 4 with the clause on line 3 to produce the empty clause, and thus prove our result. That's it. Slightly more complicated example. Let's once again consider the problem of horses and dogs introduced in an earlier lesson. We know that every horse is faster than every dog. We know some greyhounds are faster than every rabbit. We know that greyhounds are dogs. And we know the relationship of being faster is transitive. We want to prove that horses are faster than rabbits. In order to do this, we're going to negate that desired conclusion. First, we convert the premises to clausal form, as shown here. Note the use of the Skolem constant Greg in the second and third clauses, which result from the existential quantifier in the second premise. And similarly, we can convert our negated goal to clausal form as well. Note that to deal with the negated universal quantifiers, we need to add some Skolem constants. In this case, we've chosen to use Harry and Ralph, our prototypical horse and rabbit, assuming that those constants are not already in the language. Okay, we write down our clauses and go to work. First, we resolve the clause on line 2 with the clause on line 4 to derive the fact that Greg is a dog. We resolve the clause on line 6 with the clause on line 1 to derive the clause on line 10. And we resolve these two results to derive the fact that Harry is faster than Greg. Next, we resolve the clause on line 7 with the clause on line 3 to derive the fact that Greg is faster than Ralph. At this point, all we need to do is use transitivity and we're done. We first resolve the clause on line 11 with the transitivity clause on line 5. And then we resolve the clause on line 12 with the result to derive that Harry is faster than Ralph. Finally, we resolve this result with the negated goal clause in line 8 to derive the empty clause. All right, this example shows that resolution is much more focused than Fitch. The added good news is that it's every bit as powerful. In fact, it's possible to derive a conclusion from a set of premises using resolution, if and only if it's possible to derive that conclusion using Fitch. In the segment on reasoning with resolution, we saw how to use resolution to answer true or false questions. For example, is art the grandparent of Co? In this segment, we're going to look at how to use resolution to answer fill-in-the-blanks questions, such as, who is the grandparent of Co? Or who are the grandchildren of art? Recall that our method for determining logical entailment is to negate the conclusion, convert to causal form, and try to derive the empty clause. Here's an example. Given P of x implies Q of x, given P of A, we can prove there exists a Z such that Q of Z. The clauses corresponding to our premises are shown here on lines 1 and 2, and the clause for a negated goal is shown here on line 3. Starting from these clauses, we can quickly derive the empty clause as shown on lines 4 and 5. Okay, now let's take this basic method and modify it just slightly. Instead of adding the negated goal phi to our premise set, we add a sentence of the form phi implies goal. To do, we're saying that if phi is true, then the conclusion goal is true. Having done that, we convert to causal form and we apply resolution. However, instead of trying to derive the empty clause, we try to derive a clause that contains just the literal goal. Now this is equivalent to what we were doing before, because phi implies goal is logically the same as not phi or goal. And so we just have a goal literal tacked onto each one of our clauses. Here's an example. We have the same premises as before, but instead of the negated goal, we have a clause for the negated goal with the goal condition appended. Same resolutions steps apply, and we end up with a clause containing goal. It's easy to see that for any derivation of the empty clause from a set of consistent premises and a negated goal, there's a derivation of a goal clause from the premises and our goal implication. In fact, the proof steps are one-to-one equivalent. So why are we doing this? Okay, the reason is that a simple extension of this method allows us to extract answers from our proofs. Suppose we have a sentence with some free variables, nu1 through nu(n), and we want terms such that when we substitute those terms for the variables, the goal sentence is true. If we modify our method just a little bit more, we can get resolution to give us these answers. Given a goal phi with free variables nu1 through nu(n), we add the goal sentence, phi implies goal of nu1 through nu(n) to our premise set, and try to derive a clause containing just goal literals. If we manage to do this, then the arguments to the goal literal are the answers to our original question. By adding this new type of goal sentence to our premises, we're in effect saying that if anything satisfies our goal sentence, then it satisfies our goal. Okay, let's look at our example one more time. Except at this time, let's suppose that our goal is not just to prove that there exists a z such that q of z is true. Let's suppose that we want to find a z such that q of z is true. So our goal in this case is the open sentence q of z. So as we see here on line 3, we write this as q of z implies goal of z. Okay, we then execute the same steps as before. This time, because we include the variable z in the goal literal, it gets replaced by a on line 5, effectively giving us our answer. Nifty. All right, let's look at a slightly more interesting example. In this case, everything's the same except that we have two p-facts in our premise set. Our goal is the same as before. This time we do the resolution and keep on going. We see that we produce our answer from the last time, but we also get an additional answer, namely b. In other words, we can use resolution as a generator for answers to our query. Okay, one more example. Suppose that instead of knowing P of A and P of B, all we knew was that at least one of those facts were true. would happen? Our disjunctive premise is shown here on line 2. The goal is the same. We start out as before by resolving our goal clause with a clause on line 1. Producing the result on line 4. Next, we resolve this result with a clause on line 2, resulting in the clause on line 5. Okay, now there's a non-goal literal in this result, so we can't just stop just yet. We want to stop only when we have clauses containing only goal literals. Fortunately, we can resolve, there are more resolutions we can do. In particular, we can resolve this result with a clause on line 2 once again. Sorry, do that with a clause on line 4, leading to the result on line 6. Now we have a clause containing just goal literals, and so we can stop. Okay, now let's take a look at this result. What exactly does it mean? Recall that a clause is an implicit disjunction. So from this result, we know that goal of A or goal of B. In other words, we know that one of the two answers is true, but we don't know which. It's not as good as knowing which one works. We know that at least one of them works. This method can be extended to produce other interesting results, such as conditional answers. For example, if the goal is true of all purple mushrooms and so forth. Induction is reasoning from the specific to the general. If we believe many instances of a schema, and we know of no counterexamples, then we're often tempted to conclude that the schema is true in general. Suppose we believe that a schema holds for every term in our language. For example, P of A implies Q of A, P of B implies Q of B, and so forth. Then we're entitled to conclude a universally quantified version of our schema. For example, for all x, P of x implies Q of x. Incomplete induction is induction where this set of instances is not complete. From a reasonable collection, we sometimes leap to a universal conclusion, even though we have not seen all instances. Consider, for example, the function shown here. F of 1 equals 1, and f of n plus 1 equals f of n plus 2n plus 1. If we look at some values of this function, we notice a certain regularity. The value of f always seems to be the square of its input. From this sample, we're tempted to leap to the conclusion that f of n equals n squared. It's a lucky guess. In this case, that conclusion happens to be true, and we can prove it. Here's another example. This one is due to the mathematician Herbrand. He looked at various values of the expression 2 to the 2 to the n plus 1 for various values of n, and noticed that they were all prime. So he concluded, or at least conjectured, that the value of the expression was a prime number. Unfortunately, this was not a lucky guess. His conjecture was ultimately disproved, and in fact it was disproved of the very next number in the sequence. He just didn't have the computing capacity to realize it. For us, this is not so good. In logic, we're concerned with logical entailment. We want to derive only conclusions that are guaranteed to be true when the premises are true. Guesses like these can be useful in suggesting possible conclusions, but they're not themselves proofs. In order to be absolutely sure of universally quantified conclusions, we have to be sure that all instances are true. This is called complete induction. The techniques for complete induction vary with the structure of the language to which it's applied. We begin this lesson with a discussion of domain closure, a rule that applies when the Herbrand base of a language is finite. We then move on to linear induction, that is the special case where the ground terms in a language form a linear sequence. After that, we look at tree induction, the special case in which the ground terms of the language form a tree. And finally, we look at structural induction, which applies to all languages. Induction for finite languages is trivial. We simply use the domain closure rule of inference. For a language with object constants sigma 1 through sigma n, the rule is written as shown here. If we believe a schema is true for every instance, then we can infer a universally quantified version of that schema. Suppose, for example, we have a language with just 4 object constants and no function constants. Then we could write a domain closure as shown here. If a schema is true of A and B and C and D, then it's true of everything. The trivial proof shown here shows how we can use this rule to derive an inductive conclusion. Suppose we have the ground implications shown on premises on lines 1 through 4. Using our domain closure rule, we can then derive the inductive conclusion: for all x, p of x implies q of x. For finite languages, domain closure is really all we need. Unfortunately, this technique does not work well when there are infinitely many ground terms. In that case, we could write a domain closure rule analogous to the one we just saw. And the rule would be sound in the sense that the conclusion is logically entailed by the premises of the rule. However, it would not help us produce a proof of the conclusion. To use a rule, we need to prove all of the rule's premises. When there are infinitely many premises, we cannot do this in a finite amount of time, and so there's no possibility of a finite proof. All is not lost. It's possible to write rules that cover all instances without explicitly enumerating them. The trick is to use the structure of the terms in a language. In the following sections, we'll talk about how this is done for languages with a variety of different structures. Consider a language with a single object constant A and a single unary function constant S. There are infinitely many ground terms in this language, arranged in what resembles a straight line. Starting from the object constant, we move to a term in which we apply the function constant to that constant, then to a term in which we apply the function constant to that compound term, and so forth. In this section, we concentrate on languages that have linear structure of this sort. Hereafter, we call these linear languages. In all such languages, there's a single object constant and a single unary function constant. In talking about a linear language, we call the object constant the base element of the language, and we call the unary function constant the successor function. Although there are infinitely many ground terms in any linear language, we can still generate finite proofs that are guaranteed to be correct. The trick is to use the structure of the terms in language in expressing the premises of an inductive rule of inference known as linear induction. In general, if we know that a schema holds of our base element, and if we know that whenever the schema holds of an arbitrary element, it also holds of the successor of that element, then we can conclude that the schema holds of all elements. A bit of terminology here before we go on. The first premise in this rule is called the base case of the induction because it refers to the base element of the language. The second premise is called the inductive case. The antecedent of the inductive case is called the inductive hypothesis, and the consequent is called, not surprisingly, the inductive conclusion. And finally, the conclusion of the rule as a whole is sometimes called the overall conclusion to distinguish it from the inductive conclusion. In order to understand the intuition behind linear induction, imagine an infinite set of dominoes placed in a line so that when one falls, the next domino in the line also falls. If the first domino falls, then the second domino falls. If the second domino falls, then the third domino falls, and so forth. By continuing this chain of reasoning, it's easy for us to convince ourselves that every domino eventually falls. Now let's formalize this example and prove the result using induction. Let A represent the first domino, and let S represent the relationship between a domino and its successor in the line. Let's use the unary relation constant falls to express the fact that the domino given as argument eventually falls. Here are our axioms. We assume that the first domino falls, and we know that whenever any domino falls, its successor falls. Our goal is to prove that all of the dominoes fall. Here's a one-step proof of that conclusion. We start with the premise that the first domino in line falls. We also have the premise that the dominoes are so placed such that each domino knocks over the next domino. The nice thing is that these two sentences match the premises of the linear induction rule directly, and so we can derive the conclusion in just one step. Okay, here's a more interesting example. Recall the formalization of arithmetic introduced earlier in the course. Using the object constant 0 and the unary function constant s, we can represent each number n by applying the function constant to 0 exactly n times. Let's assume we also have a single ternary relation constant plus to represent the addition table. The axioms shown here describe plus in terms of 0 and s. The first sentence here says that adding 0 to any element produces that element. The second sentence says that adding the successor of a number to another number yields the successor of their sum. It's easy to see that any table that satisfies these axioms includes all of the usual addition facts. The first axiom ensures that all cases with 0 as first argument are included. From this fact and the second axiom, we can see that all cases with s of 0 or 1 are also included, and so forth. Now, in order for our definition to be a complete definition, we also need an axiom limiting the value of plus, the third argument that is, to a single value for each pair of inputs, which are its first two arguments. However, we do not need that axiom for the purposes of this example, and so for the sake of simplicity, we'll skip it. The first axiom here tells us that 0 is a left identity for addition. 0 added to any number produces the number of results. As it turns out, given these definitions, 0 must also be a right identity. That is, it must be the case that for all x plus x0 is x. Let's prove this. As usual, we'll start with our premises, the left identity rule, and the other rule defining plus. We use universal elimination in the first premise to derive the sentence on line 3. Plus of 0 and 0 is 0. All right. This takes care of the base case of our induction. We then start a subproof and assume the antecedent of the inductive case, plus of x0, x. We then use 3 applications of universal elimination on the second premise to get the sentence on line 5. We can then use implication elimination on this sentence and our assumption to derive the conclusion on line 6. We then discharge our assumption and our subproof and form the implication shown on line 7. X plus 0 equals x implies that s of x plus 0 equals s of x. We universalize this to get to the result on line 8. And finally, we can use linear induction to derive our overall conclusion, the sentence shown here on line 9. For all x, x plus 0 equals x. Tree languages are a superset of linear languages. While in linear languages, the ground terms of a language form a linear sequence, in tree languages, not surprisingly, the terms form something that's more tree-like. Consider a language with an object constant a and 2 unary function constants, f and g. Some of the terms in the language are shown here. At the top of the tree, we have our object constant a. To the left, f of a. To the right, g of a. Applying f to f of a, we get f of a. Applying g to f of a, we get g of f of a, and so forth. As with linear languages, we can write an inductive rule of inference for tree languages. The tree induction rule of inference for the language just described is shown here. Suppose we know that a schema phi holds of a. Suppose we know that whenever the schema holds of any element, it holds the term formed by applying f to that element. And suppose we know that whenever the schema holds of any element, it holds of the term formed by applying g to that element. Then, since we've covered all of the possible terms in the language, we can conclude that the schema holds of every element. In order to see an example of tree induction in action, consider the ancestry tree for a particular animal, say a dog. We use the object constant rex to refer to the dog. We use the unary function constant f to refer to the father of the dog, and we use G to refer to the mother of the dog. Finally, let's say we have a single unary relation constant P. That's true of a dog if and only if it's purebred. Now we write down the fundamental rule of dog breeding. We say that a dog is purebred if and only if both its father and its mother are purebred. All right, this is a bit oversimplified on several grounds. Properly, the father and the mother should be of exactly the same breed. Also, this formalization suggests that every dog has an ancestry tree that stretches back without end. However, let's ignore these imperfections for the purposes of our example. Suppose now that we discover that our dog Rex is purebred. This gives us an additional axiom, and given this information, we know that every dog in Rex's ancestry tree must be purebred as well. We can prove this with a simple application of tree induction. Here's a proof of our conclusion. We start with the premise that Rex is purebred. We also have our constraint on purebred animals. First, we use universal elimination to instantiate the second premise, and then we use biconditional elimination on the biconditional on line 3 to produce the implication on line 4. On line 5, we'll start a subproof with the assumption that X is purebred. Now we can use implication elimination on our assumption and the implication on line 4 to produce the conclusion on line 6. And we can use AND elimination to pick out the first conjunct. We then use implication introduction to discharge our assumption, generate an appropriate implication, and use universal introduction to universalize the result. So much for the F case. What about the G case? We still have to prove that it's true for the G case. Well, we can repeat the process almost exactly with just G in place of F and produce a similar result, here shown on line 14. Finally, we can use the tree induction rule on the sentences in line 1, the base case, line 9, the inductive case for F, and line 14, the inductive case for G, and thereby derive our desired overall conclusion. Structural induction is the most general form of induction. Structural induction, we can have multiple object constants, multiple function constants, and we can even have function constants that have multiple arguments. Consider a language with two object constants a and b, and to start, a single binary function constant c. Here we see a list of some of the terms of the language. There's no graphical rendering in this case, as the structure is quite complicated. The structural induction rule for this language is shown here. If we know that phi holds of our base elements, and we know that whenever phi holds of any two elements, it holds of their combination, then we can conclude that phi holds of everything. In order to visualize a world where structural induction is appropriate, let's transport ourselves to a primitive chemistry laboratory. In the lab, we have two liquids, and we have enough equipment to combine the liquids in various ways, to combine the combinations with each other, and to combine those combinations with yet other combinations, and so forth. Back in logic land, our goal is to prove things about the acidity of the combinations we can create in the laboratory. Let's use the object constant 1 to represent one liquid. Let's use 2 to represent a second liquid. Let the binary function constant c represent the result of combining two liquids designated by its arguments. Finally, let's use the unary relation constant a to express the fact that a liquid is acid. Let's use n to express the fact that a liquid is neutral. And let's use b to express the fact that a liquid is a base. Now for our premises. We know that mixing two acids yields an acid. We know that mixing an acid and a neutral liquid yields an acid, and vice versa. We know that mixing two neutral liquids yields a neutral result. We know that mixing a base and a neutral liquid yields a base, and vice versa. And we know that mixing two bases yields a base. It's unclear what happens when we mix acids and bases because it depends on the concentrations, so we don't have a rule for that case. As a simple example of structural induction action, let's prove that if both of our liquids are acids, then every combination is an acid as well. In other words, given acid of 1 and acid of 2, we want to prove that for all x, acid of x. The proof in this case is trivial. We have our specified facts about A and B, and we have our general fact about the combination of two acids. These three items happen to match the premises of the structural induction rule precisely, and so we can derive our conclusion in one step. Okay, but now let's see what happens when one of our liquids is an acid and the other is a neutral liquid. Clearly, we can now have pure acids. We can also have combinations that are pure neutral, or we can have any mix of the two. The result is guaranteed to be either an acid or neutral, but that's all we can say. In other words, if we know that liquid 1 is an acid and liquid 2 is neutral, then the best we can do is to prove for all x, A of x or N of x. As with our last example, we can prove this result using structural induction. The proof in this case, however, is a lot messier. However, I think it's worth looking at as it suggests the sort of complexity that's involved in doing inductive proofs with disjunctive conclusions, as in this case. There are 44 steps in this proof, but we'll skip over a lot of the details and just look at the basic structure of the proof. As usual, we start with our premises, the facts about the two liquids, as well as the general facts about our combinations of acids and neutrals. We could include all the facts about combinations, including the rules about bases, but since there are no bases, we can just omit those from the proof. As before, we deal with the base cases first. We use or introduction to disjoin our first two premises with other sentences so that the resulting disjunctions match the first two premises of structural induction for our desired disjunctive result. Here on line 7, we disjoin our premise that liquid 1 is an acid with the sentence N of 1. And on line 8, we disjoin A of 2 with our premise that liquid 2 is neutral. Now we prove the inductive case. To this end, we start a new proof and assume the inductive hypothesis. Our plan here is to generate our inductive conclusion from this assumption. The full details are in the notes. Suffice it to say that after 40-odd steps, we end up with the conclusion shown here. We know that the combination of x and y is either an acid or neutral under the assumption on line 9. We then can use implication introduction to generate the implication on line 42. And we can use two applications of universal introduction to generate the conclusion on line 43. Now we have everything we need. We can put all of the pieces together, the two base cases on lines 7 and 8, and this inductive case on line 43, and we can apply structural induction to produce the desired overall conclusion. Although our proof here is messier than in the last case, the basic inductive structure is pretty much the same. Importantly, using structural induction, we can prove conclusions that would not be possible otherwise. It's induction in any of these forms, linear, tree, structural, is an extremely powerful proof method, and one that we should all master even when it gets messy. In our discussion of Herbrand logic, we assume that there is a one-to-one relationship between ground terms in our language and objects in the application area we're trying to describe. For example, we assumed a unique name for each person. In arithmetic, we often assume a unique term for each number. This is often called an isomorphic representation because there is a one-to-one relationship from the ground terms in our language onto objects in the world. This makes things conceptually simple, and it's a reasonable way to go in many circumstances, but not always. In natural language, we often find it convenient to use more than one term to refer to the same real-world object. For example, we sometimes have multiple names for the same person, like Michael and Mike. And in elementary arithmetic, we frequently use different terms to refer to the same number. 2 plus 2, 2 times 2, s of s of s of s of 0, and so forth. The reverse is also true. We sometimes find that there are objects in an application area for which we have no names at all. For example, we have names for many real numbers, integers, decimal numbers, and some transcendental numbers like pi and e. However, we do not have names for all of them because we have only countably many names and uncountably many numbers. Herbrand semantics is also problematic when we want to define functions and relations in a general way that applies to worlds with differing numbers of objects. For example, we might want to state the fact that addition is commutative, whether we're considering finite arithmetic, arithmetic over the natural numbers, or arithmetic over the real numbers. Unfortunately, we cannot do this in Herbrand logic since it requires that we fix the language and therefore the number of objects in advance. First-order logic is an extension to Herbrand logic that deals with these problems. In many ways, it's similar to Herbrand logic. The syntax of the two languages is almost identical, and the proof method is almost the same. The main difference is in the semantics. We start this lesson by introducing the idea of a conceptualization. It's a mathematical structure consisting of a language-independent universe of objects, together with functions and relations on that universe. Then we define a semantics that gives meaning to sentences without fixing in advance the universe of objects. We present a selection of examples. We develop a proof system for first-order logic. And finally, we present some sample proofs. As we shall see, the semantics of first-order logic is based on the notion of a conceptualization of an application area in terms of objects, relations, and functions. The notion of an object is quite broad. Objects can be concrete, for example, the Eiffel Tower, Confucius, the sun, or they can be abstract, like the number 1, 2, 3, 4, the set of all integers, the concept of justice. Objects can be primitive or composite, for example, a circuit that consists of many subcircuits. Objects can even be fictional, such as a unicorn or Sherlock Holmes. In short, an object can be anything about which we want to say something. Not all knowledge representation tasks require that we consider all possible objects. In some cases, only those objects in a particular set are relevant. For example, number theorists usually are only concerned with the properties of numbers and are usually not concerned with physical objects, such as resistors and transistors. Electrical engineers usually are concerned with resistors and transistors and usually are not concerned with buildings and bridges. The set of objects about which knowledge is being expressed is often called a universe of discourse. Note that although in many real-world applications there are only finitely many elements in a universe of discourse, this need not always be the case. It's common in mathematics, for example, to consider the set of all integers, or the set of all real numbers, or the set of all n tuples of real numbers, as universes with infinitely many objects. Given a universe of discourse, a relation is a set of n tuples of objects in the universe of discourse, each set of which manifests a particular property or relationship. Suppose, for example, that we had a universe of discourse consisting of the numbers 1, 2, and 3. In this case, there are 9 pairs of numbers. Any subset of these pairs constitutes a binary relation. First, for example, here we have the less than relation. Second, we have some other random relation. We have the relation that's true of all combinations of objects. And we have the relation that's true of no combinations of objects. One thing that our definition for relations makes clear is that for a finite universe of discourse, there's an upper bound on the number of possible n-ary relations. In general, for a universal discourse of size b, there are b to the n distinct n tuples. Every n-ary relation is a subset of these b to the n tuples. Therefore, an n-ary relation must be one of at most 2 to the b to the n possible sets. Sometimes in thinking about relations, it's helpful to visualize the tuples in different ways. For example, we can think of a relation as a table in which each row represents a distinct tuple. Alternatively, we can think about a relation as a graph in which the nodes represent objects and arcs represent tuples of objects. The notion of relation is an abstract one, not a particular encoding, and we can use whatever encoding makes most sense. Before moving on to functions, it's worthwhile for us to agree on some basic terminology. First of all, there's the notion of arity. The arity of a relation is the number of objects in each tuple in the relation. A relation of arity 1 has just one object per tuple. It's said to be unary. A binary relation has 2 objects per tuple. A ternary relation has 3 objects per tuple, and so forth. Every relation also has a cardinality. The cardinality of a relation is the number of tuples in the set. For example, the first relation shown here has cardinality 2, but arity 1. The second relation has arity 2, but cardinality 6. And the third has cardinality 3 and arity 3. A function is a special kind of relation among the objects in a universal discourse. For each combination of n objects, called the arguments, a function associates a single object called the value. Note that there must be one and only one value for each combination of arguments. Functions that are not defined for all combinations of arguments are often called partial functions. And functions for which there can be more than one value for a given combination of arguments are often called multi-valued functions. By and large, we ignore partial and multi-valued functions throughout this course. Mathematically, a function can be viewed as a set of tuples of objects, one for each combination of possible arguments, paired with the corresponding value. In other words, an n-ary function is a special case of an n+1-ary relation. For example, consider the unary function shown here can be viewed as a binary relation shown in the middle. In what follows, to emphasize special property functions, we use a slight variation in our usual notation for relations, namely the use of an arrow in each tuple to emphasize the fact that the last element is the value of the function applied to the elements or elements before the arrow. Now, while every n-ary function can be viewed as an n+1-ary relation, we can see this, but not every n+1-ary relation is an n-ary function. We can see this by counting functions and comparing to relations. In general, for a universal discourse of size b, there are b to the n distinct n tuples, and every one of these must assume one of b values. Hence, there are b to the n possible functions. By contrast, there are 2 to the b to the n+1-ary relations. In the case of a universe of size 4, there are 65,536 relations, but only 256 distinct functions. The syntax of first-order logic is almost identical to that of Herbrand logic. Every syntactically legal sentence in Herbrand logic is a syntactically legal sentence in first-order logic. The only difference is that first-order logic has one additional type of sentence. An equation is an expression of the form sigma equals tau, where sigma and tau are terms in our language. An equation is a way of stating that two similar, the same, or possibly distinct terms refer to the same object. For example, to express the coreferentiality of +2, 2, and 4, we write +2, 2 equals 4. We can also distinguish terms by writing negated equations. To say that +2, 3, and 4 refer to different objects, we write not +2, 3 equals 4, which we sometimes abbreviate as plus 2, 3 is not equal to 4. In what follows, it's useful to treat equations as atomic sentences. In Herbrand logic, the only atomic sentences are relational sentences. The notions are identical. In first-order logic, we have two types of atomic sentences, relational sentences and equations. Other than this one small change, the languages of Herbrand logic and first-order logic are the same. The real difference between the two logics is a semantic one. In first-order logic, object constants refer to objects in some application area. Function constants refer to functions on these objects, and relation constants refer to relations. Such interpretations are used in defining the truth or falsity of first-order language sentences. This notion of interpretation is the source of much of the expressive power of first-order logic. Unfortunately, with this power comes somewhat greater complexity, as we shall see. The key notion, again, in first-order logic semantics is that of interpretation. An interpretation is a universe of discourse, let's call it U, together with a mapping from constants of the language into the elements of U, functions on U, and relations on U. Here's that same definition stated a little more precisely. The universe of discourse of an interpretation, I, written here as I enclosed in vertical bars, is an arbitrary set of objects. Again, let's call it U. Each object constant A in our language is mapped into an element of U. Each function constant F with arity n is mapped into an n-ary function on U. Each relation constant R with arity n is mapped into an n-ary relation on U. For example, here's an interpretation for a first-order logic language with object constants A, B, and C, with unary function constant F, and with unary function constant relation constant P, binary relation constant Q, and ternary relation constant R. Our universe of discourse in this case is a set consisting of the numbers 1, 2, and 3. Our interpretation maps A to 1, B to 2, and C to 2. It maps F to a function that gives one and only one value for each element in the universe of discourse. 1 is mapped to 2, 2 is mapped to 3, and 3 is mapped to 3. And the interpretation maps P, Q, and R to relations of the appropriate arity. Note that more than one object constant can refer to the same object. In this case, B and C refer to the number 2. Also, not every object in universe course need have a constant that refers to it. For example, there's no object constant that denotes the number 3. The function f assigns one and only one value to every number in the universe of discourse. By contrast, in the relations, some objects are paired with other objects, whereas some objects do not appear at all. A variable assignment is for variables what an interpretation is for object constants. Given a universe of discourse U, a variable assignment is an arbitrary mapping from the variables of the language into U. A value assignment based on an interpretation I and a variable assignment V is a mapping from all of the terms of the language into the universe of discourse. The mapping must agree with I on constants. It must agree with V on variables. And the value of a functional term is the result of applying the function corresponding to the function constant to the objects designated by the terms. Let's see an example. Given the interpretation of variable assignment shown here at the top, we have the following value assignments. The value assignment of the constant A is 1, because that's the value under the interpretation I. The value assignment of the variable Z is 2, because that's the value under the variable assignment V. The value assignment of the term f of A is 2, because that is the value of the function f applied to the value assignment of A. Remember, A has value 1, and looking in the interpretation of f, we see that 1 has value 2. Hence, the value of f of A is 2. And finally, the value assignment of the term f of z is 1, because that's the value of the function applied to the value assignment of z. The truth assignment based on interpretation I and variable assignment V is the mapping from the sentences of the language to true or false. The details depend on the type of sentence involved. Given an interpretation I and a variable assignment V, a relational sentence is true if and only if the tuple of objects denoted by the arguments is contained in a relation denoted by the relation constant. For example, given the interpretation and variable assignments we saw earlier, we have the truth assignments shown here. The relational sentence R of AB is true because the tuple consisting of 1 and 2 is a member of the relation assigned to the relation constant R. And the sentence R of ZA is false since 2, 1 is not in R. Given an interpretation I and a variable assignment V, an equation sigma equals tau is true if and only if the object denoted by sigma is the same as the object denoted by tau. If and only if the semantic value of sigma is identical to the semantic value of tau. For example, given the interpretation of variable assignment shown here, we can see that the object constant A and the term f of b have the same value assignment, and hence the equation f of A equals f of b is true. Conversely, A and f of x have different values, and hence the equation A equals f of x is false. The conditions for truth of logical sentences in first-order logic are analogous to those for the truth of logical sentences in propositional logic and Herbrand logic. A negation not phi is true if and only if phi is false. A conjunction phi and psi is true if and only if both phi and psi are true. A disjunction phi or psi is true if and only if phi is true or psi is true, or both. And an implication is true unless the antecedent is true and the consequent is false. And equivalence is true if and only if the truth value of the two embedded sentences are the same. Now on to quantified sentences. Intuitively, a universally quantified sentence is satisfied if and only if the embedded sentence is satisfied for all values of the quantified variable. And intuitively, an existentially quantified sentence is satisfied if and only if the embedded sentence is satisfied for some values of the quantified variable. Sadly, expressing this intuition, at least expressing it rigorously, is a little bit tricky. And in order to do so, we need the notion of a version of a variable assignment. Then we can give a rigorous definition of intuition by talking about some variations or all variations of a given variable assignment. A version, often written of a variable assignment V, often written V where omega is replaced by x, or V omega gets x, is the variable assignment that agrees with V on all variables except omega, which is assigned the value x in the version. So V of omega give x applied to an arbitrary variable theta is going to equal x if theta and omega are the same, and V omega gets x applied to theta is going to be V of theta if theta and omega are different. Okay, here's some examples. Let's take the variable assignment shown here in the upper right. All of the variable assignments at the bottom are versions of this variable assignment. In the first, we assign x to 1. In the second, we assigned x to 2. In the one on the lower left, we assign y to 1. And in the one on the lower right, we assigned y to 2. And these assignments, these versions, overwrite whatever was in V in the original variable assignment. Okay, now, with this notation, we can finally formalize the semantics of quantified sentences. An interpretation I and a variable assignment V satisfy a universally quantified sentence for all new phi, if and only if I and V satisfy phi for all versions of V that can be defined over the universe of discourse of I. And an interpretation I and a variable assignment V satisfy an existentially quantified sentence, there exists a new phi, if and only if I and V satisfy phi for at least one version of V that can be defined over the universe of I. Okay, here are some examples. Consider the sentence for all x r of xx. This is true under the interpretation of variable assignment shown if and only if the scope is true for all versions of the variable assignment. While it's true for the second version, it is not true for the first version, and so the sentence as a whole is false. By contrast, since the scope is true for at least one version of the variable assignment, the interpretation of variable assignments satisfy the existentially quantified sentence shown on the right. When quantifiers are nested, this computation becomes messier, but the definitions still work. Here you see a couple of examples. Now, I'm not going to read through the examples. However, I recommend that you pause the video here and study these examples till you're comfortable with the answers. Now, if you think this is complicated, you're not alone. Students seeing the semantics of first-order logic for the first time are often bewildered. The intuition behind the semantics is simple enough, but the details are really complex. Much more so than for Herbrand logic. To see this, compare the semantics of universally quantified sentence in the two logics. In first-order logic, we say that a universally quantified sentence is true in an interpretation and a variable assignment if and only if the scope is true for the interpretation and every version of the variable assignment compatible with the interpretation. It's quite a mouthful. In Herbrand logic, we say that a universally quantified sentence is true in a truth assignment if and only if every instance of the scope is true. Herbrand logic definition is simpler, and for many people it's more intuitive as well. We'll talk more about this in a later segment. Let's look at a few definitions and some observations before we close out this segment. An interpretation I and a variable assignment V are said to satisfy a sentence if and only if the sentence is true according to the rules we've just seen. An interpretation of a sentence is said to be a model if and only if it satisfies the sentence for every compatible variable assignment. So models are special cases of interpretations. Remember that an occurrence of a variable V is free if and only if it does not lie in the scope of any quantifier, and a closed sentence is a sentence with no free occurrences of variables, otherwise the sentence is said to be open. Now let's use these two concepts in a couple of observations. If an interpretation satisfies a closed sentence for one variable assignment, then it satisfies the sentence for every variable assignment. In other words, it's a model of that sentence. You should think about this to convince yourself that it's always true. And here's a second observation. An interpretation is a model of an open sentence if and only if it's a model of that sentence obtained by universally quantifying all of the free variables in the sentence. Again, think about this to convince yourself that it's true. Let's revisit the blocks world introduced earlier in the course. This time around, let's say we have a vocabulary with 6 object constants, namely A, B, C, D, E, and F. Now let's assume that we have just one binary relation constant, namely on. Now let's consider the ground literals shown here. As before, the positive literals are shown in black and the negative literals are shown in gray in order to distinguish the two more easily. Notice that we have A on B and B on C, and we have D on E and E on F. Everything else is false. In Herbrand logic, a set of 6 object constants fixes a universe of 6 objects. As a result, the set of sentences shown here completely defines the on relation. That is exactly one Herbrand logic truth assignment for our language that satisfies our sentences. By contrast, in first-order logic, the set of 6 object constants are simply 6 names that refer to objects in some universe, but not by themselves constrain the universe in any way. As a result, in first-order logic, the set of sentences is satisfied by more than one interpretation. That is, the set of sentences accurately describes more than one arrangement of blocks and does not really specify which one. Let's look at some examples of interpretations for this language. Here's an interpretation I that satisfies our sentences. The universe consists of 6 blocks, denoted here by 6 capital letters. Each of our object constants refers to a distinct block. Constant A refers to a block named A. Constant B refers to a block labeled B, and so forth. The relation constant on refers to a set of two tuples of blocks. Of course, there's nothing requiring that the objects be named in this fashion. The constants could refer to different blocks, as in the interpretation shown here. In this case, the object constant A refers to the block labeled F. The object constant B refers to the block labeled E. Although the interpretations of the object constants are different, the sentences still hold because the interpretation of the relation constant on is also different in a consistent way. Here's a more interesting example. In first-order logic, there need not be a one-to-one relationship between object constants and objects in the universe of discourse. Some objects can have more than one name. Some objects might have no names at all. Interpretation shown here illustrates this. There are just 4 blocks in this case. Object constant A refers to the same object as object constant D. B refers to the same object as E, and C refers to the same object as F. Moreover, there's a block with no name whatsoever. This interpretation is an example of an interpretation that does not satisfy our sentences. In this case, the interpretation fails because the block named A is not on the block named B, and so the sentence on AB is false. And here's an interpretation that also does not satisfy our sentences. In this case, the interpretation fails because the block named C is on a block named D, and so the sentence not on CD is false. Well, there are many different implementations that satisfy our original sentences. In a sense, they all have the same structure. In every block's world interpretation, there's at least one stack of 3 blocks resting directly on the table. In some interpretations, it can be multiple stacks, as illustrated earlier, and there can be other arrangements. However, to satisfy these sentences, an interpretation must ensure that there is at least one stack of 3 blocks somewhere in the scene. And before leaving this example, it's worth noting that first-order logic is even more abstract than these examples might suggest. In particular, there's nothing requiring that the objects in the universe be blocks. They could equally well be natural numbers or people or buildings. All that's required is that the on relation among these objects have the equivalent of a stack of 3 blocks. Consider the language with object constant 0, function constant s, and the relation constant plus. This is basically the same signature we used in our look at Peano Arithmetic in the lesson on Herbrand Logic. The main difference is that we've dropped the binary relation same, since in first-order logic we can use equality in its place. Here we have the sentences we used to describe the properties of addition, except that the same relation is replaced with equality. We have the identity axiom, adding 0 to any number yields that number. There is the successor axiom, if x plus y is z, then the successor of x added to y yields the successor of z. Finally, there's the functionality axiom. For any x and y, there's just one sum. In our discussion of Herbrand logic, we saw that for our language, there's only one truth assignment that satisfies this set of sentences. By contrast, in first-order logic, there are many interpretations that satisfy these axioms. Let's look at a few of them. First of all, there's modular arithmetic with modulus 2. The universe of discourse consists of just the two numbers 0 and 1. 0 maps to itself, and s maps back and forth between 0 and 1. And plus has the extension shown here. It's easy to see that this interpretation satisfies all 3 of our axioms. 0 added to any number results in that number. If x plus y is z, then the successor of x added to y yields the successor of z. For example, 0 added to 0 is 0, and 1 added to 0 is 1. And finally, the relation is functional. Each combination of 0 and 1 has just one value. Modular arithmetic with modulus 3 also satisfies our axioms. Again, 0 added to any number results in that number. If x plus y is z, then the successor of x added to y yields the successor of z. 0 added to 0 is 0, 1 added to 0 is 1, and so forth. Finally, the relation is still functional. Similarly, the axioms are satisfied by addition over the natural numbers. And they're also satisfied by this non-standard arithmetic over two numbers where 1 plus 1 equals 1. Here's an example of an interpretation that does not satisfy our sentences. This is the same as the interpretation for arithmetic with modulus 2, except that the tuple 0, 0, 0 is missing. And the interpretation consequently fails to satisfy our sentences because the sentence for all y plus 0y is false. And this interpretation is another non-example. It's the same as arithmetic, again, with modulus 2 once again, except that it has an additional tuple. And so it does not satisfy our functionality axiom. Although the semantics of first-order logic and Herbrand logic are different, many of the key concepts of the two logics are the same. Notable among these are the concepts of validity, contingency, unsatisfiability, and so forth. Turns out they have the same definitions in Herbrand logic as in first-order logic. Sentence is valid if and only if it is satisfied by every interpretation. Sentence is unsatisfiable if and only if it is not satisfied by any interpretation. And a sentence is contingent if and only if it is neither valid nor unsatisfiable. That is, there's some interpretation that makes it true and some interpretation that makes it false. A sentence is satisfiable if and only if it's either valid or contingent, and a sentence is falsifiable if and only if it is either contingent or unsatisfiable. And guess what? That's it for this segment. Shortest segment of the course, just those few definitions. The set of first-order logic sentences logically entails a sentence if and only if every interpretation that satisfies the set of sentences also satisfies the individual sentence. As with validity and contingency and unsatisfiability, this definition is essentially the same for first-order logic as it is for propositional logic and Herbrand logic. From this definition of logical entailment, it's easy to see that whenever a sentence is entailed under first-order logic, it's also entailed under Herbrand logic. That is, Herbrand logic is more powerful than first-order logic. We can capture this notion with a theorem. Given a set of equality-free sentences, sigma, and an equality-free sentence, phi, if sigma logically entails phi under first-order logic, then sigma logically entails phi under Herbrand logic. By the way, a similar result holds for sentences with equality, but we have to extend Herbrand logic to incorporate an equality predicate of some sort, as we did with defining the same relation in a previous lesson. We also know that some sentences in Herbrand logic convey more information than in first-order logic, in the sense that the sentences admit fewer satisfying worlds and therefore entail more conclusions. Again, we have a theorem. There's a set of premises sigma and an equality-free sentence phi such that sigma logically entails phi under Herbrand logic, but for which it's not the case that sigma logically entails phi under first-order logic. Fitch system for first-order logic, or first-order Fitch, is similar to that for Herbrand logic. We have the same logical rules and the same rules for quantifiers. There are some new rules to handle equations, and some rules we must discard, namely domain closure and induction. In the Fitch system for first-order logic, we include all 10 of the rules of inference for propositional logic and the 10 logical rules for Herbrand logic. We have negation introduction and negation elimination, implication introduction and implication elimination, biconditional introduction and biconditional elimination, and we have introduction and elimination rules for conjunctions and disjunctions. We also include the 4 rules of inference for quantifiers from Herbrand logic. We have universal introduction and universal elimination, and we have existential introduction and existential elimination. Our first new rule of inference, the rule for equality, is called equality introduction, QI. According to this rule, we can write down any equation in which the first term and the second term are identical. For example, without any premises whatsoever, we can write down equations like a equals a, f of a equals f of a, and f of x equals f of x. Our second equality rule is equality elimination, or QE. Equality elimination tells us that when we have an equation and a sentence containing one or more occurrences of one of the terms in the equation, then we can deduce a version of the sentence in which that term has been replaced by the other term in the equation. In order to avoid unintended capture of variables, QE requires that the replacement must be substitutable for the term being replaced in the sentence. It's the same substitutability condition that adorns the universal elimination rule of inference. Note that the equation in the equality elimination rule can be used in either direction. That is, an occurrence of tau 1 can be replaced by tau 2, or an occurrence of tau 2 can be replaced by tau 1. For example, if we have the equation x equals b and the sentence hates of xx, we can infer hates of xb, we can infer hates of bx, or we can even infer hates of bb. And that's it for equality. To finish off the proof system, we need to deal with domain closure and induction. While these rules are sound for Herbrand logic, they are not sound for first-order logic. Simply guaranteeing that a sentence phi is true of every ground term does not necessarily mean that it is true of everything in the universe of discourse. Hence, these rules no longer work. The fix is simple. We just drop the two rules. No domain closure and no induction of any sort. Okay, that's it. To summarize, Fitch for first-order logic is similar to Fitch for Herbrand logic in that we include our logical rules of inference and our rules for quantifiers. There are just these two differences. We include two new rules for equality, and we eliminate our domain closure and induction rules. Okay, now let's see what we can say about this proof procedure. Remember that a proof system is sound if and only if every provable conclusion is logically entailed. In other words, if we can prove a sentence from a set of premises, then the set of premises logically entails the conclusion. And a proof system is complete if and only if every logical conclusion is provable. In other words, if a set of premises logically entails a conclusion, we can prove it. The nice feature of first-order logic is that the Fitch system is sound and complete for first-order logic. Logical entailment and provability are identical. An arbitrary set of sentences delta logically entails an arbitrary sentence phi if and only if phi is provable from delta using the Fitch system. By contrast, the Fitch system for Herbrand logic is not complete. However, this does not mean it's not powerful. In fact, the Fitch system for Herbrand logic is at least as powerful as the Fitch system for first-order logic. Given a set of equality-free premises and an equality-free conclusion, we know that if the conclusion can be proved from the premises in first-order logic, then it can also be proved from the premises in Herbrand logic. Moreover, the result holds in general when equality is replaced by an equality-like relation, such as the same relation that we saw in some of our examples. The fact that first-order Fitch is complete does not mean that it's more powerful than Herbrand Fitch. It's simply a result of the fact that first-order logic is not as strong as Herbrand logic. In this segment, we look at some first-order logic proofs involving equality. The results are simple and the proofs are short. However, they illustrate our two new rules of inference and a couple of important issues. Let's start with a particularly easy case. Suppose we know that b equals a and we know that b equals c. Our job is to prove that a equals c. The proof in this case is particularly simple. It's just one step. We start with the two premises and apply equality elimination to derive the desired conclusion. The rule is shown here at the bottom. In this case, we let tau 1 be b and tau 2 be a. Phi here is the second equation, namely b equals c. The result of this case is phi with tau 1 replaced by tau 2. In this case, it means that b is replaced by a. The result is the sentence on line 3, namely a equals c, which is what we set out to prove. Now let's look at an example that's just slightly more interesting. Suppose we believe that f of a equals b and f of b equals a. Let's prove that f of a equals a. Again, the proof can be done in just one step. In this case, we let tau1 be f of a and tau2 be b. Phi here is the second equation, namely f of b equals a. The result in this case is phi with tau1 replaced by tau2, or vice versa. This time we use the equation in the opposite direction, replacing a by f of b. The result is this sentence on line 3, namely f of a equals a, which is, again, what we set out to prove. Now let's look at an example that illustrates how equational reasoning interacts with relational reasoning. We know that Pat's the father of Quincy. We know that fathers are older than their children. Our job is to prove that Pat is older than Quincy. Proof goes as follows. As usual, we start with our premises. The father of Quincy is Pat, and fathers are older than their children. Next, we use universal elimination to instantiate our quantified sentence. The father of Quincy is older than Quincy. Finally, we use equality elimination to replace father of Quincy with Pat, and thereby derive the conclusion that Pat is older than Quincy. Finally, let's work through an example involving a disjunction of equations. We know that P of A is true and P of B is true. And suppose we know that A equals C or B equals C is true, but we're not sure which or whether both may be true. Our job is to prove that P equals C in any case. As always, we start with our premises, P of A, P of B, A equals C or B equals C. On line 4, we start a new subproof with the assumption that A equals C is true. From this assumption and our first premise, we conclude that P of C must be true. Now, although that is what we intended to do, we're not done since we have proved the result only under the assumption that A equals C. We make this clear with the use of implication introduction to derive the sentence A equals C implies P of C. Now we start another subproof, this time with the assumption B equals C. As before, we derive P of C. And from this, we derive the implication B equals C implies P equals C. Now we have both A equals C implies P of C and B equals C implies P of C. Finally, we use OR elimination to combine our two partial results with our disjunction of equations. And we're done. Consider a language with a binary function constant plus and a unary function relation constant even. In what follows, we use a little syntactic sugar to make our sentences look familiar. We write plus of xy in the more familiar notation, x plus y. Now consider the premises shown here. First of all, we require that our function plus be commutative and associative. Applying plus to two numbers produces the same result independent of the order of the arguments. Applying plus to x and the sum of y and z produce the same result as adding the sum of x and y to z. And finally, we define evenness. Now, we usually say that a number is even if and only if it's divisible by 2. However, we cannot use that definition here since we do not have multiplication and division in our language. But if we concentrate on integers, we can characterize the concept in an equivalent way by defining, saying that a number is even if and only if it is the sum of two identical numbers. Our job is to prove that in any arithmetic satisfying these properties, the sum of two even numbers is also even. The proof's a little lengthy, and rather than proceed linearly through it, let's look at the proof hierarchically. Here's an overall outline. As usual, we start with our premises: commutativity, associativity, evenness. We assume evenness of two. We then assume the evenness of two variables u and v, and we derive from this assumption that u is even and v is even. And from there, after a number of steps, we prove that u plus v is even. We'll look at the details of exactly how this is done in next slide. However, having proved this result, we use implication introduction and then two applications of universal introduction to derive our desired conclusion. Okay, now let's fill in that gap at step 7. We start with a conclusion that u is even and v is even. From these sentences and the definition of evenness, we know that there is a y such that y plus y is u. And we know there's a y such that y plus y is v. Note the values of y can be different in these two cases. After a few steps, we conclude that for all y, y plus y equals u implies that for all y, y plus y equals v implies even of u plus v. Again, we'll see the missing steps shortly. From the conclusions on lines 7.1 and 7.4, we can use existential elimination to conclude that for all y, y plus y equals v implies that u plus v is even. And from the conclusions on lines 7.2 and 7.5, we can again use existential elimination to conclude that u plus v is even. Okay, now we just need to fill in that gap at 7.3. Here's the proof. We assume that y1 plus y1 equals u, and we assume that y2 plus y2 equals v. These are just assumptions. We use equality elimination to add in the equation, that's equality introduction to add in the equation u plus v equals u plus v. We then proceed to conclude that u plus v is even in one final proof segment, which we'll see in a minute. And from that conclusion, we discharge our two assumptions and universally quantify the results to derive the conclusion needed for the outer proof that we just saw. Now, finally, all we need to do is to prove that u plus v is even, and we're done. Okay, here's the proof. We start with the equation u plus v equals u plus v. We substitute y1 plus y1 for u, from the first assumption we saw earlier, and we substitute y2 plus y2 for v, from the second assumption. We then reassociate this sum a couple of times. We commute the arguments, and we reassociate back again. This leaves us with a conclusion that y1 plus y2, when added to itself, is equal to u plus v. At this point, we can use existential introduction to derive the fact that there's a y that, when added to itself, gives u plus v. And finally, using the definition of evenness, we derive the fact that u plus v is even. Plugging this result into the previous proof and so forth gives us a complete proof for our overall result. The example is interesting in that it shows the derivation of a non-trivial result. It also illustrates the value of thinking about structure of proofs rather than treating them as linear sequences of deductions. Time for another field trip. Not a physical trip, but a virtual one. Rather than discussing new ideas in logic, we'll be instead looking at an application of the ideas we've already seen. The destination for our trip this time is the subfield of artificial intelligence called general game playing. As we shall see, GGP is an interesting application in its own right. It's intellectually engaging and, I think, more than a little fun. But it's more than that. It serves as an analog for applications of logic in other areas such as business and law and science and engineering. And more fundamentally, it raises questions about the nature of intelligence and serves as a laboratory in which to evaluate competing approaches to artificial intelligence. We'll return to these points a little later in the lesson. For now, let's just begin at the beginning. Playing strategy games like chess and checkers couples intellectual activity with competition. By playing games, we can exercise and improve our intellectual skills. The competition, that's excitement, allows us to compare our skills to those of others. The same motivation accounts for interest in computer game playing as a testbed for artificial intelligence. Programs that think better should be able to win more games, and so we can use competition as an evaluation technique for intelligent systems. Unfortunately, building programs to play specific games has limited value in AI. To begin with, specialized game players are very narrow. They can be good at one thing but not another. Deep Blue, for example, may have beaten the world chess champion, but has no clue at all how to play checkers. And it cannot even balance a checkbook. Second problem with specialized game playing systems is that they do only part of the work. Most of the interesting analysis and design is done in advance by their programmers. The systems themselves might just as well be teleoperated. Well, all's not lost. Many believe that the idea of game playing can be used to good effect to inspire and evaluate good work in artificial intelligence. But it requires moving more of the mental work to the computer itself. And this can be done by focusing our attention on general game playing. General game players are systems able to play arbitrary strategy games based solely on formal descriptions supplied at runtime. In a typical general game playing session, the players know nothing about the game in advance. Once the game begins, they receive a game description, and based solely on that description, they must figure out how to play the game legally and effectively. Furthermore, they must deal with uncertainty about the actions of the other players and resource bounds in the form of a game clock that limits their computation time. Unlike specialized game players, such as Deep Blue, general game players cannot rely on algorithms designed in advance for specific games. General game playing expertise must depend on intelligence on the part of the game player and not just intelligence of the programmer of the game player. In order to perform well, general game players must incorporate multiple artificial intelligence technologies such as knowledge representation, reasoning, learning, and rational decision making. Also, unlike specialized game players, general game players must be able to play different kinds of games. They should be able to play simple games like tic-tac-toe and complex games like chess. Games with simultaneous moves like diplomacy, and games with alternating play like Risk. Games with complete information or games with incomplete information, for example, Battleship. Games with different numbers of players, Block Swirled, Rubik's Cube, chess, Chinese checkers. Games with or without communication among the players, for example, Bughouse chess. Zero-sum games and cooperative games. The various aspects to general game playing, and we need to address them all in order to understand the field. In this lesson, we'll start by discussing game description. Here, as we shall see, logic plays a key role as a language for writing game rules. Next, we'll discuss game management, with a focus on use of technology to coordinate the play among automated game players and possibly humans. We then sketch the main techniques used in today's general game playing programs, and we'll look at some of the problems that have yet to be solved. Finally, we will close with some philosophical remarks about general game playing and an overview of the international general game playing competition. Before closing, however, there are a couple introductory words worth mentioning. General game playing resembles a couple of other disciplines. There are significant overlaps, but there are also some important differences. And it's worthwhile to keep these relationships in mind as we look at the details of general game playing. Like general game theory, traditional game theory is concerned with games in general. However, game theory is primarily concerned with the analysis of game trees. There's no concern for how these trees are communicated to the players or for how the descriptions are used. There's also little concern for trade-offs between deliberation and action. In general game playing, the game tree is communicated at runtime. Hence, there's an emphasis on description and use of this description. And by bringing game description into the picture, there's a possibility of more refined notions of rationality. General game playing also resembles the field of action planning. In fact, they're very closely related. The inputs are the same, a state machine with initial states and goal states. However, the purpose is slightly different. In the case of planning, the objective is to create a plan that transforms the initial state into a goal state. There's no execution environment and hence no concern for deliberation and action and interleaving of those activities. In general game playing, the objective is to actually get the world into the goal state, to actually execute the actions. The main difference is the presence in GGP of an execution environment that allows the general game player to execute its plan. As a result, players can interleave planning and execution. By so doing, they can sometimes solve problems that would be unsolvable by pre-planning alone, as we shall see. In general game playing, every game can be thought of as a state graph, like the one shown here. The nodes represent states, and the arcs represent actions. For example, if the player performs action A in state S1, the world goes into state S2. Action B leads to state S3, action C leads to state S4, and action D has no effect. In other words, the world stays in the same state. Start state is denoted by an incoming arrow. Here S1 is the start state. Goal states for the player are denoted by color. Here S8 and S11 are goal states for the player. More generally, in general game playing, we allow states with varying degrees of goalhood, ranging from 0 meaning bad to 100 meaning very good. Terminal states are denoted here by slightly heavier circles, barely visible. In this case, S3, S9, and S11 are terminal states. Beginning in the start state, the player's objective is to arrive at a terminal state that's also a goal state, or in the case of multiple levels of goals, to arrive at a terminal state that has as high a reward as possible. In the case of multiple players, with simultaneous moves, the arcs become multi-arcs, with one arc for each combination of the player's actions. Here's an example of a simultaneous move game with two players. If in state S1 both players perform action A, we follow the arc labeled AA. If the first player does A and the second player does B, we follow the arc AB. And similarly for BA and BB. We also have different goals for the different players, notated with different colors, here brown and purple. Multiplayer games are a little more difficult than single-player games since each player cannot control the other player's actions. So there's more search involved. Okay, that's pretty much it. Most pure strategy games can be conceptualized, can be thought of in this framework. Since all the state graphs that we're considering are finite, it is possible, at least in principle, to describe such games in the form of lists, states, actions, and tables that express legality, goals, update, and so forth. Unfortunately, direct representations are not practical in most cases. Even though the numbers of states and actions are finite, they can be extremely large. And the tables relating them can be even larger. For example, in chess, there are thousands of possible moves and more than 10 to the 30th states. In order to be practical, we need a somewhat more compact encoding. Okay, this is the job of the game description language, or GDL. GDL is a formal language for encoding finite discrete games. It supports compact representation of games by 1, relying on a conceptualization of game states as databases, and 2, using logic to define the notions of legality, update, goals, termination, and so forth. In the vast majority of games, states and actions have composite structure that allows us to define a large number of states and actions in terms of a smaller number of more fundamental entities. In games like tic-tac-toe, states are not monolithic. They can be conceptualized in terms of cells and marks. Here, for example, are two representations of a state in a game of tic-tac-toe. On the left, we have the traditional two-dimensional representation. On the right, we have a representation of the state as a database of facts. First fact says that the cell in the first row and the first column contains an X. Second cell in the first row and the second column contains a blank, denoted here by the constant b, and so forth. And finally, this last assertion says that it's O's turn to make a mark. In other words, it has control. Okay, using this conceptualization of states, we can define the game of tic-tac-toe with a small database of logical sentences, as shown here. These are all sentences in Herbrand Logic syntax written with a pure ASCII character set. First, we define the roles of the game. There are two players named X and O. Next, we characterize the initial state. In this case, all of the cells are blank, and X has control. Next, we characterize the player's legal actions. GDL makes extensive use of reductions, which are written using the left arrow operator. A reduction is simply an implication in reverse, with the conclusion first and the conditions afterward. It's more convenient to write things this way than to use forward implications. Also in GDL, symbols that begin with capital letters are variables, and those that begin with lowercase letters or digits are constants. For example, capital P, capital X, and capital Y here are variables, while lowercase b, lowercase x, lowercase y, and no op are object constants. Okay, with that introduction, let's look at this definition for legality. The first sentence says that it's legal for an arbitrary player P to mark the cell in row X and column Y, provided that it contains a blank and provided that P has control. Second sentence tells us that it's legal for X to do the no-op action if O has control. The no-op action means that the X does nothing, it passes. Analogously, it's legal for O to do the no-op action if X has control. These three axioms assure us that both players have legal moves in every non-terminal state. Okay, next we look at the update rules for the game. The cell is marked with an X or an O if the corresponding player marks that cell in the previous step. Sentence 2 says that if a cell contains a mark that is not blank, then it retains that mark on the subsequent state. If a cell is blank and is not marked on that step, then it remains blank. And finally, the last two sentences tell us that control alternates on each play. The game terminates if either player has a line of marks or if there are no empty cells. The goal rules define the player's rewards. The X player gets 100 points if there's a line of X's and no line of O's. It gets 50 points if neither player has a line. And it gets 0 points if there's a line of O's and no line of O's and no line of X's. The rewards for the O player are analogous. And finally, we define some helper relations. A line is a row of marks of the same type, or a column, or a diagonal. A row of marks means that there are 3 marks with the same first coordinate. A column of marks means that there are 3 marks with the same second coordinate. And a diagonal is a line from the upper left to the lower right, or from the upper right to the lower left. And that's it. That's the entire description of tic-tac-toe rules. Okay, one more final twist on game description, and that's obfuscation. In order to prevent programmers from building in specialized capabilities that recognize, based on specific words in game descriptions, it's common for game managers to obfuscate descriptions before game begins. All words are consistently replaced by nonsense words, as the example shown here. The only exceptions are variables and a selection of constants common to all games, such as next, does, true, and so forth. In order to engage in competitive play, general game players need a game manager to distribute game descriptions, maintain an official game state, update the state with player moves, verify the legality of those moves, and ultimately determine winners. In the case of automated general game players, the manager takes the form of a web service that performs all of these functions. A typical game manager maintains databases of game descriptions, match records, and temporary data while games are in progress. Communicates with players via TCP/IP connections, and in most cases it provides graphical representations of games for human spectators. The process of running a game goes as follows. Upon receiving a request from a game director to run a match, the game manager's first issues a start message to each player to initiate the match. The start message contains an identifier for the match, the role the player is assuming in that match, the game description, a start clock, and a play clock. Start clock specifies the amount of time remaining before play begins, and the play clock specifies the amount of time each player has to make each move once play begins. Once play begins, it issues play messages to each player. This includes the match ID and an indication of the moves made on the last time step by the various players in the match. Once the manager receives plays from the players, it simulates the results to determine the next state of the game. This part of the process then repeats. Another play message is sent, moves received, state simulated, and so forth. And this process continues until the match is over. Once the match is over, the manager issues a stop message to each player. This is useful so that players know what happened on the last move. And finally, one other function of the game manager is handling problem cases, failure to play, or incorrect moves. In such cases, the game manager plays an arbitrary legal move for the player and reports that move in the next play message. Now, that's only one way to deal with such cases. The alternative would be forfeiture. However, that's a somewhat severe consequence in a world where communications are not perfect. Also, it could give a win to a weak player just because another player failed to move in time or because an internet connection dropped. Doing things this way at least forces players to do better than random. Having a formal description of a game is one thing. Being able to use that description to play the game effectively is something else entirely. In this segment, we discuss strategies for building general game players, and we discuss some of the difficulties that need to be handled along the way. Since the game descriptions are written in logic, it's obviously necessary for a game player to do some amount of automated reasoning. There are two extremes here. One possibility is for the game player to process the game description interpretively throughout a game. Second extreme is for the player to use the description to devise a specialized program and then use that program to play the game. It's effectively automatic programming. As this is just an introduction to general game playing, we'll discuss just the first possibility and leave it to you to think about the second possibility and various hybrid approaches. As we mentioned earlier, in GDL we can conceptualize a state as a set of facts that are true in that state, such as the facts here about the state of tic-tac-toe shown on the left. Computing the legal moves in any such state is straightforward. We simply use the rules defining legality together with the facts about the state to deduce statements about legality. For example, in the state shown on the right here, we can compute the conclusions shown at the bottom. The O player has 6 legal moves, and the X player has only 1, namely the no-op action. Given a state and actions for each of the players, we can compute the facts true in the next state using the update rules. In the case shown here, we use the update rule at the bottom to compute the facts shown in red at the right. The other facts on the right are computed using the other update rules. These sentences mentioned next, they can then be rewritten with true in place of next to form a description for the resulting state. One way for a player to decide on a course of action is to use these two computations to expand the game tree. Starting in a known state, it computes the legal actions for itself and its opponents, as we previously discussed. For each combination of actions of the players, it simulates the combination to compute the next state and thereby expands the tree. Here we see the tic-tac-toe tree expanded from this initial state down 1 level. Repeating this, we can expand the tree to 2 levels, 3 levels, and so forth. Until, finally, we encounter terminal states on every branch, such as the one shown here in the middle of the bottom row. By examining the various branches, we can choose the one that produces the best payoff. Now, of course, this choice depends on the moves of the other players, and we must consider all possible opponent moves or make some assumptions about things that the other players will or will not do. In principle, this procedure allows us to identify the best possible strategy to play the game. Unfortunately, even in cases where there's a clear-cut solution, the tree may be so large as to make it practically impossible for any player to expand the game tree. tic-tac-toe, there's just 5,000 states. It's a manageable number. But there are more than 10 to the 30th states in chess. Using this approach, the player would run out of time and memory long before finishing. The alternative is to do incremental search. On each move, expanding the tree as much as possible, and then making a choice based on the apparent value of non-terminal states. In traditional game playing, where the rules are known in advance, the programmer can invent game-specific evaluation functions to help in this regard. For example, in chess, we know that states with higher piece count and greater board control are better than ones with less material or less control. Unfortunately, this is not possible for in GGP. Program cannot invent such game-specific rules in advance, as the game's rules aren't even known until the game begins. The program must evaluate states for itself. One possibility is to use general heuristics. A number of such heuristics have been proposed over the years. Goal proximity is one. Proponents of this heuristic argue that all other things being equal, it's a good idea to prefer states that are closer to goal states than states that are farther away. And distance here is usually judged by similarity between the states, the number of facts in common in the descriptions of the two states. Mobility is another general heuristic. Proponents argue that all other things being equal, it's better to move to a state that affords the player greater mobility. That is, more possible actions. It's better than being boxed into a corner. And symmetrically, proponents of mobility argue that it's good to minimize the mobility of one's opponents. Monte Carlo, originally known as depth charge, is a particularly powerful heuristic for evaluating states. Suppose a player is comparing two states with too little time to search the entire game tree descending from those states. The idea of depth charge is to play through a few complete games from each of the states being compared, making random choices until a terminal state is attained. After doing this a few times, we compare the numbers of wins and losses and select the state that leads to the largest number of wins. All of these heuristics have been shown to be effective in some games. And of these, Monte Carlo is by far the most successful. Unfortunately, they're just heuristics. They frequently fail, sometimes with comical consequences. Final match of GGP06 is an example. The game was cylinder checkers, that is, checkers played on a cylinder. The board here, although you can't see it, wraps around vertically. Recall that in checkers, a player is permitted to move one of his ordinary pieces, and his pieces that are not kings, one square forward on each turn. Here, red is moving from top to bottom, and black is moving from bottom to top. If a piece is blocked by an opponent's player, he can jump that piece, if there is an empty square on the other side. Moreover, the player must make a jump if one is available. The objective of the game is to take all or as many of the opponent's pieces as possible while preserving one's own pieces. Here we see this snapshot of the game. It's red's turn to play. What should he do? And what do you think he did? Here's a hint. The player in this case was Clune player, and had decided for some reason or other that limiting the opponent's mobility was a good heuristic. If we're to move the rearmost piece, black would have multiple possible moves. However, if it were to move the piece in front, black would be forced to capture its piece. In other words, it would have at most one move. Clearly, moving the forward piece minimizes the opponent's mobility. So that's what Clune player did. Actually, the whole match played out this way, with red giving black captures at every single opportunity. It was sad to watch, but also, I have to say, a little comical. The moral is that non-guaranteed heuristics are sometimes useful, but they are not always useful. That said, there are some evaluation techniques that always work. For example, there's no harm preferring new states to states that have previously been seen, provided there's a way to get back to the original states. Also, if a player is able to determine some observable condition that corresponds to actual distance from the goal, then it's good to minimize that quantity. Suppose the player, for example, were in a cave trying to get out. If it saw a brighter light in one tunnel than in another, it might go for the brighter light. And finally, there are some states that can be determined to be bad and avoid it, even if other states are not known to be good. For example, stepping off the roof of a tall building is probably not the best way to get to the store, at least not in the real world. This discussion of game tree search and heuristics reveals just how difficult the general game playing problem is. Monte Carlo works fairly well, but it breaks down badly in certain cases, just like the others. Fortunately, there is another complementary approach to general game playing that has a lot of power, and that is metagaming. Metagaming is the process of analyzing and or modifying a game in general, that is, out of the context of a specific match. Metagaming is usually done during the start clock period of a match, or sometimes in a separate thread while a match is being played. Typical metagaming techniques include pre-searching the game tree, optimizing the game description in various ways, or compiling the game description to achieve higher performance. In some cases, it's possible to reformulate a game into one or more simpler games, and or to discover that there are some game-specific evaluation functions. As an example of reformulation potential, consider this game called Hodgepodge. Hodgepodge is actually two games glued together. Here we show chess and Othello, but it could be any two games. One move in a joint game of Hodgepodge corresponds to one move in each of the two constituent games. Winning requires winning at least one of the two games while not losing the other. What makes Hodgepodge interesting is that it's factorable. That is, it can be divided into two independent games. Realizing this can have dramatic benefit. To see this, consider the size of the game tree for Hodgepodge. Suppose that one game tree has a game tree for one of the subgames has a branching factor A, and the game tree for the other has branching factor B. Then the branching factor of the joint game is A times B. And the size of the fringe of the game tree at level n is A times B to the n. However, the two games are independent. Moving in one game does not affect the state of the other game. So the player really should be searching two smaller game trees, one with a branching factor A and the other with a branching factor B. In this way, at depth 10, there would be only A to the n plus B to the n states. It's a huge decrease in the size of the search space. Factoring is just one example of game reformulation. There are many others. For example, it may be possible to find symmetries in games that cut down on the search space. Some games are bottlenecks that allow for a type of factoring. Consider, for example, a game made up of one or more sub-games strung together, in which it's necessary to win one game before moving on to the second game, and the second game before moving on to the third, and so forth. In such cases, there's no need to search to a terminal state in the overall game. It's sufficient to limit search to the termination in the current subgame. These examples are extreme cases, but there are many simpler everyday examples of finding structure of this sort that can help out in curtailing search. The trick in metagaming is to analyze or reformulate games without expanding entire game trees. The interesting thing about general game playing is this, that sometimes the cost of analysis is proportional to the size of the description rather than the size of the game tree, as in examples we were just examining. In such cases, players can expend a little time and gain a lot in search savings. That's pretty much it for a quick tour of general game playing strategies. I want to close this segment with an anecdote about my own early experience in general game playing. After building my first general game player, I decided to see how well it performed on a game of tic-tac-toe. I let it play blue while I played red, and here's the state of the match after 6 moves. I was intentionally playing badly to see what my player would do. The question is, what did my player do at this point? Now, if you or I were playing blue, we would probably play in the lower left or maybe in the lower right, winning the game. But that's not what the player did. Instead, it played in the upper right, the next legal move in lexicographic order. So I scratched my head and wondered exactly why it did this. I wondered if it was too stupid to see the obvious win. In the end, that's not at all the case. It was playing perfectly. It had already realized that it had a guaranteed win, no matter what I did at this point. So why not play in the upper right? It was aggravating for me as a human to have my defeat dragged out in this way. But this sort of delayed gratification is not unusual in general game playing. It's just frustrating for us humans to watch. While general game playing is a topic with inherent interest, work in this area has practical value as well. The underlying technology can be used in a variety of other application areas, such as enterprise management and computational law, science, engineering, and so forth. In the case of enterprise management and computational law, just consider that the rules of games are analogous to the laws of society, the rules of business, and so forth. More fundamentally, general game playing has value as a testbed for theories of intelligence. Game descriptions provide full information about a world and determine optimal strategies as a baseline for evaluating the behavior of actual agents. By its nature, the GGP setting can be used to evaluate problem-solving strategies, and by extension, theories of intelligence, by taking into account representation, incompleteness of information, and resource bounds. That said, it's worth noting that there are some shortcomings of the current state of GGP as a testbed for AI. First, there's the tabula rasa critique. It goes as follows. Human intelligence is arguably the product of eons of evolution. We are, to some extent at least, wired to function well in this world. General game players have nothing at their disposal but pure mathematics. Okay, that's true. However, a key indicator of intelligence is the ability of each individual to function in radically new environments, and general game playing is exploring that capability of our intelligence. Second shortcoming of GGP is the learning critique. In GGP, players are told how the world works. The critique goes that real intelligence requires the ability to figure out new environments. Okay, well, there's no question that the ability to learn is essential. However, real intelligence also requires the ability to use theories once they are formed, and that's what general game playing is emphasizing. This is really the domain of what's often called general systems or universal systems, or sometimes declarative systems. And the interest in this problem dates back to the very beginnings of the field. It was in 1958 that John McCarthy invented the concept of the advice taker. The idea was simple. He wanted a machine that he could program by description. He would describe the intended environment and the desired goal, and the machine would use that information in determining its behavior. There would be no programming in the traditional sense. McCarthy presented this concept in a paper that has become a classic in the field of AI. And let me just read this quote. The main advantage we expect the advice taker to have is that its behavior will be improvable merely by making statements to it, telling it about its environment and what it is wanted from it. To make these statements will require little, if any, knowledge of the program or the previous knowledge of the advice taker. Well, that's an ambitious goal, but that was a time of high hopes and grand ambitions. The idea caught the imaginations of numerous subsequent researchers, notably Bob Kowalski, one of the high priests of logic programming, and Ed Feigenbaum, the inventor of knowledge engineering. In a paper written in 1974, Feigenbaum gave his most forceful statement of McCarthy's ideal. He says, the potential use of computers by people to accomplish tasks can be one-dimensionalized into a spectrum representing the nature of instruction that must be given the computer to do its job. Call it the what to how spectrum. At one extreme of the spectrum, the user supplies his intelligence to instruct the machine with precision exactly how to do his job step by step. At the other end of the spectrum is the user with his real problem. He aspires to communicate what he wants done without having to lay out in detail all necessary sub-goals for adequate performance. Okay, one final remark. Some have argued that the way to achieve intelligent behavior is through specialization. That may work so long as the assumptions one makes in building such systems are true. For general intelligence, however, general intellectual capabilities are needed, and such systems should be capable of performing well in a wide variety of tasks. To paraphrase the words of Robert Heinlein, a human being, or computer or robot, should be able to change a diaper, plan an invasion, butcher a hog, con a ship, design a building, write a sonnet, balance accounts, build a wall, set a bone, comfort the dying, take orders, give orders, cooperate, act alone, solve equations, analyze a new problem, pitch manure, program a computer, cook a tasty meal, fight efficiently, die gallantly. Specialization is for insects. Those of us who are more interested in artificial intelligence than artificial insects agree with Heinlein. The main focus of the general game playing community is the annual general game playing competition. The competition is typically held in conjunction with the National Conference on Artificial Intelligence, sponsored by the AAAI, the Association for Advancement of Artificial Intelligence, or sometimes by the biannual IGCAI, International Conference on Artificial Intelligence. It's administered by Stanford University, so many of those of you who are at Stanford are not eligible to participate, at least while you're still at Stanford. The competition began in 2005 and has run annually ever since, with the exception of 2009. Here's a photo of Jim Clune on the right being congratulated by the AAAI president, Ron Brockman. He was obviously pleased at his player having won. However, that smile might be due in small part to the $10,000 he received for winning the competition. Here's Michael Thielscher and Stefan Schiffel, winners of the competition at AAAI 06. And here we have an assembly of winners. That's Helmar Finsen and Yngve Bjornsson on the left, the winners of the 2007, 2008, and 2012 competitions, together with Stefan Schiffel and Michael Thielscher, the winners of 2006, and Jim Clune on the right, the winner in 2005. And these were not the only winners. Some of the spectators even got in on the action with a bit of betting. Now, I don't want to toot my horn here, but just let me say that last year I came away somewhat wealthier than I expected at Chris Welty's expense. The format of this year's competition is typical. There will be a qualification round in June of 2013. This will be followed by a semifinal tournament just prior to the AAAI conference in Seattle. And it'll culminate in a final competition at the conference itself to determine next year's winner. And the winner will take all the glory and a chance to compete in the carbon versus silicon competition. In addition to the regular GGP competition, there will also be another battle between carbon and silicon. This will be the third such contest. Unfortunately for us, the humans are not doing all that well. This past year, Katia player, the world champion, handily defeated the human race, represented by here Chris Welty, pictured here. In keeping with the double elimination format of the competition, the contestants played two different games. In the first, Katia player easily defeated the human in a very well played match of dual Connect 4, then won a match of platform jumpers. As a consolation prize, the human was awarded 2 bottles of scotch, in part to ease his disappointment in having let down the human race. And my hope is that the prospect of receiving the scotch didn't affect his performance. Okay, for those of you who want to get involved in the competition or just want to learn more about general game playing, here's a list of resources. Games.stanford.edu is the homepage for general game playing at Stanford. And there's also a database of official competition results at gamemaster.stanford.edu. ggp.org and the general game playing site in Dresden provides support for the development of general game playing programs. There's also a short Wikipedia article. And you can find scholarly publications on GGP by Googling general game playing. Finally, for those of you who want to learn more, there will be an online course on GGP via Coursera in the spring of 2013. As part of the coursework, you'll get to build a general game player, and the course will be over in plenty of time for you to register your player to compete in next summer's competition.